Hi everyone, welcome to our annual Molecular Biology and Genetics Turkey Agenastro 3rd International Astrobiology Conference. Today, I will be hosting the first session of the day. I'm Suda Kalın. I'm a third-year biology student in Marmara University. I'm interested in marine biology, microbiology, and astrobiology. We will be opening our conference with Dr. Svetlana Shkolyar. To introduce her shortly, Dr. Shkolyar is an astrobiologist interested in life detection techniques and methods on planetary surfaces using laser spectroscopy instrumentation. She was also a member of the last two NASA Mars mission science teams, Mars Science Laboratory Curiosity rover and Perseverance rover, Mars 2020, and of the upcoming European Space Agency's ExoMars rover. Currently, Dr. Scholar is a member of the Center for Life Detection, a NASA team, that is creating web tools to help life detection mission planning efforts. Now, we will be having Svetlana Shkolyar on the topic of informing Perseverance Mars rover biosignatures. Hi Svetlana, welcome.
Hi everyone, thanks for having me.
Of course. Thank you for joining us. How are you? How are you doing?
Good, thanks. It's very early here on the East Coast.
Oh, really? If you would like to add anything to your bio, you may. And if that's fine, you can continue with your presentation, but we'd like to hear anything you might add on.
No, you gave a good intro. Thank you.
Of course.
So should I start sharing my screen?
Of course.
Okay, let's go ahead and screen share and play. Does that look okay on your end, Suda? Is that okay?
Yes.
Okay,
Yes,
great.
that's okay.
Okay, so let's jump right in. I wanted to talk today about informing Perseverance Mars rover studies of fossil biosignatures. So this talk is going to combine some of the work I did before the launch of the rover, preparing for some of the protocols and strategies for biosignature detection using laser spectroscopy instrumentation. And I will integrate some data, some hot off the press data from that was published about last year from actual studies of the Mars rover. So let's jump right in. To give you just a brief introduction, if you're not familiar, the Perseverance rover or Mars 2020 mission objectives, there are 4 of them. To, of course, understand the habitable environment that was present on ancient Mars, to go the next step and really look at the habitability and even seek evidence of past life in that environment, specifically looking for samples that may contain fossil carbon or have high biosignature preservation potential, and bring those samples back to Earth. And that's the main interest I have, and that will be the main subject of this talk. Whoops. And then sampling, of course, that's what I just mentioned, bringing back about 40 or so samples back to Earth in what we call the Mars Sample Return campaign, the MSR campaign, and finally preparing for humans. So let me give you a quick overview of what that Mars sample return strategy will look like. It's quite a complex concept. Currently, the first step is, of course, Perseverance's surface analysis of samples and caching those samples in tubes. And then after we have completed this part of the mission, there will be a sample retrieval lander, which will come pick up that little carousel of samples. Perseverance will return those samples to another lander. That lander will then transfer those samples to a set of helicopters, which will then transfer those samples to in orbit at Mars. And then a Mars ascent vehicle will transport those samples further. You can see there are a lot of transferring steps. Those samples are going to undergo a lot of steps to being very carefully moved along this chain to a capture, contamination, control, and return system, then to Earth orbit. Then they will finally be brought back to Earth, distributed among the various facilities on Earth, and given to sample receiving facilities, which will then do much more high resolution, much more in-depth studies to look for signs of life in those samples, and do additional studies, for example, assess the precise age of the rocks and the environments on Mars. And all of this will be done, of course, using instrumentation, using groups, international teams, and facilities and instruments that cannot really be done on the rover. So what I'm trying to emphasize here is simply that Perseverance rover is kind of step one to select those samples, use its very capable instrument suite. But the real detection of life won't really occur until after those samples are brought back to Earth. So here's what the rover looks like, and I'm just going to highlight a few of the instruments on the rover payload. The exciting thing about Perseverance rover is that there are a few instruments that are firsts in space, firsts on a Mars mission. Certainly NASA, but in general on any Mars mission. So these are Raman spectroscopy instruments, SuperCam and Sherlock. Sherlock is a really cool acronym. It stands for Scanning Habitable Environments Using Raman and Luminescence of Chemicals. Sherlock. And it has a camera named Watson, an imaging camera that images the regions identified by Sherlock, interrogated by Sherlock. So like Sherlock and Watson. And so these two instruments are very special because they represent many of the first laser spectroscopy capabilities on a rover in space. SuperCam is a visible laser Raman spectroscopy instrument. And after this, I will give you a little overview of what Raman spectroscopy is. But SuperCam represents the first visible, so that's visible excitation wavelength, meaning precisely 532 nanometers. So that's green laser light. The first ever green Raman instrument in space. And Sherlock is actually the first ever deep ultraviolet, deep UV, 248.6 nanometer instrument in space that does Raman spectroscopy. So not one, but two on Perseverance. Both of these are also suites of other instruments that do additional types of spectroscopy and imaging, and I don't want to talk too much about that. But the other capability that both SuperCam and Sherlock have is the ability to do fluorescence spectroscopy. Fluorescence spectroscopy is similar but also very different information that you can get from Raman spectroscopy. And again, I will show you what the two techniques can give you on one sample together. And so both of them are combined Raman and fluorescence spectroscopy instruments. And Sherlock is also the first Raman instrument to map a mineral surface composition on Mars. So why is Raman spectroscopy so exciting in space? Why is it so exciting for biosignature identification? It has a lot of advantages. It's basically, shining a laser light off the surface. You're bouncing a laser off the surface of your sample. Which gives you a very unique spectral fingerprint of that compound. And it's very precise. A Raman fingerprint, a Raman, spectral band is very precise to a very specific compound. So you can truly diagnose very precise types of organics or minerals. And you can do them together. You can identify both the organic and the context, the environment, the rock that organic is hosted in. And together that information is very powerful because it allows you to reconstruct not only if you have a biosignature, but what the environment was that preserved that biosignature, which is very, very important sometimes for astrobiology purposes. Raman spectroscopy is also non-destructive. And as I mentioned, it preserves that context, that environmental microscopic context around the organic, if you're looking at a rock with preserved carbon. And that's what I'm assuming. That's kind of my assumed scenario for fossil life detection. It's the carbon preserved in the rocks. I should mention that. So keep that in mind as we go through this. It's fast. It's unlimited. There's no shortage of laser times you can shoot the laser at the sample. unlike other chemistry instruments on board, for example, Curiosity, which are very limited by the number of cups or the number of chemical reagents that you can use. Raman does not have that limitation. And finally, you don't need to really prepare a sample. You just need to have the rock abraded or flat, so you can have the laser light scattering, get more good laser light scatter if the surface is flat. However, Raman does have a few disadvantages, as does every instrument, right? It is a laser, and lasers can be hot, and lasers can be high powered. So if you're not careful, or if the organics are very geologically immature, if you have a compound that is very sensitive to thermal alteration, you will cook it. You can basically cook the organics and turn them into something that does not represent what the original biosignature is that you're detecting. So that could be a danger. And also, you cannot prove biogenicity. You cannot look at carbon preserved in a rock and say, this carbon came from life, or this carbon came from a meteorite, or this carbon came from a hydrothermal system. You cannot say, because spectrally, at the molecular level of what a Raman spectrum will give you, you just see the carbon. And so you won't be able to say without additional, that's why you need additional suites of evidence. You need additional chemical information. And that is why, again, Mars sample return is so important, because it is going to be on Earth when you can truly look at that carbon with a variety of instruments and really understand its biogenicity, or not, because sometimes carbon is just very, very complex to understand. And finally, the last issue is fluorescence interference. I mentioned that Sherlock and SuperCam on the rover are both combined Raman and fluorescence spectroscopy instruments. But when that fluorescence interferes, when that fluorescence gets into the Raman spectrum, you get this bump that I'm showing you on these two spectra. You can see two Raman spectra, a blue one and a red one. That one with the bump with that fluorescence background, you can actually cover up Raman bands, because the fluorescence effect is much, much, much stronger. There is much more light that comes in to the detector from the fluorescence effect. So that can really, cover up very important information. And so Sherlock and SuperCam both have ways of removing that fluorescence from the Raman spectrum. And I will talk about that in a moment. But first, let me also explain a little bit what the difference is between Raman and fluorescence. Raman is an inelastic scattering. It is the Stokes scattering effect, if you're more familiar with that term. Basically, the laser bounces off the surface of your sample. It has an incoming wavelength, and it has an outgoing wavelength that is changed by the molecular structure of your sample, by the chemical structure of your sample. And that difference of wavelengths is called a Raman shift, and it is measured in wave numbers. So it's the inverse of a wavelength. So that's how we quantify it. And it's a very, very low number of photons that undergo this effect. So it's a weak effect in the detector compared to fluorescence. And as you can see here in this diagram, fluorescence is a true absorption. Light is truly absorbed, energy is lost, and then it is re-emitted. It is cascaded back down to the ground electron state at a time later. And that is a very, very strong effect, because that light is truly absorbed and re-emitted. So when they compete in the same spectrum, you can see how the fluorescence effect will definitely sort of overwhelm it. However, as I mentioned, both Sherlock and SuperCam can do both types of detection, and both separately can give you very important information about a sample. And I will show you how in the samples I've looked at and in the samples that Sherlock is looking at, those two techniques can be used kind of together to give you complementary information when they are detected correctly and separated in the instrument. Both Sherlock and SuperCam onboard Perseverance rover have a way to separate this fluorescence, to remove it from the Raman spectrum, at least when you're trying to just get the Raman information. And those two techniques are time resolution and ultraviolet UV laser wavelength excitation. So first, let me pause for a minute and go into the SuperCam's fluorescence strategy. before I get into any of the data. Fluorescence the fluorescence strategy for removing fluorescence, the strategy for removing fluorescence in a green excitation, 532 nanometer excitation instrument like SuperCam is to use time resolution or gating. Basically, what this means is the detector chops part of that signal off. It puts a gate in front of that signal. So if you look at Raman, and fluorescence and time in a 3-axis system like I'm showing here, you will see a laser pulse, that green pulse. And the Raman spectrum is basically these tiny little peaks, what I'm indicating with those red peaks, and it basically happens at the same time as the laser. The Raman effect is fast, but the fluorescence effect is much slower, and you can see it has this much, much bigger, broader kind of feature that's long in time. And you can gate that time anywhere you like. You can gate short gate or long gate, and you can basically chop off the rest of that fluorescent signal. So that's what time resolution is, and that's what SuperCam uses. What Sherlock uses is simply moving to a different wavelength, to the UV wavelength, to the deep UV. And so in that case, if you imagine Raman plotted against the excitation, the laser's excitation wavelength and intensity, if you imagine that three-dimensional space, you will again see, as you can see, the theme is fluorescence is a very, very broad, very long effect, and it's also very long in wavelength space. It spans many hundreds of wavelengths. That's the fluorescence. One fluorescent signal from one sample can be this big. Whereas the Raman information is these discrete little bands that basically sit on top of it. And by moving to the UV, so moving towards down in this diagram, away from visible towards the UV, you can see how the Raman information is basically separated out, and it basically comes out to the tail end of the spectrum. So a conventional 532 nanometer instrument would give you fluorescence roughly where I'm pointing in, between at 532 nanometers in this diagram, which you can see is still pretty high on that fluorescence signal. And compared to Sherlock, which is 248.6, so again, that's deep ultraviolet, you're going down in wavelength space and you're separating out the Raman effect towards the tail end. So you can see how that would reduce fluorescence. And I'm also going to talk about another instrument that is similar to Sherlock that I used in some of my strategy pre-planning experiments before the rover launched. And it was a UV system at 266 nanometer excitation. So similar to Sherlock, but still a little bit different. But you can see that this would also mitigate the fluorescence. So now I want to share with you a little bit of data that I did when I was trying to understand how to reduce fluorescence in Raman spectroscopy instrumentation when I was looking at these very challenging Mars analog samples. This was part of my dissertation work. So again, this was several years before Perseverance launched, and we were trying to understand and trying to help the team understand how to do these Raman data collection protocols on Mars. And I should mention that Mars samples, we expected them to be highly fluorescent because the kind of environments that we knew we would encounter on Mars, sulfate-rich, clay, phyllosilicate-rich environments that are good for preserving habitable environments and preserving signs of life, actually in the Raman spectrum are known to be very fluorescent. So we knew this was going to be a challenge when we started. So let me introduce to you some of the work I did. I'm going to start with a case study at a Mars analog site where we went to collect Mars-like samples containing fossil carbon to inform Perseverance rover studies. This was a site in central Arizona, which was an evaporitic playa. So again, containing a lot of the similar types of environments that you would expect in Jezero crater. Water, full of water in the past, but then it, basically evaporated, and this is now a desert in Arizona. And what I'm showing here is actually there was a NASA website that features Mars analog sites, and you can kind of play around and you can compare how those sites compare to their space environment. And I submitted the pictures of my field site, and they turned it into this really cool image where you can flip this white screen and toggle back and forth between Mars, and between the Arizona site. So if you haven't seen this website, it's solarsystem.nasa.gov, and there's the full link. I encourage you, if you're interested in planetary analog field sites, there are a lot of really interesting sites that you can play around with. So we went to this site, we collected samples containing carbon in the form of kerogen, and we looked at it under various Raman spectroscopy instruments. Kerogen is basically a macromolecular carbon. It's basically aromatic rings. It is the most common biosignature on Earth. If you look at basically fossil carbon on Earth in rocks, like you would expect to see on Mars, the majority of the organics you would see would be in the form of this macromolecular clumps of aromatic carbon called kerogen. And that is why this is the specific type of biosignature that I was targeting in all of my work. And if you look at kerogen in a Raman spectrum, this is kind of what you will see. And I also want to introduce a few other features that you would see in a Raman spectrum if you were looking at any Mars analog sample. You would see minerals. All of the Raman spectral information from minerals would be kind of below about 1,000 wave numbers, so kind of the first half of that spectrum. And really, the majority of the organics that we're interested in, and particularly the spectral bands from kerogen, which look like these two bands here that I'm showing, around 1350 and around 1600 wave numbers, they appear kind of in the second half of that spectrum. And you can see in this spectrum, you do see a little bit of that fluorescence, but it's okay because there's so much kerogen, you're not having any issues with the fluorescence overwhelming the Raman information. But this is kind of a best case scenario of what you'd like to see in a good Raman spectrum. And so we took the samples from that field site I mentioned in Arizona, and we looked at them with the UV, the 266 nanometer, the UV instrument that I mentioned in the lab of my collaborators at York University, actually in Toronto, Canada. And we wanted to understand how these very realistic samples would behave in a UV Raman system. And this is also a fluorescence system too, but we're looking at the Raman spectra, and I will show you the fluorescence spectra separately. And again, what these instruments can do, what Sherlock and this instrument that I used can do, is on the same sampling volume, you get both. You get the Raman and the fluorescence spectrum. You just have to interpret that information separately, and you look at it separately, and you can get complementary information, which is what I will show here. But so let's start with the Raman side of things. We see kerogen. Good news, we see kerogen in our samples. We see one band from the kerogen. Here's the pink overlay of the organics, and then in the blue portion of the spectrum, we are seeing the mineral that kerogen is encapsulated in. So these are rocks rich in quartz, rich in calcite, calcium carbonate, and rich in gypsum, which is a sulfate. So that's good. And we're not really seeing too much fluorescence. And now I'm overlaying the fluorescence lines. You can kind of see at the very past 2000 wave numbers, you can kind of see some of this fluorescence. But again, it's removed so far away from the organic and the mineral regions of the spectrum that it's not really preventing. There is Raman information in that region between 2500 and 3500 wave numbers, but for this study, that wasn't important to us, and we didn't really need it. So the conclusion that I came to in this study was, yes, the kerogen and its hosting minerals were successfully detected with minimal fluorescence interference using this UV system. So that's good news. However, in one sample, you can see that we don't have any. You can see that one sample basically has no mineral or Raman information, and it was the second spectrum, this iron-rich mudstone. And I'm showing you a microscopy image of the orange, these bright orange iron-rich phases in that sample preserved within that gypsum. The white is gypsum, and the orange is these iron-rich, very micro-scale phases. And this was actually this sample actually created a lot of problems in our study, because what we learned is that in the UV, you have strong absorption near 266, near the excitation wavelength. And that UV absorption basically, it's due to iron coordination complexes. So in samples that are rich in iron, but we don't know how much iron. When you have basically iron-rich samples, you will get so much absorption that you won't see the Raman. It will also absorb the Raman information. So in a sample that we knew contained a lot of minerals that obviously have very detectable Raman spectra and a lot of kerogen, we did not see it. But you may be wondering, well, obviously Mars is full of iron. Is this going to be a problem for Sherlock? We're working on that. We are trying to, members of the team are trying to understand, is it certain iron phases? Is it certain abundances of iron phases? Is it certain types of coordination of the iron? I'm not sure, but work is definitely undergoing. So what I just showed you was, pre-planning studies before Perseverance's launch. Now I want to show you what the actual Sherlock data was with Raman spectroscopy on Perseverance rover. So this is from a paper our team released last year. So this represents basically the first 200 or so days on Mars, what we call sols. And this is kind of a representation of the Raman data that we're able to see on Mars. This is I'm showing only one spectrum here. In A, you see, in image A, you see basically a rock called Bellegarde. That is the target. And those boxes are different instrument footprints, the different imaging areas of the instruments, including the Sherlock one, which is, I think, the white. Sherlock is that smallest white one. So you can see how much of that rock, based on the scale, was sampled. And Sherlock actually mapped. So these little red in picture C, you see these little red dots, that's the map. So it took a spectrum at every point step, some number of millimeters step across that whole two-dimensional area. And so in B, I'm showing this black and yellow Raman spectrum. And in the spectrum, you can see a peak from sulfate. And that's it. And again, let me highlight the organic range. You would expect the organics to be in that 1350 to, a little past 1600. Well, here I'm showing from about 1200 to 2000. And you can see that there are no organics in that spectrum. And this is really representative of the data I've seen recently on Sherlock. There's largely good mineral information, but very limited to no organic information. And in this Scheller et al. 2022 paper, they concluded we did not detect Raman peaks consistent with aromatic organics, and organic concentrations were likely insufficient to produce Raman, either because of low concentration or the organics were just so degraded by the UV radiation environment or other things. But perhaps it's one of the reasons that we found in my study. Perhaps it's also this iron coordination absorption issue. I don't know, because these samples are actually, as I'm showing you, sulfate rich. They're looking at regions that are high in sulfate. So there shouldn't be too much iron where these spectra were taken. So that's the Raman side of things. I want to now switch gears to the fluorescence. I've been treating fluorescence spectroscopy as the bad guy, as the thing we want to get rid of in a Raman spectrum, right? And I want to show you the other side of that coin. When you get combined Raman and fluorescence info, what the fluorescence will say. And I want to make the point that it's actually very valuable. And sometimes the fluorescence will tell you more than the Raman. and sometimes it will tell you less. The key is each instrument, each technique has weaknesses, and it's only together that you can really see the sort of a bigger picture of your sample. The biggest weakness of fluorescence is that, as you can see here, the spectra are very, very broad. The bands are so big and so broad in time and in wavelength space that you can't get specifics. You cannot say that you have a specific, a benzene or a tryptophan compound or a kerogen compound. Or maybe you can say you have that class of organics, but it's very, very hard to really precisely say as well as you could in Raman. So fluorescence spectroscopy does not diagnose. All it does is it gives you kind of a general overview of what the fluorescence might be caused by. So with that, let me show you two spectra of organics and, well, kerogen specifically, and organics that were not in kerogen. So we looked at regions where we knew there was kerogen in my samples, and this is what a fluorescent spectrum of kerogen looked like every time. I'm showing you in the first spectrum. And you'll see that in all of these samples, kerogen is basically this very broad band or bands, probably a convolution of many bands. In some cases, you can see it's a convolution of different bands that is centered roughly around 430 nanometers. And remember, fluorescence spectroscopy is measured in wavelength, so nanometers. And I'm also showing you this gray zone. And the gray zone is basically Sherlock's range. So Sherlock has a window that is very small. It can go from about 250 to about 360 nanometers. And that is not a lot. That's a little over 100 nanometers in wavelength space. And the reason it does that is because they targeted specifically a region of the fluorescence spectrum, which is known to be only rich in organics. It is thought that if you're going to find organics on Mars, that is the window where you should look, because yes, there are organics outside of that window, as I'm showing here, but really that's like for DNA, for various organics that are more extant. So maybe not fossil organics, but at least smaller organics and compounds that are associated with extant life. You would see them in this very, very narrow window that I'm showing in gray. So that's kind of bad news for kerogen, as you can see, because kerogen has a peak well outside of that window. But you can still see the tail in Sherlock. And you can see that kerogen does look consistent. It has a peak that is kind of similar across very different samples. And the other good news is that when you're not looking at kerogen, when you're looking at other organics preserved in these types of sulfate, evaporite, limestone type rocks, you will see the other organics that look like this. They have basically this sort of kind of a double, maybe even a triple feature convolved together that peaks somewhere between 400 and 450. And the other really good news about this is that, remember that sample that I told you was iron rich, that didn't have any information in the Raman spectrum? Well, we do see organic information in the UV fluorescence spectrum. We are picking up organics. So where Raman didn't give us any information on that same sample in the same spot, in the same sampling volume, fluorescence spectroscopy did. And that leads us to the conclusion that fluorescence from kerogen does reveal a distinguishable feature from other features. And even when those features are not detectable with Raman, organics are detected in at least this one iron-rich mudstone sample with fluorescence spectroscopy. So this shows you kind of the two sides of the story, where one instrument doesn't give you the information and the other one does. And this is probably why Sherlock is a combined, well, Sherlock and SuperCam are both combined UV fluorescence and Raman instruments. There are also other things that fluorescence can do that I'm not talking about here, including, for example, giving you the decay lifetime of that fluorescence. And that can give you information on organics too. But I'm not showing that data here. That's in the paper if you're interested in this, in that work. That's in this 2018 paper. Now, there's something very interesting that we also discovered on the fluorescence side when we looked at the mineral standards. So now I'm showing you the third spectrum here, which is the standards that, like the powdered, clean, quote unquote, clean laboratory mineral standards that we looked at: gypsum, silica, calcite, and dolomite, which represent the main minerals in these natural rock samples. And we looked at these mineral standards just to confirm that there would be no organics in the fluorescence spectrum. However, we were surprised. You can see that some of these samples have organic features right in the same area as in the second spectrum here. Like that dolomite standard has a pretty big organic feature. And the other ones, you can see it's kind of small. It's not as large as that peak around 350 or 325. But it probably is organic contamination. So we're not going to be too worried about that, because I really think that because the fluorescence effect is so strong, we try to avoid, fingerprints and other contaminants. But I think these samples are ultimately not super clean and they are contaminated. So we did see some organics. However, the main surprise in these data is that in the mineral standards, you see these peaks around between 300 and 350 nanometers that are in Sherlock's organic range. Remember, that gray zone is what I told you is the window of the fluorescence spectrum in Sherlock, because that is where you're supposed to find the majority of the organics that we want to find on Mars. Or at least that's how Sherlock's engineers tuned that instrument. So the question becomes, why are we seeing mineral fluorescence signals in an organic window of the fluorescence spectrum, in a window where we expect to see nothing but organics? So this led to another study that I worked on. And this was before the launch of Perseverance. So I really wanted to help the team understand if this could be a false positive source of biosignatures with the Sherlock instrument. So I did some digging, and I learned that there are actually some rare earth elements that do produce in the organic Sherlock's organic window, and particularly cerium. Cerium is a common substitute for cations like calcium in many, many minerals. And you can see that cerium has a beautiful peak right in the middle of Sherlock's organic window. So my hypothesis was maybe this is cerium in these samples. Now, if we look at Jezero crater and we look at the kind of minerals that actually produce fluorescence spectrum, these are pure minerals that one study looked at, and they looked at UV excitation. And they found that this whole table of minerals does have strong UV excitation in 266 nanometer UV instruments, maybe due to cerium, maybe due to other things. And this group of minerals is quite prevalent in Jezero crater on Mars, where Perseverance landed, right? Sulfates, we see sulfates in Jezero. Carbonates, we see carbonates. Phyllosilicates, pyroxenes, all of these lithologies that are known to have high UV fluorescence are present at Jezero. So then I concluded we can assume that cerium will be present at Jezero and it will be detected by Sherlock. We went one step further in my study to see what organics does cerium actually look like when you look at it with a UV fluorescence instrument. So we took a variety of organic complexes, and I've separated them out here. You can see that we had everything from fatty acids to alkanes to nucleic acids, aromatics, aromatic aminos. Then we had the cerium standards that we synthesized. We synthesized cerium phosphate at different concentrations of cerium, and we plotted them all together here. And this was our result. And again, I'm highlighting in gray Sherlock's window. And what you can see from this plot is that tryptophan, specifically the amino acid tryptophan, looks just like cerium phosphate. Both of them have bands roughly around 325, 320, and 338, 340. And now again, let me emphasize, there is no precise alignment. This, plus or minus 5 nanometer difference is really not important, because the fluorescence spectrum is highly sensitive to concentrations, to the specifications of your instrument. So a few nanometers shift doesn't mean anything. It's that imprecise. So what we can conclude is cerium mimics tryptophan in UV fluorescence. How does that differ with different concentrations? You may think, well, okay, if we went super low concentrations of cerium, maybe that wouldn't be the case. So we synthesized, we doped Mars analog soil with different concentrations of cerium. We took MGS1. MGS1 is a common Mars soil simulant created by NASA that we use in Mars analog studies. It has the mineral composition of your average soil on Mars. And we doped it with different concentrations of cerium, in concentrations that were actually taken from meteorite abundances. So we know cerium is present on Mars because we see it in Martian meteorites at concentrations ranging from very little, 50 parts per million ppm, to like thousands of ppm. So that's what these concentrations were based on. And so I'm plotting the fluorescence spectra of all of these different soil stimulants. And you can see that in every single one, any concentration we looked at, even those that were realistically expected on Mars, super tiny, we were seeing the same result. We were seeing these features between 300 and 350, so around 320 something and 340, and that is not good. Again, false positive organic detection. But surely, if you looked at the Raman spectrum of that same sample, of those same cerium doped Mars soils, you would see the phosphate, the mineral peaks. You would see that in the Raman spectrum, and you should be able to determine that this is a mineral, not an organic compound. That's what we thought. So we took the Raman spectra of all of these samples. And as you can see, these Raman spectra are pretty bad. They're pretty flat. You see this little like zigzag in kind of feature. This is not Raman. This is not a Raman signal. This is an artifact from the instrument. And you can see at 0, you can see the peak from the laser. That's the laser excitation. So essentially, this is giving you 0 Raman spectral compositional information on these samples. So we can conclude several things from this study. We can say that the UV Raman side of the instrument did not identify cerium. And the reason for this is because, just like we saw with the iron, cerium also has very strong absorptions of scattered light in the region between 255 and 340 nanometers. And again, the wavelength, the excitation wavelength of this instrument was 266, so right there in the middle of that range. And Sherlock's is 248.6, so very close to that range. So we would not expect to see cerium or the phosphate or the minerals that the cerium is in on a UV Raman instrument, even if we're looking at these high concentrations. And these samples are really an example of a UV fluorescence signal suggesting a potential biosignature on the fluorescence side, with no additional evidence provided on the Raman side. And you can imagine how on Mars, this is going to be a problem if Sherlock sees this for sample caching scenarios. So that was what my study predicted when we published this in 2021. So let me actually show you. This is one of my last slides that I'm going to show, and then I'm going to wrap up. So this is the data from Sherlock on fluorescence from three targets that were sampled for their potential to contain organics. So Guillaume, Bellegarde, and Garde. These are what the 3 rocks look like with when the rock surfaces were abraded, so flattened. And you can see these are the images with the Watson imager, the camera on the Sherlock instrument. And on the right, you see the 3 fluorescent spectra. And in each case, we had 3 different regions of interest, ROIs, that we picked in these 3 samples. And so you can see some organic information. This is good news. Let me overlay the organics that we did see in these samples. So for example, these benzene-like organics, this first blue region that I'm highlighting, these are single-ringed aromatics, probably very, very broken, small organics with 1 ring. And they peak roughly between like 270 and 285, something like that, in Guillaume and Bellegarde. Let me jump over to the third one, the naphthalene-like organics. So these are a little bit bigger. These are double-ringed organics. Probably that this is what the team concluded these features were due to, peaking roughly around like 325 to 345. And again, that's the range where I expected to see cerium in my study. And sure enough, they concluded that, well, it could have been naphthalene-like organics, or it could have been cerium. They could not tell it apart. And you can see another region of organics in this Bellegarde, in the second rock target, between like 295 and 310, where they're calling it a combination of single and double ringed organics. So 3 precise regions of potentially organics, potentially cerium. We weren't sure. And what the Sherlock team concluded is that they did identify potential organics. And again, I'm calling these potential organics in samples on Mars, but in some cases, cerium couldn't be ruled out. And Bellegarde, so the second rock here, Bellegarde is one of the samples that is actually being cached for a return to Earth. So this Bellegarde rock is in a tube that is going to be hopefully brought back to Earth, which is very, very exciting because we do see potential organic, potential cerium information in it. And of course, more information about the organics, the nature of the organics that Bellegarde contains, will be answered after Mars sample return. The team said that it could be like some other contaminant in the dust, or it really could be degraded organics that were truly preserved in the rock. So that's very exciting. And this is real data from Sherlock that we will have to wait until Mars sample return, probably in the late 2030s, to learn more about this rock. And that was only one example of a cached rock. There are something like 15, I believe, that have been cached to this point. So finally, let me conclude with a few takeaway messages, just to leave you with some of the highlights from this talk. Raman spectroscopy can detect organics as well as their minerals in context, and that is why it was debuted on the Perseverance rover for the first time. That is the power of this technique. When combined, Raman and fluorescence spectroscopy together, as we saw in the Sherlock, as we saw in my lab study of a UV instrument, could enhance the ability to detect biosignatures. It could give you a better picture together when you see both sets of data. But we've still had issues with both false negative detections, like with the iron-rich sample not giving us any organic information, and we've had false positive cases with the cerium, which can occur with this type of combined UV Raman and fluorescence instrumentation. And we really need to do more work in the laboratory. I do have a colleague who's doing more work on the cerium side to figure out, to help inform future Perseverance mission studies. And finally, the Mars sample return campaign is really strong right now. It's got a lot of support, a lot of funding. It's going strong within the NASA program to select the best samples for return to Earth, which may contain evidence of preserved carbon as life in the rocks. Keep in mind, though, that the Mars sample return campaign is also collecting samples that don't have carbon for other research, for geochronology, age dating, and things like that. And Perseverance rover is actually actively analyzing and caching those samples as we speak to determine whether life occurred on Mars, and those life detection studies will occur when we bring those samples finally back to Earth. So I'm looking forward to that. Okay, and that is the end of my talk. There's my contact information if you have any questions for me. This work was done in thanks to many of my supporting agencies and sponsors and everyone from the folks I worked with at York University to where I work now at Goddard. Of course, Blue Marble. I know there are a lot of Blue Marble folks at this conference. And thanks to the Mars 2020 team. And thanks to my funding at the University of Maryland for allowing me to speak to you today. And that's all.
Thank you so much for joining us today. Hello?
Hello?
Can you hear me well?
Yep, I can hear you.
Thank you so much for joining us today. It was a pleasure, and I really enjoyed the topic as well. Now, if you'd like to, we can have some questions. We
Sure.
have a lot of. You can maybe close the presentation. Okay, I removed it. Okay, I got it.
Okay.
So now, can we use another nanometer that tryptophan gives signal? Is 255 340 nanometer the only interval that we can determine tryptophan? Sorry.
No, it's not the only wavelength. You can determine, you can use, I've seen fluorescence instruments at various wavelengths from visible to ultraviolet. You can use different types of wavelengths. As with any instrument, you're going to have trade-offs. You're going to have a reduction in signal or an increase in, artifacts, or the acquisition time will change. So no, it's not the only. You're right. It's not the only wavelength. And if you use different excitation wavelengths, the tryptophan signal will also shift in a fluorescent spectrum, not in a Raman spectrum. The Raman effect is anchored to a particular Raman shift. But again, as I mentioned, fluorescence is so much harder to work with. So yes, you're right. There will be shifts. It's not the only option you have. The purpose of my study was to inform Sherlock. So I found a UV instrument that was 266 nanometer, and it was supposed to be as close as I could find to a fluorescence instrument on board Sherlock. And that was my goal going into the study, unless I was using the breadboard. At NASA Jet Propulsion Lab, they built an instrument that is a duplicate of Sherlock, and also at NASA Johnson. So those are exactly the same wavelength, exactly the same instrument parameters as the Sherlock will have. And I didn't have access to those NASA breadboard instruments. So I found some collaborators at York University who had something similar. So that was the purpose of my study. But you're right, it's not the only option.
Great. Another one. Do you use machine learning in any area of biosignature identification, or do you use any ML in any other areas of astrobiology? If so, may you explain a bit and give some keywords to search?
I do not. I do not do any computational or machine learning in my work. Some names, some of my colleagues at NASA Goddard, they do. And specifically for astrobiology, to look at, I think that trying to characterize habitable environments. I would give you some names to search. Bethany Thieling, Theiling, Thieling. She's a colleague of mine, so look for her papers on machine learning. And also Lu Chu. Her name is a bit hard to spell, Louth, but it's pronounced Lu. And Chu, Chou, I believe. And she works with Bethany, so look for her papers too. Those are the top names that come to my mind on my colleagues, astrobiology colleagues, that do use machine learning for astrobiology.
Okay, another question. Did we ever have an alternative before RS to have spectroscopy fingerprints?
Yeah, that's an interesting question. Are you referring to instruments that have gone like to Mars on planetary missions, or just in general in the laboratory? Because if you're referring to Mars, We have had instruments that have given us spectral fingerprints. Yes, on Curiosity rover, we had ChemCam, and that instrument was sort of like, it was SuperCam. SuperCam is built based on ChemCam, so it did have the ability to do laser-induced breakdown spectroscopy, LIBS. So you can chemically fingerprint minerals that way. In terms of spectral fingerprints for organics, Raman is the first on Perseverance. We did not spectrally identify organics with zero sample preparation before Perseverance. On Curiosity, we did have the SAM instrument, the Sample Analysis at Mars instrument. And that was a chemical, it was what they call a chemical wet lab. So you had to powder the rock, completely destroy the chemical context, put it in a cup inside of a carousel with a chemical reagent, and use high heat basically to do what we call mass spectrometry on that sample. So observe what compounds come off at high heat temperatures.
Another one that is really close to this is, how does RS keep the thermal alteration to organics in an endurable way, or this con is an often problem?
It's a big problem on Earth because on Earth people try to analyze minerals and organics using similar settings, and really if you're looking for organics, you have to use very different settings than minerals. On Mars, what they do is they just simply use lower power. Well, that's the strategy you would use anywhere. You just go down like to milliwatt. I would say like 1 to 10 milliwatts in power is probably good. On Earth, you have very, very sensitive Raman instruments that can go way less. And you can even focus, the way you focus the laser, you can focus inside under the surface of the rock. And that's called confocal Raman. There are some very powerful laboratories on Earth where you can do that. And so that really removes any kind of thermal issue. That's not as doable easily on a rover, but yeah, there are ways to remove the thermal alteration. So,
okay. How does the Perseverance tool analyze the samples it collects? How does it know what these samples contain?
Oh, that's a that's a very big question. Well, there's a different answer for every payload instrument, right? There are, I didn't talk about the other instruments on Perseverance, but there are, for example, Pixel, the I'm blanking on what Pixel, the acronym stands for, but it is an X-ray fluorescence instrument, so you can get elemental compositions in the rocks. There are, as I mentioned, the 2 spectroscopy instruments. It really depends on the instrument. Every single instrument is supposed to work kind of together to give you a holistic view of one rock. And I only showed you the 2 capabilities on Sherlock. But for example, there has been a lot of work showing that Pixel, the X-ray fluorescence instrument, combined with Sherlock, can give you additional chemical and elemental information on one sample in the same sampling volume. So that's a really complicated question to answer. I hope that was sufficient.
No, it was great. This is actually my question. How did the actual Mars samples and Mars analog sites differ in general, but specifically in Raman technique search? Was the difference big enough to tell them apart as different planets?
You mean the different rock targets sampled on Mars?
Yes.
We did see differences, usually in the environment, usually in the composition of, like, for example, olivine and feldspar to more aqueously altered phases. So we did see the same, categories of mineral phases that we expected to see. We knew there'd be a ton of olivine. We knew there'd be a ton of sulfate, because sulfate is a habitable, a mineral that forms in ancient aqueous habitable environments. So it was the proportions of these phases that we saw. In some cases, textural information. So the way the minerals were sort of what we call the paragenetic context of these minerals, how how they were preserved and what phases came through secondary, what phases were there originally, that type of thing. So reconstructing the environment, yes, you can see differences. There were different samples collected from the delta, the ancient delta in Jezero. There were different phases collected from the sort of the overlying units. And yes, we can see differences as the rover continues to rove and sample these different regions within Jezero crater.
Mm-hmm. Also, do we know why Mars is so iron rich?
Oh, yeah, I mean, I think there are a lot of hypotheses as to why Mars is iron rich. I don't closely follow that particular side of the science. I can tell you about ancient aqueous habitable environments, but in terms of environments that were altered by the iron, it has to do a lot with the aqueous history of the planet and just the evolution of the planet.
Mm-hmm. Let's see. Sudanaz asked if strong UV absorption is a problem and messing with the results, how can we detect other elements with fluorescence spectra, or how can we be sure?
Absorption. Yeah. Again, my work found that the UV absorption was an issue, like I said, with the iron-rich phases and with the cerium-rich phases.
Mm-hmm.
If you're not looking well in other, I mean, we've successfully detected other mineral phases with Sherlock. So I suppose if you're looking at different types of minerals, then it's not necessarily a problem. And it's not necessarily a problem in all iron phases either, because obviously Mars is very iron rich, and they wouldn't have sent Sherlock to Mars if this was going to be, of a very pronounced problem. I think it comes down to different types of iron and different types of cerium, really, really understanding the nature of the coordination and the bonding environment, the chemical bonding environment within those phases. Maybe in this case of iron, it's also an abundance question. How much of it? Is it in phases that are detrital, meaning they came in later, or is it in the primary fabric, primary, hosting phase? So with iron, there are a lot of questions that are still being answered. With cerium, I should say that we only looked at cerium phosphate. So keep in mind, there are a variety of minerals that can trap cerium as a rare earth element, as a substitute for example, I mentioned calcium, and probably other phases, maybe other phases too that I'm not aware of, other elements too that I'm not aware of. So I have a colleague looking at that question, and I don't know what the answer is. Her paper hasn't published yet.
Wow. Well, thank you so much for everything. It was so good. And now we answered all the questions we had.
Oh, good.
And if you want to add anything, we're open to that.
No, thank you for inviting me. And if anyone has any more questions, feel free to send me an email.
Thank you for that. I hope to see you in the future too. And thanks for coming to our conference.
Thank you.
Have a nice day.
Thanks.
Days.
Hi everyone, I'm Zainab from Agenastro. You know me from previous years. I'm one of the founding members of Agenastro and I'm the coordinator of this organization and previous year's conferences. I am a master degree student in microbiology department at Istanbul Medipol University and I'm aiming a future career in astromicrobiology. Today is the World Quantum Day. Therefore, we want to talk a bit also in astrophysics. Dr. Christophe Grojean is professor at Humboldt University and a leading scientist in Dutch electronensynchrotron. He is working on particle physics, especially Higgs boson in CERN. He is a writer of a book named Higgs Boson, The Ultimate Building Block of Matter. He will talk today about decoding matter and its fundamental interactions. Hi, Dr. Grojean. How are you?
Hello, yeah, pleased to meet you.
Nice to meet you. We are really happy to welcome here.
Very pleased to talk to you today, yes.
Did I forget to mention anything about you, or if you want to add, you can?
No, nothing, it's fine. Yeah.
Okay. You can share your screen and you can start your presentation.
Okay, so hopefully you can see my slide now. No?
Yeah. Okay,
Okay.
I take to the screen. Yeah, we can see.
Okay,
Yeah.
I'm full screen now, so hopefully you can see
Yeah, it's
everything.
full screen. Yeah, we can see.
Okay, perfect.
Okay, stage is
So,
yours. Thank you.
good, thanks a lot. So, of course, I mean, I'm planning to give you a little presentation about, our current understanding of matter, the fundamental constituent of matter, together also with the way those fundamental constituents interact with each other. So, namely, what are the forces among those building blocks of matter, right? In case you have any question, I mean, don't hesitate to interrupt me. I mean, if it has to be an interactive discussion, that will be even better, right? Okay, good. So let's start from the beginning with a simple puzzle, simple quiz. The quiz is the following, how high can you jump with a pole, with a wooden pole? You know that the best athlete can reach something like 6 point something meter. Um, but when I was a kid, I was asking myself, I mean, to jump higher, it's very simple. I just need to take a longer and longer stick, a longer and longer pole, right? But actually, fortunately, I think I've learned a little bit of physics, and I understood that it doesn't work like that, right? It doesn't work like that simply because you have energy conservation. So this means that the higher you can jump actually is related to the faster you can run. And a very easy equation, just converting your kinetic energy when you run into gravitational energy will give you this simple relation that the height that you can jump is related to the squared of your speed divided by this gravitational interaction or gravitational constant, gravitational accelerations. And now if you put a number, the fastest man on earth, Usain Bolt, that in Berlin in August 29, actually he reached the maximal speed of 44.72 kilometers per hour, right? And then if you use this formula, if you remember the value of this gravitational acceleration, you see that in principle, really Usain Bolt could jump 7.62 meters. By the way, it's very interesting, that how high you can jump actually is related to how fast the moon turns around the Earth, right? Because you have really a universal gravitational interaction, G, right? And this is the same force, the same interaction that control really the interaction between, a human that is trying to jump on Earth and also the moon, which is turning around the Earth, right? The only difference is really the distance, right? The distance, because the human is closer to Earth, and the moon is something like 380,000 kilometers, right? But so that makes clearly gravity a little bit weaker because you are further away. But otherwise, you have really experiencing the same gravitational accelerations. So the magic about this little exercise is really energy conservation. You have a conservation, a quantity which is always conserved, whatever the interaction among the particles, whatever the interaction among the human and Earth is going on. So over the years, we have learned a few other conservation laws that tell us what an athlete or what a particle can do or cannot do. Right? And I think there have been a remarkable breakthrough in the understanding of nature is that the forces among the particles are actually associated to symmetries. So this is a famous Noether theorem from the beginning of the 20th century. Right? So why energy is conserved is simply because, the laws of physics are invariant by time translation. Whether I'm doing the experiment today, tomorrow, or in 1 year, I should get the same result. Physics is invariant by time translation. And simple consequences of this invariance is really that energy is conserved when you have interactions. So that was a simple and well-known conservation energy, but later on, really people understood that there is further quantity that are conserved, and that lead to new interaction among the particles. So the typical example that you may be familiar with is actually electromagnetism. Electromagnetism, so the interaction, let's say, of the electrons with an electron. So you take two electrons, you want to collide those two electrons, and then there will be a scattering, right? So they will go away with some scattering angle. So what is this electromagnetic interaction? So how it is related to a symmetry? Well, the fact is that an electron, is a spin one particle, so it's described by a wave function. The wave function in quantum mechanics is just giving you the probability of finding the electron at a given point of space and time, right? And this wave function is actually a complex number. And what physics is telling us is that the phase of this complex number is something which is not really physical, right? You can rotate the phase of the wave function of the electron. So you have something that remains invariant when you perform a rotation of the phase of the wave function of the electron. Right? And the invariance, the symmetry, really imply the electromagnetic interactions. Right? That's really a remarkable breakthrough in the understanding of nature, is that really all the fundamental interaction among the particles are associated to symmetries. Right? So then the next question is really, what are the symmetries that exist in nature, right? And that's really the purpose of this lecture, to explain to you what are those different symmetries. So nowadays, we really understand the standard model of particle physics based on these following symmetries. So first of all, you have space and time rotation. So you can perform rotation in space, but you can also perform rotation in time. And moreover, that's what is called a Lorentz transformation. You can change space and time, right? And that's at the heart of special relativity. And I'm going to explain to you a little bit more about special relativity in a moment. Right? So that's basic symmetry of space-time. But in addition, you have also some internal symmetries among the particle. Let's say you will have different type of particle, and it turns out that nature is invariant when you can change those particles into each other's, right? So we are talking about internal symmetries. So electromagnetism is the first example of an internal symmetry, right? In the sense that you really change the phase of the wave function of those particles, right? So that's one example of those internal symmetries. But there are others that have been discovered, in 20th century by performing various experiments with those particles. We have really understood that there is extra symmetries, and those extra symmetries give rise to extra interaction, extra forces among those particles, right? And I will tell you exactly what are the fundamental interactions that exist among the particles of nature. Okay, good. So far, so good. So the next question is, how do we probe actually the structure of matter? You know that if you take a piece of wood, you can cut the piece of wood, you can cut further and further, and at the end of the day, you will end up with atoms, right? But atoms are not yet elementary particles in the sense that you can break the atoms, right? And you probably know that the atoms are made of a nucleus with some electrons that are spinning around the nucleus. Is it the end of the story? So the electrons indeed are elementary particles as far as we know today. But the nucleus themselves are not elementary particles. They are made of proton and neutron. And those proton and neutron are not elementary particles either, in the sense that you can break the proton and the neutron to find out that they are made of quarks. Right? They are made of quarks and other gauge boson that I will describe in a moment, which are called the gluons. So how did we end up with this understanding of the structure of matter, right? Because sometimes, I mean, you cannot always break matter into smaller and smaller pieces simply because, you don't have enough energy, or your knife that you want to use to cut matter is not sharp enough, right? Fortunately, I mean, you can really understand a lot of matter without destroying matter. And the simple example that I want to give you is really this experiment with boiled eggs, right? You want to understand whether you are dealing with eggs that has been boiled or whether it's a raw eggs, right? And to understand the difference, of course, you can break the eggs, but breaking the eggs, I mean, it's not always nice because sometimes later on you want to use the eggs to make a cake or whatever, right? So how do we do that? Well, I mean, the easiest way to understand whether the eggs is boiled or not, you try to really turn the eggs, and there you can see really the difference. I mean, the way the egg is spinning, is telling us if it's boiled, namely if the eggs is in one piece only, or whether it's raw, namely that it has an internal structure with different components which are moving independently from each other. So if you're doing this way, you can really understand what is the internal structure of the eggs. So of course, I mean, we can repeat this kind of a little experiment, trying really trying to understand the structure of matter by turning matter around, right? And one famous example of an experiment that worked like that is actually the Rutherford experiment, right? So Rutherford, had a foil of gold, like right here, and then he was sending a beam of alpha particle. Alpha particle is basically helium atoms where you have extracted the electrons. And what he noticed is that most of the time, actually, these alpha particles were going through the piece of gold without being deflected at all. In other cases, these alpha particles were getting a big deflection, and sometimes they were even getting back, right? And what does it learn from this experiment? Well, it really learned that atoms are mostly made of void. So mostly in matter, there is nothing, right? And this is due to the fact that the volume of the nucleus inside the atom is really small compared to the volume of the atoms, right? So most of the matter is actually made of void. Or say it in another way, matter is very concentrated, right? So all matter inside the atom is mostly inside the nucleus of the atoms, right? And then in addition to the nucleus, there are few electrons that are spinning around the nucleus, right? So basically, when the alpha particle were not deflected, it just means that the alpha particle were going through the void of the atoms. And then sometimes, this alpha particle hits the nucleus of the atoms, and then they are really deflected very highly, right? Because they feel really the nucleus. So that's a very beautiful, that tells us how the atom is made of, what the atom is really made of, right? It's made of a nucleus with some electron around. And then in the 1960s, there were further experiments going along this line. And one nice experiment is actually what is called electron-proton scattering. So, you have some protons. So again, the protons are just some piece of the nucleus of the atoms. And then you were sending some high energetic beam of electron over this proton. And you looked again at how the electron is deflected by its interaction with the nucleus, right? And from this experiment, right, what people concluded is actually that the proton is not an elementary particle, right? The proton is a composite bond state, which is made of 3 spin 1/2 quarks, right? So 3 elementary particles that are called the quarks, and the spin 1/2, it just means that they are fermions, right? It's just telling you how these quarks behave when you perform a Lorentz transformation. So when you do a rotation of space and time, these spin 1/2 particles behave in a particular way, and that's giving you really the property of these quarks. Furthermore, they have learned that those quarks also exist in 3 different colors, right? So you can call this color blue, red, or green, or whatever, but there are 3 types of colors, so 3 types of quarks, and those quarks are bound together inside the protons, basically. And furthermore, when you keep increasing the energy of the electron beam that you're sending on the proton, you are learning few extra properties, right, of this quark inside the protons. And what did you learn? You learned that, those quarks have very feeble interaction among each other when the energy of the electron is very high. So that's something that has been called asymptotic freedom, namely that you have strong interaction. So the strong interaction is the interaction among the quark inside the proton or the nucleons. And those interactions are very strong when you try to tear apart the quark from each other. So that's why the quarks are bounded inside the proton. But once they are inside the proton, when you want to probe the structure of this quark at very small energy, at very large energy, so it means at very small distances, it looks like actually the quarks behaves exactly like free particles, right? So the strong interaction becomes zero inside the proton and inside the quark. So that's a remarkable property of the strong interaction, which is totally different than electromagnetic interaction. Electromagnetic interaction, when you try to bring very close to each other the proton and the neutron, the electromagnetic interaction diverge, right? It becomes stronger and stronger. While inside the proton, the strong interaction is just the opposite. When you try to bring the proton closer and closer, the strong interaction becomes zero, basically. So that is called asymptotic freedom, and that's exactly a nice property that has been understood theoretically by David Gross, Frank Wilczek, and David Politzer, and they got the Nobel Prize for this understanding, really, of the structure of the proton and the neutron. Okay, so far so good. So we have understood more or less, that there are those elementary particles, the building blocks of matter. So particles is basically a very small object, very small because that's something that you cannot cut further. It really has no size in the sense, so we can call it small. And furthermore, what has been understood from all this experiment is that this particle obeys the laws of quantum mechanics and obeys the laws of special relativity, right? So, of course, I'm sure you have heard about quantum mechanics already, and there are mainly 2 properties of quantum mechanics, right? That an object, a quantum object, can follow different trajectory at the same time. Right? It can enter through the window or it can enter through the door at the same time, because a particle is actually not a localized quantity, but it's really like a wave, and a wave can clearly enter into different places at the same time. Right? In the same way, that the student, can follow the lecture staying in their bed in the morning and still listening to their professor thanks to Zoom, right? So Zoom, for instance, is also a kind of example of quantum mechanics behavior. Right? So that's the first property of quantum mechanics. The second property of quantum mechanics is what has been called quantum fuzziness or Heisenberg inequalities, right? It means that you can never measure with an infinite precision at the same time the speed and the position of the particles, or the speed, or if you want the momentum of the particle, right? The momentum is just the product of the mass times the speed, right? So really, that in a sense, the product of the uncertainty in the determination of the momentum times the uncertainty in the determination of the position of the particle has to be equal at least equal to the Planck constant h bar. So of course, this is a ridiculously small quantity compared to the units that we are used to in everyday life. So that's why you and I are not quantum particles, right? Because our quantity, are much larger than this than this Planck constant. So we don't feel these quantum mechanical properties. Nonetheless, the atoms, or the proton, the electron inside your body really behaves according to the laws of quantum mechanics. So so this product of the the uncertainty on the speed of the momentum times the uncertainty of the position is one Heisenberg uncertainty. The other one is a product of the determination of the energy times the determination of the lifetime of the particle. And the two are, again, cannot be sent simultaneously to zero because their product has to be at least equal to the Planck constant. So this means that you can never determine exactly the energy of the particle. You have some fluctuation of the energy. In classical physics, you can always determine the energy of the particle. You measure exactly the speed of the particle, and then you can associate the energy of this particle. But in quantum mechanics, you cannot do that, right? So there are always some fluctuation of energies. And then those fluctuations of energy are becoming very interesting, when you try to combine the laws of quantum mechanics with the laws of special relativity. So as I told you already, special relativity is basically, the fact that you can transform space and time by moving at a given speed, So you don't see space and time flowing in the same way when yourself, you are moving at a speed which is close to the speed of light. So again, in everyday life, when you go into a train or you go into a plane, you never experience those special relativity effects because your speed is always very small compared to the speed of light. Nonetheless, when the particle is approaching the speed of light, then indeed, at some point, you will mix space and time. So you will have a rotation, that transforms space into time. Okay, and the other, very important property of special relativity is this equivalence between mass and energy. The famous equation of Einstein that E is equal to mc squared, right? The mass times the speed of light to the square. Right? But I told you, right, that in quantum mechanics, you have fluctuation of energy. But since energy is equal to mass, it means that you have also fluctuation of mass, right? So this means that in the quantum world, you have not a unique mass. So it means that you can create mass. So it means that you can create matter, right? So you have fluctuation of matter in a quantum world. Right? So that's very fundamental, and we will see in a moment really the consequences of this combination of quantum mechanics and special relativity. One more property that I wanted to emphasize is that when you try to combine quantum mechanics and special relativity, automatically, you will discover that you need antimatter, right? So if you have an electron, if you try to describe electron in a way which is consistent with quantum mechanics and special relativity, automatically you need to also have a positron, which is an anti-electron, right? So Dirac in 1928, I think, really discovered or predicted the existence of antimatter by really trying to get a consistent description of quantum mechanics and special relativity. And indeed, a few years later, people indeed discover for the first time the positron, so the anti-electron, as a cosmic rays particle which is coming really from the space, right? So the antimatter was able to really reach the Earth. And of course, as soon as antimatter encounter matter, it will disappear and form pure energies, right? Nonetheless, people really observe for the first time these positrons that were predicted few years before by Dirac, just by trying to get a theoretically consistent description of quantum mechanics and special relativity. Right. So let me come back now really to the special property of particle physics, which is the combination of quantum mechanics and special relativity, right? And this gives you something which is totally different, for instance, than chemistry, right? So if you take various processes in chemistry, you will understand that it's simply a reorganization of the constituent of matter, right? So for instance, take some gas that you burn. So the way it is done, when you are burning some methane, for instance, the methane is 1 atom of carbon and then 4 atoms of hydrogen here. And what does it mean to burn the methane? It simply means that you combine with some oxygen atom, right? So you have some oxygen atom like that, and then you take this atom of carbon and then you associate it to 2 atoms of oxygen to form carbon dioxide, right? CO2. And then you see that you have extra hydrogen atom that you can combine also with extra oxygen atom to form water, right? So you really start with CH4 plus 2 O2, and then you get carbon dioxide, CO2, plus 2 molecule of H2O, right? So 2 molecules of water. So what you're doing in chemistry, right, is simply reorganizing matter. You break some atoms, you take some atom of some molecules and you combine them with atom of another molecule to form different molecules. And it's very nice. I mean, there is very rich structure associated to it. You can gain some energies, etc. I mean, it's fantastic. I mean, chemistry is certainly a fantastic discipline, fantastic science. Nonetheless, in particle physics, there is some new phenomena that occurs really because you can transform energy into matter, right? So typical example, where this can happen is really when you try to collide an electron with a positron, right? I told you that the positron is the antimatter of the electron. So that's exactly the kind of experiment that is done in big colliders. You take an electron, a positron, you give them a lot of energy, and you make sure that they collide, right? And when they collide, what is happening is that you are transforming the energy of those particles into matter. So for instance, you will produce some photon, you will produce some muons. So the muons are objects that have particles that are very similar to electron, except that their mass is 200 times heavier than the mass of the electron. And you can also form some quarks, So the quarks are really the constituent of the proton and the neutron. You can even produce what is called some gauge boson W plus or W minus, or some gauge boson Z0, some gluons, right? So all those particles are really obtained from the energy of the electron and the positron. And clearly, it's totally different than chemistry, right? Because the mass of the W is 200,000 times heavier than the mass of the electron. So there is no way that the W can fit into the electron, right? So it's not that you are trying to cut, the electron and rearrange the fundamental constituent of the electron into other fundamental particles. No, it doesn't work, right? There is not enough energy inside the electron to produce the W. It's simply the kinetic energy of the electron, the kinetic energy of the positron, which is transformed into matter, right? So it's really this equivalence between energy and matter that you are using here, and with the property of quantum mechanics to really produce new particles. I hope it's clear that you are learning things. Okay, good. So it's a fantastic experiment. It's like trying to collide strawberries and then get some bananas, some pears, or some nuts, etc. Right? So that's really what is going on into a particle physics experiment. Of course, it doesn't work with strawberries because the strawberries are not quantum particles. Right? The strawberries don't obey the laws of quantum mechanics, but the electron, the positron, the quarks are quantum objects. So they really obey the laws of quantum mechanics, and that's why it works beautifully inside the particle accelerators. Right? So those experiments have been done over and over the years, and the remarkable thing is that this way you were able to produce all the particles that exist in nature. So those particles don't necessarily exist, in nature directly, but you can produce those particles. And what is really remarkable is that you produce a finite number of different types of particles. So what are those particles? So if you want, I'm talking about the genetic code of matter, right? Really the building blocks. At the moment, we have never discovered any other type of particle. By colliding any sort of particle with the more and more energy, we have only obtained the particle that I'm going to talk about, and a few more that I will be talking about, in particular the Higgs boson, which is the latest particle that has been discovered in 2012, so about 10 years ago, at this big accelerator at CERN, the LHC, the Large Hadron Colliders. So what are those elementary particles that we have obtained, that we have observed so far? Well, so there are basically two big class of particles. There are the leptons and the quarks, right? So the leptons are basically the electron and another particle which is called the neutrino. So the neutrino is a particle that doesn't carry any electric charge, right? So I'm sure that you are familiar with the notion of electric charge of the electron, but the neutrino is a particle that doesn't carry any electric charge, right? But we will see that it still interacts with the electron in a very peculiar way, which is called the weak interactions. So there are the electrons, and the electron, I mean, you are very familiar with. There are electrons all around the world, right? I mean, inside the atoms, in the batteries, whatever, everything is made of electron. You know, when you're turning on light, what is happening? Electricity is basically electrons which are moving around. Right? But what people have discovered is that in addition to the electrons, there are other sort of leptons that exist that have basically the same property of the electron, you know, the same electric charge, the same kind of interaction, except that they are much heavier than the electrons. So they are the muons and they are the taus, right? So the muon is 200 times heavier than the electron, and the tau is 20 times heavier than the muons. And in addition to this muon and tau, there is also a muon neutrino and a tau neutrino, right? And one big property of those leptons is that they can exist as free particles. So you can always find, you know, in space, you can see, you know, an electron which is traveling, right? A free electron which is propagating in space, right? At least you can also see a muon traveling in space for some time. I mean, the muon is not a stable particle. At some point, it will decay because the muon is a heavy particle. So it will decay into an electron and some neutrinos. But the same is also true for the tau. You know, the tau is a particle that can exist as a free particle in nature, and it will propagate alone without being surrounded by other particles. Good. So these are the leptons. And in addition, there are the quarks. So the quark, I mean, we have already talked about the quark. These are the fundamental constituent of the proton and the neutron. If you are really trying to cut in smaller and smaller pieces the proton and the neutron, you will find out that those particles are made of quarks. So the proton, for instance, is made of 2 up quark and 1 down quark. Fine. But in the same way that, you know, you have electron and you have heavier cousin of the electron, the muon and the tau, here is also the same. You have heavier cousins of the up and down quark. You have the charm and the strange, and you have the top quark and the bottom quark. And those particles are about 1,000 times heavier than the up and the down, or 100 times heavier than the charm and the strange, right? So again, those particles, you know, don't really exist in nature, but you can produce them by colliding heavy particles. So contrary to the lepton, the quark never exist as free particles. They are always in bound state, like the proton and the neutron. You know, you can never see a free up quark in nature. The up quark will always pair with another up quark or with a down quark to form a proton, or will pair with a 2 additional down quark to form a neutron, or will pair with an antiparticle associated to the up quark, which is called anti-up quark, right? Anti-quark, to form what is called a meson. The pion is a composite bond state made of up and anti-up quark. So you can never see a up quark propagating freely in space. It will always be in the form of in the form of bond states. Good. So now we know exactly what are the elementary particles in nature. You know, we know the genetic code of matter, the building blocks of matter, and the next step was to understand exactly how those different particles interact with each other. What are the forces that those particles experience with each other? And there, you know, we can quickly understand simply by looking at the sun, right? We can quickly understand that there should exist different form of energies, different form of different source of interaction among those particles. So let's do a little bit of math, right? If you take a piece of ice, in the summer, you leave it in your nice drink, right? For instance, or you leave it in the table under the sun, and this piece of ice, it will melt in about 30 or 40 minutes, right? But then you ask yourself, yes, okay, why this piece of ice is melting? Simply because you receive a lot of energy from the sun, right? But I mean, the sun is radiating in an isotropic way, right? There is no preferred direction. So that means that the energy that I receive on Earth, I mean, I will receive exactly the same energy if I were located at the same distance of the sun in the opposite direction, right? So it means that if I take the same piece of ice, I move it around, I put it on the other side of the sun, it will also melt in 40 minutes. Which means that, you can really imagine that you are surrounding the sun with a thick cap of ice, a thick cap with a thickness of 1 centimeter, right? So it's a big sphere, a big sphere of ice surrounding the sun. And I claim, by isotropy, that this big sphere of ice should also melt in 40 minutes, right? Because really nature is isotropic. There is no preferred direction. The sun is radiating in any possible direction in exactly the same way, right? So now you ask yourself, wait a minute, what is the amount of energy that I need really to melt this big amount of ice now, right? Because it's really a huge amount of ice that is surrounding the sun, right? It's a sphere of, a radius of 150 millions of kilometers and a thickness of 1 centimeter. So you can compute the volume of ice. You can open Wikipedia, you look at the latent heat of ice, and you compute the amount of energy that you need to burn every 40 minutes, for instance, to melt this amount of ice. And simple math will tell you that you need every 40 minutes, every 30 or 40 minutes, you will need to burn 10 to the 18 liter of oil, right? And then you think a little bit, right? But what is the volume of the sun, right? The volume of the sun is of the order of 10 to the 30 liters, right? This means that since you need to burn, every 30 minutes, you need to burn 10 to the 18 liter, it means that the sun could live only, few tens of millions of years, right? Otherwise, after that, all the energy of the sun will have disappeared, right? So this simple computation actually led to one of the biggest controversy in science, right? Darwin, the guy that wrote this famous book on the origin of species by means of natural selection, who understood that the age of the Earth should be at least 300 millions of years to give time, for some hills to erode and then for life to develop, etc. Right? So I need the Earth to be at least 300 millions of years. And then Lord Kelvin, or Mr. Thomson, I mean, these are the same person, which was a very famous physicist at that time. He didn't like at all this notion of natural selection. He said, no, your theory is all wrong. And actually, I can prove you that it's all wrong because I can really compute the gravitational energy of the sun. And if I assume that all this energy is converted into heat, I can conclude that the sun cannot be older than 20 million of years. And actually even say that if all the energy of the sun is due to chemical energy, so the kind of burning of oil that we are talking about, the sun could live at most 1 million of years. So your theory of evolution, that needs 300 millions of years is all wrong. It cannot be. It cannot be consistent with the laws of physics, right? And actually, it turns out that Kelvin was so influential at that time, that in the second edition of his book, Darwin actually erased completely this estimate of the age of the universe, the age of the Earth, and the age of the sun. Of course, nowadays we know that Kelvin was wrong and Darwin was right, right? Because the sun is more than 5 billion of years, right? So clearly you needed extra source of energy, which is not gravitational energy and is not chemical energy. So you need a new source of energy, a new fundamental interaction among the particles that produce much more energy than the interaction associated to chemistry. And the interaction associated to chemistry, by the way, are nothing else than electromagnetic interactions. Right? So this little experiment, basically this little fact that ice melt in 30 minutes, really tells us that there are at least extra source of energy, extra fundamental interaction. So in addition to electromagnetic interaction, we have basically discovered the weak interaction and also the strong interaction that are really responsible for the quarks to be sitting together inside the proton and the neutron. In addition, it's true that there is also gravity, but actually gravity is a fundamental interaction which is totally negligible among the fundamental particle that I was talking about. Of course, gravity is very important, when you are talking about interaction among huge amount of matter. Why I am sitting on the chair, why you are standing on Earth is because of gravity. But I'm sorry to tell you that you are not a fundamental particle. You are not an elementary particle, right? So at the level of the elementary particle, because the mass are very small, actually you can neglect gravity. So the gravitational interaction is much, much smaller than the electromagnetic interaction, much, much smaller than the weak interaction and the strong interaction. Okay, so we have understood that there should exist those fundamental interactions. But now the question is, how do I describe those interactions? I told you at the beginning that one of the biggest discoveries of the 20th century was to really understand that all these fundamental interactions are associated to symmetries, right? So what are the symmetries associated to electromagnetic interaction, associated to weak interaction, and associated to strong interaction? So for that, to understand this, again, this equivalence between dynamics, so between force and symmetries, I need to get back to basics, right? I mean, think about the chicken and egg problem, right? So you know that the egg is produced by the chicken, right? And it turns out that the chicken has a particular way to produce the egg in such a way that the egg turns out to be basically invariant under some rotation, right? There is, yes, approximate exact rotational symmetry for the eggs, right? So what I'm trying to tell you is that the dynamics, so the forces, so all the processes that are taking place inside the chicken is such a way that the eggs obtain this particular shape, right? This particular symmetry. So the same was also true at some point with the laws of physics that govern the propagation of light. This famous Maxwell equation. I'm sure that you have seen in school all this equation that really tells you how light is propagating. So it's telling you how the electric and magnetic field behaves, or the waves associated to electric and magnetic fields propagate into space. Right? And it turns out that if you play with this Maxwell equation, you will quickly realize that the speed of light in the vacuum is actually a constant. No matter how you are moving with respect to the with respect to the photon, the photon is just light, right? So no matter how you are moving with respect to light, you will always see the light which is propagating at the same speed, right? Which is something which is counterintuitive, right? Because if you're moving yourself inside the train and the train is moving, compared to the train station, clearly you will add or you will subtract your speed to obtain your own speed relative to the train station. But for light, it doesn't work like that. If you are moving together with light, you will still see propagating. You will still see the light propagating as exactly the same speed as if you were not moving. Right? So what I'm trying to tell you is that the dynamics of the Maxwell equation tells you that light is actually always propagating at the same speed. Right? And for quite some time, people were really puzzled. I mean, how come I I can really show that Maxwell equation implied that the speed of light is constant. You know, they were doing math, I mean, trying really to understand this property of the fact that speed of light is constant. Until one guy who came, Einstein, I mean Albert Einstein, say, wait a minute, actually, you have to think about the opposite way, right? In the sense that I want the speed of light to be constant. It's a fundamental property of nature, fundamental property of space and time, that light is always propagating at the same speed. And then from that, I can directly obtain actually the Maxwell equation. So the only requirement that the speed of light is constant, you know, determine uniquely the Maxwell equations. In the same way, you know, if you want to require that the eggs has some particular symmetry properties, it will tell you exactly how the egg is produced inside the chicken. Right? So the shape of the eggs determine its production modes. You have to think in the opposite way. It's really the symmetry that dictates the dynamics. The symmetry properties, the fact that the speed of light is constant, determine the interaction, determines electromagnetic interaction, determines the way electric field and magnetic field propagate over space and time. Right? So you have to think totally in the opposite way. Right? It's really the symmetry that dictates the dynamics. It's because you have things that are some symmetry property that dictates those interaction among the particles. So that's exactly this symmetry principle that we call sometimes gauge principle that control electromagnetic interaction. So again, let me repeat it again. The fact that you want that the phase of the electron, you know, the phase of the wave function of the electron is somehow not physical, that you can remove, you can perform a rotation of the phase of the electron that dictates electromagnetic interactions. So in a sense, you know, the photon, which is the particle associated to the electromagnetic interaction, is a memory of how the electron phase is changing from one point to another in space-time. Right? So I told you that you can change the phase of the electron, and you can change the phase of the electron differently in different points of space-time. But of course, you have to keep track of the memory. You have to keep memory of how you are changing the phase, and that's exactly the electron. The electron is knowing exactly how the phase of the electron is changing in this space and this point of space-time. So in a sense, electromagnetic interaction is simply the exchange of an electron. Right? So you are changing the phase of the electron. By changing the phase of the electron, you are actually exchanging a photon. Right? So those two guys, for instance, can interact with each other by sending themselves a ball. So that's the way also particles interact with themselves. They are exchanging some gauge boson, so photon in the case of electromagnetic interactions. And the same is also true for all the other fundamental interactions that have been discovered. So for instance, the weak interaction, which is simply a nuclear interaction, so nuclear decays, you know, the fact that some nuclei decays into smaller nuclei. So what is happening is really that a neutron is decaying into a proton plus an electron that we call a beta particle plus an anti-neutrino electron. So it seems that this interaction is actually an interaction among all these four particles, but actually what is happening is really that the neutron, you know, is exchanging a W gauge boson to become a proton, and then this W, you know, propagate, and ultimately it gives you an electron and an antineutrino. So the weak interaction, you know, the interaction that are really responsible for all nuclear interaction, you know, the decays of big nuclei, etc., is simply the exchange of a W gauge boson. Skip that. Sorry, here it's important. So what is really the symmetry? So I told you that, okay, you are changing the gauge boson, but what is the symmetry associated to this weak interaction? Well, this symmetry is simply the exchange of an electron with a neutrino, or if you want, an up quark with a down quark. Right? So it seems very strange that this is a symmetry of nature, because indeed those particles are totally different from each other. The electron has an electric charge, the neutrino has no electric charge. Nonetheless, what we have been discovered is that nature will remain the same. If you replace an electron with a neutrino, if you replace an up quark with a down quark. So this is a symmetry. This is an internal symmetry. And this internal symmetry is what is responsible for the weak interaction. So what about the strong interaction? Well, I told you at the beginning that the quark exists in 3 different colors. In the same way that you can change the phase of the wave function of the electron, here you can change the color of the quarks. And nature should remain identical. Nature shouldn't care about the color of the quarks. And that's a symmetry. And this symmetry is what is called a strong interaction. For gravity, the particle, the symmetry that is associated is what is called a diffeomorphism. So you can change, generalization of rotation, if you want. Generalization of rotation in different points of space and time. And of course, the particle that is associated to gravitational interaction is what is called the graviton. Okay, so we are learning about these different properties, these different fundamental interaction. And there is one important property of the weak interaction, which is called chirality, right? And chirality is the following, that chirality, the weak interaction sees a big difference between left and right. Electromagnetism of the strong interaction don't see the difference between left and right, namely that if you have a process which is mediated by electromagnetism, you cannot distinguish this process from the same process that you will see in a mirror, right? So mirror, you know that a mirror will exchange left and right, But for the weak interaction, a process which is mediated by weak interaction is totally different than the same process seen in the mirror. So that was a big experiment that was done by Mrs. Wu in 1956. She looked at how big cobalt atoms actually die. They die simply because they decay, right? They decay into smaller nuclei. And she noticed that this death of this cobalt atom actually were not identical when you look at them in the mirror. So there is a violation of the symmetry between left and right. So again, that's really peculiar to the weak interaction, something that never happened for the strong interaction, nor for the electromagnetic interaction. So what it's telling you is that the electron, which has 2 chirality, because the electron is spin 1/2. So spin 1/2 means that you have two spin states. So you have the left-handed electron and the right-handed electron, and those 2 particles behave totally differently under the weak interaction. So it's only an accident of the history of physics that we call those 2 particles electron, right? Because indeed they are the same particle, they have the same property under electromagnetic interaction, but under the weak interaction, they are totally different particles. The left-handed electron is totally different than the right-handed electron. So for instance, it's only the left-handed electron that couple to the W. The right-handed electron never couple to the W gauge boson. Right? So the right-handed electron doesn't feel at all the weak interaction. Right? So that's what was learned really from this experiment by Mrs. Wu. Well, by the way, talking about chirality, right? You know that in molecular biology, chirality is an emergent property, which is essential for life to emerge, right? If you want life to exist on Earth, you really need some sort of chirality in molecular biology. And as far as I know, nobody really knows for sure whether the chirality in biology is also related to chirality of the weak interactions. Right? So this is still an open question, whether really chirality in biology is due to the fact that the left-handed electron behaves differently than the right-handed electron. And we don't know either whether, just give me a second. we don't know either whether chirality of the weak interaction is also an emergent phenomenon, namely that if you go at very high energy, whether chirality or parity, so this symmetry between left and right, is restored, and it's only at low energy that you see this chirality breaking, parity breaking. This is still an open question too. So why this chirality property gives trouble to people, right? It gives trouble to people because it's not consistent with a special relativity when the electron has a mass. Simply because of the following argument, right? I mean, I told you the electron exists in two different polarization states, so different spin. So what it means that the electron can spin in one direction or the opposite direction according to this propagation, to this momentum propagation of the electron. Right? So an electron propagates in this way, it can spin in this way, clockwise, or it can spin counterclockwise. Right? Fine. But now, let's what is happening when you are moving faster than the electron, right? So if you are moving faster than the electron, then you will see, yourself, you will see the electron going in the opposite directions, right? But on the other hand, I mean, the spin of the electron won't change, right? So whether it's spinning clockwise or anti-clockwise, depends on the way you are looking at the electrons. So what you call a left-handed electron, a right-handed electron, depends on your relative motion compared to the electron. But then it's very problematic, right? Because I told you that left-handed electron behaves totally differently than the right-handed electron under the weak interaction. But then being left-handed or right-handed depend on the way you are looking at the electron. So there is some inconsistency there. So the only option is, of course, that the electron is always propagating at the speed of light. In this case, you can never go faster than the electron, and then you can never see the electron going in the opposite direction. So indeed, if you want to have a left-handed electron that behaves differently than the right-handed electron, the only option is that the electron is massless, namely that it's propagating at the speed of light. It's only a massless particle that can propagate at the speed of light. Every particle that has a mass, you can always go faster than this particle. So this means that the chirality property of the weak interaction requires that the mass of the electron is exactly equal to 0. So mathematically, we say that the chirality operator doesn't commute with the Hamiltonian of the weak interaction. But of course, we know that the mass of the electron is non-zero, right? So we have two experimental facts, right? The fact that the weak interaction are chiral series, so they break parity, they see the difference between left and right, and we also know that the mass of the electron is non-zero. So there is something which is incompatible with the laws of special relativity. It was really a big puzzle, and people really, for many, many years, didn't understand how it could work. I mean, there are some big physicists like Pauli, say that your theory is totally absurd. You cannot describe the weak interaction in terms of this chiral series simply because it's incompatible with the fact that the electron has a mass, right? Of course, I mean, Pauli was, a genius, right? I mean, he got the Nobel Prize for discovering the neutrinos, etc. But, he couldn't understand really this chirality nature of the weak interactions. And the solution to this problem is actually associated to what is called the Higgs boson, namely the fact that the short distance interaction can be different than the long distance interaction, that the symmetry of the vacuum doesn't have to be the same thing as the symmetry of your interactions, the symmetry of your Lagrangian that describe those interactions. So the vacuum, is not a space which is totally empty. The space is actually filled with what we call the broad angular Higgs substance that breaks the symmetry, right? So, I mean, just imagine, when you know that, I mean, the interaction on Earth are invariant when you perform a rotation. Nonetheless, if I have this pen, if I let the pen go, it will choose one particular direction, right? So we will break spontaneously the invariance by rotation. So the vacuum, the way the pen is falling, the vacuum is breaking the rotation symmetry. And that's exactly what is happening in nature. So the vacuum breaks part of the symmetry that I was describing before. So I was insisting of this U1 symmetry, which is a rotation of the phase of the wave function of the electron. This SU2 symmetry, which is the exchange of the electron with a neutrino. So mathematically, this is described by a group theory, which is called SU2. So those symmetry, SU2 cross U1, is broken down to U1 electromagnetism in the vacuum. So the only symmetry that survives in the vacuum is the symmetry of electromagnetic interaction. And how this symmetry breaking occurs via this broad angular Higgs mechanism that was invented by those people in 1964 and was finally discovered for sure in reality in nature at CERN at the Large Hadron Collider in 2012. And it's not a surprise that, the masses of the different particles have to do with the existence of this Higgs boson, right? That's something that has been now well established by this experimental data at LHE, by these two experiments, which is called ATLAS and CMS. So they have measured the masses of these different particles, elementary particles, the muon, the tau, the bottom quark, the top quark, the W gauge boson, the Z gauge boson. And at the same time, they have measured the interaction of those particles with the Higgs particle, with the Higgs boson. And they discover, as it was predicted by the broad angular Higgs mechanism, that those masses and those couplings are related to each other, namely that the coupling are proportional to the mass of the particle. Right? So that was a big prediction of the theory, and this prediction has been confirmed experimentally. So how the Higgs boson was actually discovered? So the Higgs boson indeed coupled to particles proportionally to their mass. But in nature, the particles that you have at your disposal are mostly very light particles. You have light quarks, the up and down quark inside the proton, or you have electron that exist as free particles in nature. But those particles are very weakly coupled to the Higgs boson. So you cannot produce a Higgs boson by interacting with up quark, the down quark, or the electron. Right? So the way you want to produce the Higgs boson, you want to really produce the top quark. Unfortunately, the top quark can be produced by the gluons that are inside the proton. Right? By quantum mechanics, you have this fluctuation of energy. Those fluctuation of energy produce the top quark, and the top quark, directly has a large coupling to the Higgs boson, and then produce the Higgs boson. But the Higgs boson is actually a very unstable particle. He has a lifetime of 10 to minus 22 seconds. So you spend a lot of time trying to produce the Higgs boson, and 10 to minus 22 seconds after, he has already decayed into other particles. So in which particle he decays? Well, he will decay mostly into bottom quark, but it's very delicate to see the bottom quark. So it's much easier, much cleaner to actually see the decay of the Higgs boson into 2 photons or into 4 electrons, for instance. Because then, you have a very clear way to see the photon, to measure their properties and reconstruct the mass of the Higgs boson that you can see here in this experiment, right? So here, in this little bump, so these are all the photons that are produced, by interaction of the quarks. And sometimes, when the proton has the right energy, they produce actually a Higgs boson. And this little bump here in the spectrum is the production of the Higgs boson, right? So that's really what occurs at the LHE. They started with few collisions of proton, and they accumulated more and more collision. And at some point, they see really this little bump in the distribution of the energy, and this little bump is really the production of the Higgs boson. So that's exactly the way the Higgs boson was discovered, right? By what is called the fusion of gluon and the decays into 2 photons or in the decays of 4 electrons. Of course, that was the beginning. That was 10 years ago. And since then, I mean, much more collision, much more protons have been collided. And now this is, what we really observe. And here we can really reconstruct the Higgs boson very cleanly and separated the Higgs boson from the Z boson, which is, the gauge boson associated to this weak interaction. So there is no doubt at all that the Higgs boson exists. It's an elementary particle here, and it has been produced in your colliders. Okay, I mean, since then, I mean, many Higgs boson has been produced. I mean, something like 8 million of Higgs boson has been produced at the LHE, and we have been observed the various production mode of the Higgs boson and the various decay mode into 2 photon, into 2 Z boson, into 2 Ws, into blah, blah, blah. There's many decay modes, and all these things has been observed, and this is consistent with the experimental data. So really, this discovery of the Higgs boson has been a very important milestone for high energy physics, and many of us are still excited about it, and others should be excited about it also for various reasons. First of all, because the knowledge of the values of the coupling of the Higgs boson is really essential to understand the deep structure of matter and the universe, right? So, for instance, I told you, right, that the coupling of the Higgs boson to the W and the Z gauge boson is responsible for those masses, right? And it turns out that the value of those masses is directly connected to the lifetime of stars. Why the sun is burning since 5 billion of years is simply because the mass of the W and the mass of the Z is about 100 times heavier than the mass of the proton. Right? So this has to do only because the Higgs boson interacts with the W and the Z in a particular way. Right? It will be different, the coupling will be different, the lifetime of stars will be totally different. And then, you may also know, I mean, since you are expert in biology, you may also know that the typical lifetime of stars is also related to the typical lifetime for life to evolve, right? So, why life takes the form that we know today, maybe because, the Higgs boson has this particular coupling to the W and the Z. So this is now well established. I mean, those coupling of the Higgs boson to the W and the Z has been well measured. And there is no doubt everything works fine, right? But there are also things that we don't know at all, right? For instance, I mean, in this plot that you showed before, and this plot that I show you here, I've stopped at the mass of the muon, but I never show you the point for the mass of the electron, simply because we are not able to measure the coupling of the Higgs boson to the electron, because this coupling is too small, because the mass of the electron is too small. So you expect a point here, which you have no sensitivity to. And that's very sad, right? It's very sad that we don't know yet if the mass of the electron is due to the coupling of the electron with the Higgs boson. Why is it sad? Because at the end of the day, the mass of the electron sets the size of the atom, right? Remember this Bohr radius, that give you the size of the atom is determined by the mass of the electron. And the mass of the electron is supposed to be determined by the value of the coupling of the Higgs boson to the electron. Same way, we don't know yet either the coupling of the Higgs to the up quark and the down quark, right? The fundamental constituent inside the proton and the neutron, right? So I told you the difference between proton and neutron is that proton is 2 up quark and 1 down quark, and neutron is 1 up quark and 2 down quark, right? But of course, I mean, QCD, the strong interaction, doesn't see a difference between up quark and down quark. I mean, this is exactly like the weak interaction. In weak interaction, you can exchange up and down. So according to QCD, which is responsible for the big part of the mass of the proton and neutron, don't see the difference between up and down. So QCD predict that the mass of the proton should be equal to the mass of the neutron. Of course, the up quark has an electric charge 2/3, the down quark has an electric charge 1/3. So electromagnetism should make a little difference in the mass of the proton and neutron. But it turns out that electromagnetism should make actually the proton slightly heavier than the mass of the neutron, because up is electric charge 2/3, right? So 2 up quark of electric charge 2/3 means that you have more electromagnetic energy. So the mass of the proton is heavier than the mass of the neutron, according to electromagnetism. But the mass of the up and down, which is generated by the interaction of those quarks with Higgs boson, are slightly different. And it turns out that the coupling of the Higgs boson is probably smaller than the coupling of the Higgs boson to up quark is probably smaller than the coupling of the Higgs boson to the down quark. That makes the proton actually lighter than the neutron, right? And that's good, right? Because in this case, the neutron can decay into proton, but the proton cannot decay into neutron. So it means that nuclei will be stable, right? If the proton were heavier than the neutron, the nuclei won't be stable. So you couldn't form atoms, right? Because you couldn't form nucleus. But because of this particular value of the coupling of the Higgs quark to the up and the down, then nuclei are stable and nature can exist, right? But that's theoretical understanding. I mean, we still need to measure, to go ahead and measure with precision the value of those couplings, right? There are other properties. I mean, I told you indeed that you have symmetry breaking. So SU2 cross U1 is broken to U1 electromagnetism. And that's a phenomenon which is supposed to take place something like 10 to minus 10 seconds after the Big Bang. And why this symmetry breaking occurs is probably due to the fact that the Higgs boson interacts with itself. Right? So it generates its own mass. So the Higgs boson generates its own mass. But again, this is something that has never been measured. So far, people have never measured the way the Higgs boson interacts with itself. We need to perform more experiments in colliders to really have access to these couplings. There are also this question of matter and antimatter. You know that in the universe, we have matter, but antimatter disappeared. While during the Big Bang, they should have formed in an equal amount, right? Because nature, I mean, the laws of nature should be invariant under the exchange of matter into antimatter. So why matter dominate over antimatter? This is still a puzzle that nobody really understands. And this might have to do with the way the Higgs boson coupled to the various particles. It will have a breaking of what we call the charge and parity symmetry, which is responsible really for this imbalance between matter and antimatter. So you see here that we have plenty of questions that need an experimental answer. We need to go ahead and measure things to make sure that what theorists like me have been thinking about is the correct description of nature. And for that, clearly we need experimental data. So we need a new collider after the Large Hadron Collider to really have access and to answer these type of questions. So we'll go a little bit fast because I think time is running short. There is still several questions that we don't understand. For instance, we don't understand this kind of picture. When you go into electrostatic field, your air will be lifted. It means that electromagnetic interaction, will be much stronger than gravitational interactions, right? And that's really a puzzle, right? We really don't understand why gravitational interaction are so much weaker compared to electromagnetic interaction, compared to the weak interaction. This is a puzzle, right? In quantum mechanics, you don't really expect this phenomena to occur. It will be actually the opposite. You expect that all the interaction should be of the same order. Or if you want, we expect that the masses of all the particles should be of the order of what we call the Planck mass, so the typical scale of quantum gravitational interaction. Why this is not the case in nature, we don't understand. I mean, we have various hypotheses. Maybe there exist a new particles in nature, which we call superparticle. Maybe there are extra dimensions in space and time that could explain why gravity is so weak compared to the other forces. So these are hypotheses, and we don't know the answer to these questions. Right? So we need to go ahead, make some experiment, and get the answer. I think I don't have much time, so we'll go quickly through the conclusion. I mean, it's very nice historical discussion about discovery of America, but I don't have time. And let's go to the last point. I mean, data always bring new understanding. We need facts and data because physics is a natural science. So clearly we have profound questions. I gave you various interesting questions that, I wish I get the answer to this question. And really, I want to create experimental opportunities to answer these questions. So high energy physics provide tools to other fields. I mean, medicine, climate, energy. They use the fundamental particles that have been discovered in high energy physics. So certainly high energy physics remain a very good investment for the future of mankind. So I will close the lecture here, and maybe we can take a few questions. So thanks a lot. Stop sharing, bring back online. Okay, sorry.
It was an amazing presentation. Really, you explain everything in detail. Even people who don't know anything about physics can understand easily. I understand also.
Okay, perfect.
And also, I think we can go through the question parts. Yeah, I will start with the first question here. Yeah. Why can't quarks be found while leptons can be found on their own?
Well, I mean, you cannot find quarks because quarks are sensitive to the strong interaction. And, I told you that the strong interaction become very strong when you try to tear the quark apart from each other. But leptons, are not sensitive to the strong interaction, so they can be separated from each other. So really, you can find an electron alone in space and time, right? That cannot happen with a quark because of the strong interactions.
Okay, thank you. Why did the universe choose matter over antimatter in the beginning? Actually, you answered that, but
yes, I mean, I told you we don't really have the answer to this question. This is a fundamental question. I mean, indeed, Big Bang should produce an equal amount of matter and antimatter, and for some reason, you had a little bit more matter than antimatter. There are various ideas along this line. I mean, we know exactly what you need, what are the properties of the interaction that you need to produce this imbalance between matter and antimatter. But we don't know how nature works. I mean, in a sense, whether the theoretical ideas that have been formulated by people like me are correct or not. So we need to find evidence of this. I mean, in particular, one important property is this violation of the CP symmetry, charge and parity symmetry. So charge and parity symmetry is broken by the interaction that I've been describing, by the standard model interaction. But it turns out that this breaking of CP in the standard model is not enough to produce this imbalance that we observe between matter and antimatter. So we need new source of CP violation. People are looking for it, very clearly.
Yeah. Actually, you answered so many questions in your presentation already, so we don't need to ask. Okay, next question. What would happen if the value of the Higgs field was 0?
I mean, one dramatic consequences will be that all the masses of all the elementary particles will go to 0, right? Another problem will be that the W and Z boson mass will go to 0. So this means that the weak interaction will be a very long range force, exactly like electromagnetism. So it means that basically the sun, the sun and all the stars will disappear immediately because they will burn all their gases immediately.
Yeah.
So that cannot happen either.
Yeah. Is entropy valid in the quantum field too?
Yeah, that's a delicate question. I mean, entropy is really due to the fact that you have many degrees of freedom at the same time, that you have also entanglement and all these things. So there are various studies, in particular these days, in quantum entanglement, and to understand exactly this kind of property, how entropy is created and these things. And there are some ideas. In particular, also entropy can be created by gravitational interaction. I mean, this is what we call this Hawking laws, or Hawking laws for black hole evaporation. So black holes actually are not stable objects. They will radiate particle, And this is due to the fact that a black hole has an entropy. So you can associate a temperature to a black hole, you can associate an entropy. And one big question is, of course, where the entropy of the black hole is coming from, right? So you need entropy because usually, you have various, you have different microscopic configuration of the various arrangement of the fundamental degrees of freedom that gives the same macroscopic description. And the big question is, of course, how do you describe, at the microscopic level, how do you describe the black holes? And this may be due to the fact that a black hole is actually formed of strings. I didn't have time to tell you about string theory, but string theory is probably a correct description of quantum gravity, of gravity at the quantum level. And there you could, for some black holes, you can compute the entropy and recover the Hawking law of radiations.
Okay. Why don't electrons agree to be in the same quantum arrangement?
I don't really understand this question. Let me think. Why don't electrons agree to be in the same quantum? So I don't know. Maybe you refer to the fact that you have two different electrons. I told you electron right and electron left.
I think yes.
This is due to the fact that electron is really a spin 1/2 particle, so it's a fermion. The difference between fermion and boson is that fermion, you cannot put two fermions at the same point of space and time. That's that Fermi statistic, Fermi-Dirac statistics. You cannot put two electrons which have exactly the same property at the same point of space and time. You can do that with boson, but you cannot do that with electron. In the sense, electrons are repelling from each other, so it's really like object. When you have a macroscopic object, you cannot, force them to be at the same time. So this is the property that really electron is a spin 1/2 particle and not spin 0 particle. So I guess that's really the answer to this question.
Okay. Next question. In the future, do we adapt these elementary particle concepts from physics to chemistry in order to increase our understanding about the molecules which are essential for living organisms?
Certainly what will happen is that we will learn how to play with those new interactions that I've been describing. So, chemistry is essentially playing with electromagnetic interaction. So I told you that we rearrange the different atoms inside the molecules, and this rearrangement is due to the interaction with the photon. So the molecules are split by emitting photons. So what we are learning to do is actually playing with matter and playing with the weak and strong interaction. And that's exactly already what is happening for instance, in nuclear power plant, right? In nuclear power plant, you are playing with a different proton and neutron and using the weak interaction among those particles to produce energy. And certainly in the future, we will learn also how to use the strong interaction and how to use the interaction between the Higgs particles and the quarks of the lepton. And I don't know what we will be obtaining, right? Maybe we will form new form of matter, that new materials that nobody have been dreaming at the moment. But for sure, at some point, all these theoretical ideas, all this description of matter and their interaction will find some technological applications. Yes.
Okay. Next question. What is the mechanism by which matter gains mass?
Gain mass by interacting with the Higgs boson. So, for instance, the photon has no interaction with the Higgs boson. That's why the photon is a massless object. But
you actually answered that.
Right. The W and the Z have a large mass simply because they have a large interaction with the Higgs boson.
And last question. How did the Higgs boson prevent the universe from becoming a black hole? Yeah, everyone is curious about that.
Yeah, that's a good question. I don't know. I think I mean, it's difficult to answer this question because at the moment we don't have a good description of gravity at the quantum level. I told you, during the lecture that we could neglect all the gravitational interaction among the particles. This is true as long as the energy of the particle remains small compared to the value of the Planck scale. The Planck scale is 10 to the 19 GeV, so 10 to the 19 times the mass of the proton. So as long as you are doing an experiment which are at energy much smaller than this Planck scale, then you can neglect gravitational interaction. But when you will be approaching this energy, then gravitational interaction become the dominant interaction among the particles. And then in this case, yes, in principle, you can form some black holes, right? So you will take two protons. If you give enough energy, so energy close to the Planck scale, to this proton, then you will form a black holes. But that's something which is difficult to do at the moment because we still don't know how to give very large energy to this proton. There is not enough way to accelerate the proton to really reach this Planck scale energy.
Okay, thank you. We have finished all the questions at the moment. Okay, thank you for joining us today, and it was really amazing presentation. We have learned so many things. So thank you for joining us.
It was a pleasure to talk to you. Okay.
Okay. See you.
Hope to see you at some point.
Bye-bye.
Bye.
Okay. We will continue with our next session. See you.
Hello everyone, I'm Misra from the Agenastro team. First of all, I'm very excited, so if I make any mistakes, I apologize to you in advance. Now we will continue the topic of astrobiology as origin story, a cross-cultural journey with Daniella Scalice. Daniella Scalice is the education and communications lead for the NASA astrobiology program. She has led the NASA and the Navajo Nation initiative in which ongoing collaborations with the Navajo government and education community have resulted in classroom materials, which weave together science and cultural knowledge, as well as teacher trainings and student summer camps. She also leads a science communication training program for early career scientists called PAMELab, and co-developed a project-level impact assessment method that facilitates the assessment of overall project health and quality, as well as participants' impact. Hello.
Hello, thank you for having me. Can you hear me okay?
Yes, of course. Welcome to our conference.
Thank you so much.
How are you?
Doing well, doing great. Looking forward to sharing with you and hearing all your voices and thoughts and ideas about this work.
It's great. I hope I have not forgotten to mention an important point about you.
No, thank you for the introduction.
Of course. If you're ready, you can start your presentation.
Okay, let's make sure I can do this. Okay, that's not going to work. Let me try again. Press present, share screen. Share screen. Entire screen, thank you. Okay, got it. Sorry about that. Okay, hopefully you're seeing my whole screen. I'm going to go full screen with the PowerPoint. All right, if that looks good, I will begin. Okay, well, thank you all so much for having me. I'm very grateful to be here. My name again is Daniella Scalice. I'm joining you today from the lands, waters, and skies of the Piscataway people. These are the occupied territories known today by some as Annapolis, Maryland, United States, North America. I'm grateful that you're all here, and I look forward to sharing this journey with you and hopefully having a good discussion afterward. Okay, I'm going to jump right in and talk about astrobiology as an origin story, as a healthy expression of a culture that many of us are living in now, as illustrated in many ways by Western science. And as all of you know in astrobiology, this is the big sweeping story. This is from the beginning till now, how the universe was created. This is our cosmology, from how the Big Bang brought the universe into being and created many of the elements over time, especially those elements that are now sort of bound up in our solar system and our planet and our bodies and in the bodies and of all life forms here on Earth today. The story goes through how the Earth was formed, how our solar system was formed, all those processes that brought the Earth into being, what early Earth was like, what the conditions were like when life arose on our planet, what was going on, what energies were needed, what elements were needed, and then, of course, the origin of life story itself, and the last universal common ancestor and the emergence of the first life on Earth. And then, of course, through space and time, since that moment, how life and the Earth co-evolved together in a sort of cosmic dance where the environment put out an influencing factor and the life responded and adapted and innovated to live in the new conditions. And then, of course, life itself produces new environmental conditions, and back and forth over time in a beautiful, again, co-evolutionary dance that has produced the glorious diversity of life on Earth that we know it today. So, as you know, this is, again, a sweeping, big story that astrobiology is bringing into being right now. And so how can we
relate to this story? How can we bring this story, I should say, into relationship with other cosmologies that exist across the globe and have existed for since time immemorial, thousands and thousands of years, millennia? What is the relationship between astrobiology as origin story and these other cosmologies? And that's at the heart of the work that I've been doing for the past couple of decades. So before we get into that, I want to give a little bit of background for how things sort of are here in the US, and setting the stage for bringing astrobiology as origin story into relationship with other indigenous cosmologies of North America. So here in the United States, and I apologize for all the text here, but I think it's important to have it all out there. Our entire, every aspect of our lives here in the United States and our sort of white supremacist culture, very much including the enterprise of science and the systems of education that we have going on here, is deeply rooted in colonialism, which by definition marginalizes and eliminates indigeneity. The history of the interaction between Western and meaning European-based colonial cultures and indigenous cultures is an ongoing narrative of colonialism, genocide, land theft, broken treaties, assimilation, erasure, extraction, and appropriation. Histories of federal policies here in the US, such as the boarding school era, and we can talk more about that later if you'd like, as well as, very broadly speaking, Western cognitive imperialism and cultural hegemony, have paved the way for active exclusion of indigenous knowledge and extreme, quote unquote, underrepresentation of indigenous people, certainly in science, science education, science discourse, scientific practice. Despite this, as you hopefully know, indigenous cultures, people, voices, ideas, perspectives, knowledges, and lifeways are very much still alive and present, and in most cases, many cases, thriving. In others, struggling to survive still. So building relationship is really the foundation of everything that I'll share with you. Building relationship and trust. This is the foundational practice, and it can have positive impacts when applied in many settings across the scientific landscape, including STEM education programs, especially when Western and indigenous knowledges are brought together, free from a dominant paradigm. We can see this a positive impact when this relationship practice is applied to scientific nomenclature and efforts seeking to honor and include indigenous languages in the naming of things like comets or features on Mars or things like that. Ethics and responsible practices in field work. Indigenous cultures are very much tied to the land, waters, and skies. Where the people are thriving in those places. And so scientific fieldwork needs to evolve its ethical framework in order to understand and have a positive relationship when they go into the field and do field work. And of course, the indigenous data sovereignty movement, which basically means, again, within science, when data are collected in a way that involves indigenous lands, waters, and skies, which is every inch of the United States, we need to make sure that those data are in right relationship with the indigenous cultures who are responsible for those lands, waters, and skies. And they should have sovereignty over those data. So this foundational practice of building relationship and trust is operable across all scientific disciplines, certainly not just astrobiology, and can influence all of us and everything we do and our institutions and our education systems. This is the last wordy slide, I promise. So just wanting to also make a final point here, that we're talking about building relationship and trust, but the reality is that we, again, here in the United States and in the scientific community broadly, we're already in a relationship with indigenous communities that historically and contemporarily is defined by historical colonial violence. And this is a relationship that is not of the choosing of indigenous communities. We have the opportunity now to reimagine and remediate this relationship and build a foundation of trust, co-creativity, and collaboration. The potential for authentic reciprocal relationship between scientists and science educators and indigenous communities is ripe. And it can have many kinds of benefits, most importantly, to healthy indigenous lifeways. So with that background in place, I want to talk to you about a partnership that I've had the great good fortune and privilege to be part of for the past 18 years. We call it very simply NASA and the Navajo Nation Partnership. And this is an image of a place called Window Rock, which is in Arizona here in the United States, and is the seat of the Navajo Nation government. This is our team: Angela Barney Nez on the left, Alice Karen in the middle, Dana Nez on the right, and myself. We are celebrating 18 years of working together, which began in January of 2005. I always like to talk about the origin story of our partnership because this is the very important part of things. It matters how things get started. We'll talk about that later. A focus group, if you like, really more of a roundtable, was convened in January of that year. And all kinds of, it was on the Navajo Nation. All kinds of people came, educators, people from the tribal government, community leaders, medicine people, all to discuss a question. Is the Navajo Nation even interested in partnering with NASA on education initiatives? And this was very important because in beginning with that question and not assuming that the answer is yes, really demonstrates respect for tribal sovereignty and self-determination. So we had a wonderful 2.5 day conversation about many wide-ranging things, mostly focused on education and how it works on the Navajo Nation. How are the schools situated? How do they work? Are they federally funded? Are they charter schools? Are they public schools? Are they private schools? We discussed a new tribal legislation that would eventually pass called the Sovereignty and Education Act. We talked about when that passes, the need for materials in order to teach Navajo culture and language in those classrooms. What are the standards that teachers would teach to, and so on. So it was a very rich discussion. Some of the main essential points that were made from the Navajo side of the house, we focused and continued to focus on how the Navajo education system has changed over time, which is a euphemism for colonialism, and how their vision is to rebuild a new system, which, quote, preserves and perpetuates the identity and authenticity of what it means to be Navajo. So that was a very important guiding point in the discussion. And from the NASA side, we understood that we were not being invited in to fix anything. This wasn't the great white savior situation, but rather we were being invited in as authentic partners to serve Dene youth and communities. Dene is the Navajo word for people, the people, Dene people. So we were being invited in as authentic partners to contribute to this vision and represent the science authentically and be in service. So the outcomes were that, yes, collaboration is very much desired. Partnership must be equitable. Both parties must contribute. The two ways of knowing, both scientific and cultural, are 100% equitable. And anything we would do, produce materials, programs, need to weave together these two bodies of knowledge. Our foundational philosophies, which still guide our work today, very much so, and our core values, again, are recognition and respect for tribal sovereignty and self-determination. Relationality, and that really has to do with the absence of transactionality. Everything is going to be based around how we relate to each other and to the knowledge systems and the bodies of knowledge. We need to be able to hold multiple knowledge systems as equally valid, valuable, and vital. This is very important because in the sort of contemporary paradigm of science education in Indigenous communities, the knowledge systems, the bodies of knowledge, are not held as equal. It is typically done in a way where science and STEM broadly are the truth, are what's real, where Indigenous knowledge is considered myth or legend or lore or something like that. And it's usually presented after. The science comes first and Indigenous knowledge is presented after. So that's not going to work for us. We need to be co-creative where everybody contributes and we make decisions through consensus. And we need to prioritize and privilege Indigenous knowledge, again, presenting it first, only by Indigenous voices, perspectives, leaders, people, and on Indigenous lands. So our way of working evolves from this. Again, traditional knowledge, Indigenous knowledge is centered and presented first, always and only by community elders, cultural practitioners, language speakers, and educators. Corresponding Western scientific concepts are presented afterward by experts in those fields. And this way of working facilitates the learning of both Indigenous knowledge and STEM in a culturally based way. Over the years, we have produced 2 educator guides. We're working on a 3rd right now. Each of them contains multiple hands-on activities for Navajo youth. These are scenes from some of our workshops over the years. Again, always bringing together cultural knowledge and Indigenous knowledge. We bring in cultural experts. You can see on the upper left there, that's Dr. Johnson Dennison, a active medicine person in the Navajo community who's speaking to the teachers. These are some scenes from our student summer camps where we go out into the field, so to speak, and visit sites that are at once culturally significant and very sacred, as well as geologically rich and full of knowledge and information about the land from the scientific perspective. So our camps have been residential. We are seated at one of the tribal colleges, and it's about a week long. And each day we get on the bus and go to a different place. And again, our cultural experts and scientific experts come with, and we talk story, if you will, on the trails and in the places and spaces. And then at the end of the week, the kids get together in teams and talk about connections that they've made between these 2 bodies of knowledge while they were out there. So what does it look like, though? What does culturally based dual learning actually look like? How are we bringing together these bodies of knowledge? So a couple of examples. This is an activity that we've developed for teachers to use in their classrooms, and it brings together in the broadest of senses the 2 cosmologies, that of Navajo culture and that of Western scientific culture. And on the upper left, you can see an artist's painting of Navajo cosmology as told through a description of 4 worlds, each one progressing into the next and sort of ending at this time. So it doesn't really end, but currently represented by one of the worlds we're living in now. So similarly, Western scientific thought has produced a timeline, if you will, from the Big Bang, again, until now. And so you can see that physical timeline represented on the wall in the other pictures. And on that timeline are marked very significant events in the history of our solar system, the Earth, the origin of life, the evolution of humans, and so forth. Similarly, in the Navajo cosmology, we teach and talk about different events in the progression from one world to the next. And what we do is we talk about the relationship between some of those events from the 2 different cosmologies. And we're still experimenting with this, but one of the things we're doing, and you can see here what's happening, is that the teachers are using different colored yarn. And again, the 4 worlds have different colors. There's white, blue, yellow, and black. And so we present those colors in yarn, and they take those colors of yarn and place them along the Western scientific timeline where they think the correspondences are. So we're still working on that. We still think that has a little bit of a colonial, cognitive imperial framework to it. So we're trying to think more outside the box to finalize this activity. So that's an example of how the culturally based dual learning environment works. Here's one example from the summer camps. This is a place we visited with the kids called Chaco Canyon, and it happens to be a national park here in the United States, so it's pretty well preserved. And we go out on the trails and we look at the remains of some of the architecture that was there, that was built by the indigenous people who lived there a long time ago. And but we also look deeply at the geological formations that are in the canyon. You can see on the upper left, for example, those have been identified as shrimp burrows. And there are other fossils that have been found in the area of shark's teeth, for example. And so we talk to the kids about, the scientists talk to the kids about, as you can see on the upper right, basically a giant ocean that bisected this continent once upon a time and ran right through this area. This whole area was underwater. It was part of the ocean floor at that time. So hence there are fossils and remnants of sea life that lived there. So we talk about that, and it's recorded in the geology. And we also talk about the people who lived there, what their culture was like, and what they did, and the astronomy that they did with their buildings, actually. I believe the term is called archaeoastronomy. It's an extremely sophisticated way of understanding the heavens. So we talk about that as well, and then we jump off into Western scientific astronomy and things like that. So we have a very rich discussion and a great day there. And here's a quote from one of the kids at the end of the day. At Chaco, the people may be gone, but the spirits are still there. And the ancient sea is gone, but the rocks record its presence. Similarly, we visit a place called Canyon de Chelly, which is also in Arizona here in the United States. There's Dr. Dennison speaking to us about the people who lived there, looking at, you can see on the bottom, a place called Spider Rock. And he tells one of their fundamental tellings of Spider Woman and how she helped create the universe and brought weaving to the Diné people. We look at petroglyphs that are in the rocks at that place. But then we also talk about this spectacular geology of that canyon, and we make comparisons with different types of canyons on Mars and other places. And again, the kids are telling us they understand the relationship here. Both the rocks themselves and the petroglyphs are telling a story. So I want to wrap up with this, just getting back to this idea of relationships as being foundational to everything. Our relationships with each other, the bodies of knowledge relationship to each other, and how we can do this, how we can actually build a relationship in a good way going forward. So some of the things, and colleagues and I have written a paper about this, so this is just a few points from that paper, and I'm happy to put that in the chat if there's interest. But there are some things we can do as the Westernized scientific community prior to initiating a relationship. We can learn about the Indigenous community. We can learn about their history. We can learn about what has gone on in the history between the relationship between, for example, the federal government and that Native nation. We can also self-reflect. Why are we interested in building this relationship? Are we prepared to be involved in this relationship? Because one of the main parts of this is that this relationship doesn't end. It needs to go on. It needs to transcend grant making and funding and time, and it needs to be long-term. So we need to do some serious self-reflection about why we're interested in this. Are we prepared for this? What are our motivations? Are they to advance our own careers, for example? We might want to rethink that if that's the case. So with respect to initiating a relationship, we recommend having an open mind and not coming to the community with an ask of any kind or a set program. For example, I've often seen people where the relationship is initiated by, oh, well, we're writing this grant proposal. We'd like to focus on your constellations and your star knowledge. That's an ask. The relationship has to come much prior to that and needs to be strong and solid before you write proposals together, for example. Other asks that I've seen are, we're having a conference in the city that's on your lands, for example, Santa Fe, New Mexico, or Albuquerque, New Mexico. We'd like you to come and give an opening blessing. That's an ask in the absence of relationship, pre-existing relationship. As things progress, if you are invited to visit, we recommend being very humble, listening more than you speak, bringing gifts, things like that. building the relationship, spend time to cultivate it, give of yourself, be open, continue to visit, continue to bring gifts, build trust over time. What does that mean? It means saying you're going to do something and then doing it. It's as simple as that. Sustaining relationship. Again, continuing to visit and continuing to be open, giving of yourself. Maybe the time has come to write a paper together or to apply for a grant together, to start doing the work. Everybody needs to be included in that. Everybody needs to be part of that. Once you have a strong foundation of relationship and trust, then you can get to the co-creativity part. What is the shared vision? Is it summer camps? Is it teacher workshops? Is it co-storytelling at a powwow? What is it? And it needs to be driven by our Indigenous partners. What is their vision for their youth? What are their philosophies and core values? Once that's in place, then you can start working toward writing grants together, doing work together, whatever it is, making programs together. And the relationship can be sustained through the doing of the work. And just a final note, recognizing that the community is under no obligation to partner with us. They are, again, sovereign nations with their own way of being, their own way of doing. And so this is where we can check our baggage of hubris as the scientific community at the door and let go of the expectation that everybody wants what we have because we're Western scientists and we know the quote unquote truth about the universe, and offer ourselves in humble service, however that needs to be. So I leave you with that. Thank you. I can put my email in the chat, and I would love to be able to hear your thoughts and have a discussion with you. I'll stop sharing now. Thank you.
Thank you very much for everything. It was a very informative presentation. Also, you explained everything very nicely.
Thank you. Good.
If you're ready, we can take the questions. The first question is, what methods can be used to detect the presence of life on a planet, and what are the cultural implications of these methods?
Oh, what a fun question. Thank you for that. Cultural implications of those methods. That's something I could attempt to speak to, but I do not identify as Indigenous to North America, so I won't attempt to speak for the Indigenous communities here. But we can talk about, there are many ways to think about detecting the presence of life on a planet, and I suspect the other speakers in the conference will give much more detail on this. But certainly within NASA, there are several different areas of influence going on that have to do with sending actual spacecraft, robotic spacecraft, to other planets in our solar system. And they each will carry a suite of instruments that will be able to detect certain things about the environment, the geology, and so forth. And again, any mission that carries a camera on it should probably be considered a life detection mission, because any form of life could walk or swim in front of that camera, and there you have it. But there are also methods, and I think Eddie Schwiedeman is going to talk about this maybe tomorrow, to detect life on a planet around another star. And that's a very different type of detection that has to do with high-powered telescopes and things like that. So, but with respect to the cultural implications of these methods, again, I'm not sure I certainly wouldn't attempt to speak for communities, but what I think we do need to do as a scientific community is ensure, because the scientific community is holding the power, the energy, the resources, the money, to build and make these things. And so the onus is on us to make sure that the doing of that is inclusive of all perspectives, of all nations, globally. NASA does a really good job of saying how its exploration is on behalf of humanity. And so I think it does a good job of saying that. I don't think it does a good job of meaning that and demonstrating that. So again, with a foundation of relationship and trust, I would like to see NASA and others move forward to ensuring that all perspectives are included in how and when and why we attempt to detect the presence of life on a planet. So I think that's the best I can do with that question. Thank you.
Thank you. The next question is, what is the importance of astronomy in our daily life?
Oh, thank you. That's a great question. Well, I think that needs to be up to each of you. But for me, I think the stars are extremely important. They're our ancestors. We wouldn't be here. We wouldn't be walking and talking and having this conversation at all unless there were generations of stars prior to us that, turned the first hydrogen into the first carbon and turned the first helium into the first calcium and the iron. So for me, the relationship to the stars is very important. It reminds me that I'm connected to absolutely everything else in the universe atomically. I think this is a quote from Neil deGrasse Tyson. We're connected to everything else in the universe atomically, everything on the earth chemically, and every other form of life biologically. So understanding the role of stars in that is the key. So to me, that's the importance of astronomy in my daily life, is to remember my relationship and my connection to all that is.
Okay, thank you. What do we need to do first in order to be an astrobiology researcher? Do you have any suggestions for our scientists? Sorry for that.
That's okay. Candidates.
Candidates, thank you. Who are considering becoming astrobiologists?
Thank you for that question. Yes, so the way the path seems to be unfolding for people who want to become astrobiologists is that the recommendation is to kind of find, there's so many parts to astrobiology. There's geology, astronomy, biology, chemistry, physics, paleontology, and all of the intersections between each of them, biogeochemistry, and so on. So the recommendation is to feel out where you fit. Are you attracted to working with rocks? Do you want to be looking through telescopes? Do you want to be going to, hot springs in the middle of a desert and sampling and culturing microbes in the lab? Are you a paleontologist? Do you want to spend time thinking about microfossils? And are you a chemist? Are you interested in atmospheric chemistry? Are you interested in the atmospheres of other planets or moons in our solar system? Feel out and find your place, and then pursue your doctoral degree, very deeply in that place. Planetary science, geology, molecular biology, and so forth. And then from that position of grounding, depth, and strength, come and join the sort of community of astrobiologists where your specialty and your depth can now be brought into the same space with those of others, and you can enter in a deep way the collaborative space of astrobiology. Having said that, that requires some sort of side training as you come up, which has to do with interdisciplinary communication. Different scientific disciplines have different cultures, really, in many ways. They have different languages in many ways. Certain words mean different things to geologists and astronomers and so forth. So make sure you're holding space for learning how to communicate with each other, because you can never do astrobiology on your own. You have to do it with all the other scientists. So we have to be able to communicate with each other, and we have to create safe, psychologically safe and inclusive and open and welcoming and belonging work environments. That really needs to be part of our training as well, from the ground up. So thank you for your question. And again, I'll put my name in the chat or my email, and I'd be happy to talk with you more if you have more questions about that.
Okay. How can intercultural travel and the study of astrobiology help us better understand the origins of the life and the universe?
Oh, that's great. Thank you so much for that question. So in our work in bringing these two cosmologies together, we have been struggling to find the word. We have been totally awestruck and amazed at the resonance between the two stories, both from the scientific perspective and the Navajo cosmology. The similarities are spectacular. For example, the Diné cosmology accounts for things that the scientific community has observed and has created evidence for, and things like the Great Oxidation Event, Snowball Earth, the Western Interior Seaway, as we talked about, that bisected North America, flooding, things like that. All kinds of the Hadean, the entire Hadean is accounted for in the Navajo cosmology. So in this way, how can it help us better understand the origins of life in the universe? This, I think the best way to say it is that, have you ever really looked at the word universe as it's written in English? This is a compound word with two components, uni meaning, of course, one, and verse referring, depending on the definition you look at, referring to song. It's a song. So the universe is really, I mean, when we hear that word, we think, oh yeah, this big giant thing with all the stars and planets in it. But it's actually, the word actually translates into English from Latin as one song. And so the more we can bring these cosmologies together and hold them as equals and allow them to interact and show us how they resonate, the better we can sing the one song together.
Okay, the next question is, how Earth survive a gamma burst from a black hole or a quasar?
Okay, I thank you for that. I'm not sure I can answer that. To my knowledge, I don't think the Earth has survived such an event. I don't know if it's experienced such an event. Please enlighten me if anyone knows. The one thing I can tell you is that we have a very robust magnetic field that certainly protects us from solar radiation from our sun. A gamma burst from a black hole or a quasar might be something else entirely, but I would sure hope that our magnetic field could hold strong for us. Again, please, if anyone else has thoughts or knowledge on that, I'd love to learn from you.
I don't know that too. The next question, what is the importance of the astrobiology education for prisoners? What can they gain with this education, or what can we gain from this?
Thank you so much for that question. This is a body of work I've been involved in for a number of years that I didn't talk about today, which has to do in a similar way of sharing the astrobiology as origin story with people here in the United States who are incarcerated and really don't have, both adults and children, who really don't have access to science education in the same way others do, and but have the time and the desire and the right to learn about these things. So the importance of that can be framed in a couple of ways. It can be framed just as in a social justice lens, where, again, NASA does a really good job of saying that it wants to share, the stories of the universe and all the knowledge that it's creating with everyone, and that everyone needs to be involved in what NASA's doing. Okay, well, if you really mean that, then we have to be serious about everyone. And let's have a look at who we can serve and where they are and how we can reach them. And again, reaching these communities is a matter of relationships and ensuring that we can come in and share. We've done evaluation on our programs, and we have learned that they are learning everything very quickly, in a very short period of time. So they're actually gaining knowledge in the situation. But what we're finding, a couple of interesting things we're finding that we hear over and over again, is how grateful people are that NASA would come to see them. That big, strong, powerful NASA, right, would take the time and the effort to come visit them. There's a very strong stigma for people who are incarcerated. I think there's a lot of shame and a lot of broken self-confidence and self-love. And that doesn't need to be that way. There are lots of circumstances for why people end up in the carceral system here in the United States. It's really just an extension of the injustices that have been perpetrated on Black and Brown people here in the United States systematically for centuries. So we have a lot of problems to solve, but there's, what we were hearing was a lot of amazement and gratitude that we would come. So we're bringing that inspirational capital with us as NASA when we visit places and people like that. The other thing is that there's a lot of communities within the incarcerated world that are heavily involved with faith-based traditions, like Judeo-Christian, mostly Christian, here in the US anyway. And so we were able to frame, again, much like the work with Indigenous communities, we're able to frame the astrobiology narrative as a narrative, not as the only narrative. And so we were able to have very fruitful and beautiful dialogues about the Christian faith-based narratives that are really serving in a good way folks who are incarcerated and bringing them together with what we're offering from the scientific perspective.
Okay, another question. Where and how macromolecules and building blocks were formed before the first cell formation?
Thank you for that question. Again, I think some of my colleagues later in the program might be getting more into that, but the way we teach about it has to do with the conditions on early Earth and what types of scenarios, what physical scenarios were present at the time that could have given rise to our last universal common ancestor, a protocell situation. So, and the basic thinking about that is that we need to have the raw materials, we need to have the actual simple molecules, carbon dioxide, ammonia, things like that, very simple, non-macro molecules and building blocks. They are present physically because of how the Earth differentiated and formed. There was an early atmosphere, there were early oceans that had particular pHs and salinities, etc. So the raw materials have to be there. The energy has to be there. There has to be some source of energy to get these molecules together so that they can interact with each other and build macromolecules, eventually building themselves into cellular-like structures. So there has to be energy, wave action, crystal surfaces, volcanic, geothermal heat, all kinds of environments on the early Earth, sort of microenvironments, will have different combinations of the raw materials and the energy sources. And that's where we get to sort of the third factor, which is the container. It's one thing to have the energy there and to have the tiny molecules there, but if they can't find each other, then they can't interact and progress on an evolutionary way toward a cellular structure. So you have to have physical ways to get them together. There are many different theories about that. Hot spring systems is one way to hold them tight together with heat and water and porous rock spaces in black smoker chimneys, for example. I think one of the prevailing theories today has to do with puddles, so to speak, on a surface that would have a cycle of being wet and being dry and being wet and being dry. So those are some of the theories that are present today in the Origins of Life community.
Okay, thank you. What kind of problem can the gravity of Mars cause in the human biological system?
Okay, I'm not sure I understand that one. The gravity of Mars. Okay, sorry, I think I have it. How does the gravity of Mars relate to human biological systems? That's a great question. Again, I think my colleagues are going to be able to answer that a little bit more later in the program. But I think you're talking about potential eventual human settlement on Mars and how the gravity of Mars how we would need to deal with the gravity of Mars. My understanding is that the gravity of Mars is significantly less than it is here. So we will have to, please correct me if I'm wrong, we will have to develop systems that work in the absence of a lot of gravity. So we have the benefit of that here. It holds us on the planet. It holds our stuff on the planet. It applies certain pressures to things, which can do work. So we'll have to account for that. But over to my colleagues for more on that. Sorry.
Thank you. The last question is, how would you describe astrobiology in one sentence?
That's fun. Thank you. How would we describe astrobiology? I'd love to hear your thoughts on this too. But to me, astrobiology is the Western cultural expression of our origins.
I think the astrobiology is understanding the universe. That's all I think about.
Yeah. And I would just add a dimension to that, again, from our particular cultural lens. There are many other understandings of our universe.
Yes.
Thank you.
And that's the all question, I guess.
Great.
Yes. Thank you for your answer. Thank you for your answer. And thank you very much for coming and taking time for us. Your presentation was very valuable to us. Is there anything else you want to add?
No, I'm so grateful for this opportunity. And again, my name and email is in the chat. I would love to hear from you. And I wish you all the best with the rest of your conference. Thank you for letting me be part of it.
Thank you for joining us. Have a nice day.
You too. Take care. Bye, everyone.
Thank you. Bye.
Hi again, everyone. We will move on with our next guest, Dr. Sanjoy Som. He is a scientist, engineer, and social entrepreneur about space exploration and astrobiology. He is the CEO of the nonprofit Blue Marble Space Institute of Science. I was a research assistant in Young Scientist program in 2021, and it was really incredible experience for me. If I'm not wrong, this year applications are still on. I encourage you to apply actually. Dr. Som is also a scientist at NASA Ames Research Center. He is selected as Voices of Sciences Ambassador. He is an Earth system scientist and aerospace engineer interested in interdisciplinary approach to scientific problems. His current research focuses on understanding the physical properties of the Earth's ancient atmosphere using geological proxies and quantifying the link between environmental geochemistry and bioenergetics. He also has a project actually on Salda Lake. Today, he will talk about thinking at multiple scales, the search for life in the universe, and the quest to quantify habitability. Hi, welcome.
Hello, can you hear me okay?
Yeah, we can hear you.
Great.
Thank you for joining us. Because it was really hard to welcome you here. 3 years I was always emailing you, but you have so busy schedule. That's why it was really hard, and I'm really happy to welcome you here at this conference.
Well, thank you very much for inviting me. I was always very disappointed not being able to attend in the previous year, so I'm very glad that I can connect with you all today.
Yeah, thank you. Okay, you can start to present your presentation, and I will take to screen. Okay, stage is yours. Thank you.
Thank you very much. Well, good morning and good afternoon and good evening, wherever you're connecting from. It's a great pleasure for me to be here and be able to present at this conference. As I mentioned, I've been trying to talk to you at this meeting with all of you in Turkey for a long time, and this year it worked out, so I'm very excited. What is amazing about today's world is that you and I can be almost in the same room, despite the fact that we are so far from each other. It's a new world that we live in, that we can communicate so clearly at so far distances. Ankara and San Francisco, where I am, are separated by 11,000 kilometers, which is a lot, from the human perspective. And it's worth thinking about whether the distance is effective in our own mind, or is it a true distance? And what I mean by that is, from a different perspective, 11,000 kilometers is actually not far at all. This is a picture called the pale blue dot that you're probably very familiar with. It was taken in 1990 when the Voyager 1 spacecraft turned back around and took a picture of the Earth. It's at a distance of about 40 AU from the Earth, where 1 AU is the distance from the Sun to the Earth. So from this perspective, you and I at this very moment are exactly at the same location. The Earth and the galaxy in which is so vast that 11,000 kilometers is absolutely nothing. And so this is true also when one thinks not only in space, but in time as well. If you do some statistics about the human population, you and I, all of you in the audience and I, have a common ancestor going back, I don't know, between 3,000 and 5,000 years ago, which is not a long time. I'm sure you've all seen the pictures of the Neanderthal cave paintings, where they have the handprints on the rocks, and with the red ochre traced their handprints. These are ancestors, direct ancestors to all of us. From that perspective, we are cousins. But given how old the universe is, 13.7 billion years old, a few thousand years is in the noise. So all of us and all the humans that have lived up to today are essentially born at the same time, and we are currently at the same space. I think this perspective is very healthy to have. It really introduces the fact that we're all brothers and sisters living a same future, living a same life together on a very small planet. In our modern days, we get trapped in the space and time of where we live. We have to go to work, we have to go to school, we have to go to the grocery store, we get mad about the politics in our own countries. But with the perspective that we live on Earth, among our brothers and sisters, and if this perspective is shared, I think, among more humans, then maybe there's a path to realize that we're all humans first and foremost. And the diversity, the magnificent diversity that we have about the colors of our skin, the gods we believe in, the languages we speak, the food we enjoy, adds richness to this humanity. Yet for thousands of years, these differences have been used as a source of conflict. And it's a complete tragedy, because again, from the perspective of space and time, when you just increase your ability to see in space and in time, you realize how common, how unique we all are. The discipline of astrobiology is powerful because it seeks to ask an incredible question about whether or not we're alone in the universe. And the answer is fundamentally important, because if indeed, after all our efforts, we find that we are alone in the universe, well, this means that humanity is the guardian of intelligence in our galaxy. Are we prepared as a species to have that kind of responsibility? That's for us to decide. I'm not convinced that we're there yet. And conversely, if we do in fact find that there is life elsewhere, what does it mean to be human? Will it take the discovery of extraterrestrial life for humanity to realize that is in fact a common family? So that's where the power of astrobiology comes in the broader scientific perspective. So when I was asked to present at this conference today, I was thinking about what I could share with you that's perhaps different than what you already know. All of you are interested in astrobiology. You know a lot about physics. You know a lot about astronomy. You know a lot about biology and chemistry. So what kind of new angle could I present to you that would help you grow in your careers as scientists and students and as humans? And so that's why I thought I'd have presented this talk about the ability to think at multiple scales and couch it within the discipline of astrobiology. As I mentioned, I think you can become a better scientist and a better human if you're able to think at scales that are larger than the scales that we think on a day-to-day basis. So I'm a geologist and a geochemist, so I enjoy thinking about the time aspect. I think that's very inspiring. But the spatial aspect is very inspiring as well. So let's get that out of the way right now. This is kind of a change in scale from the top left to the bottom right. So let's go through it, because I think it's a very humbling experience to go through this process. So on the top left, we recognize our own planet. And our own planet is big from our perspective, 11,000 kilometers between Ankara and San Francisco. There are direct flights that take us between at least San Francisco and Istanbul, and it is a long flight. But then again, the Earth is part of a solar system. So if you look at the image on the right that says solar system, the Earth is a very small dot in a much larger family of planets orbiting a single star. But our star, of course, is within a family of stars called a solar interstellar neighborhood. Around each of these stars, most likely, is a planet or multiple planets that orbit it. And it's an exciting time to be alive today, because we can actually put some numbers as to how many planets are orbiting these close by stars. This interstellar neighborhood, of course, is just in one little corner of the Milky Way galaxy. So we are not towards the center, we're not towards the back, we're kind of like 2/3 of the way out in one of the spiral arms in a vast galaxy that contains probably around 1 billion, with a B, stars. So that's already very humbling. But our galaxy is part of a local galactic group of other galaxies. And there are images that I'll share later in this talk called the deep field images, first taken by the Hubble Space Telescope and now updated with the James Webb Telescope, that shows the incredible diversity of galaxies that are out there. Now, our local galactic group is part of the Virgo supercluster of galaxies. So you can see the scales is starting to get overwhelming here, because our local group of galaxies belongs to another group of galaxies, which is itself is part of a local supercluster of galaxies within an observable universe. I think we need to take a deep breath here, because this is just humbling. What are we? We are what Carl Sagan called mites squibbling on a plum, right? It makes kind of our day-to-day problems feel insignificant. Not that they are. What we're experiencing on a day-to-day basis is really relevant to our day-to-day lives, but put in a global perspective or in a galactic perspective, it calms you down a little bit, which is important. So as I mentioned, I find a great deal of value in thinking about time, and I want to take you a little bit through that journey as well. So I'd like you to join me in these wonderful chairs on the shores of Lake Superior in Canada. So the northern shores of Lake Superior contain very old rocks. So the rocks that the chairs are on here are almost 2 billion years old. So they were formed in a time where the planet was very different than what it is today. And I'm looking in a direction east here for a good reason, is because about that time, 1.9 billion years ago, 400 kilometers from where I am right now, it was a catastrophic event in the history of Earth. It's called the Sudbury Impact Event. There's a meteor that crashed into the Earth, the second largest impact crater recorded on Earth today. The largest is in South Africa, but the second largest is in Canada, and it's 400 kilometers from where I took this picture. You can still see the crater in the rock record. It's kind of deformed because it's so old, the land has moved, but nonetheless, it was a catastrophic event for all life that was nearby. Do we know anything about the life that was nearby 1.9 billion years ago? I'm sure you're familiar with trilobites, the diversity of life that came about on Earth about 600 million years ago. Well, we are talking about life on Earth 1.9 billion years ago. So this is 3 times older than the trilobites that you might be familiar with. So if you go from that locality where those chairs are at, and you walk about 1 hour in the forest to another location along the shores of Lake Superior, you come across a locality called Schreiber Beach. And this is Schreiber Beach, not much of a beach compared to the beautiful beaches you have in Turkey, but nonetheless, from a Canadian perspective, this is paradise. And from a geologist's perspective like mine, this is incredible. So this is me for scale there, and you can see what I'm sitting on, all these round features. And this is not geological, this is microbiological. These are essentially the cross-sections of microbial mounds called stromatolites. Stromatolites are found throughout the ancient rock record and up to the modern rock record as well, because they're still alive today. You can find stromatolites in areas that are a little bit, saltier than the ocean. And when it's too salty, the snails and whatever biology that can eat the microbes are not happy, so they don't live there. So that allows the microbes to grow. So the microbes kind of coalesce together, and they kind of go on top of each other. They go upwards because they're in the water wanting to get to the light. And as their cilia of the bacteria baffle the water, they trap the sediments, which falls on the microbes. The microbes climb above it. And again, so slowly, little by little, those sediment mounds form. So today you can go to special locations, for example, Shark Bay in Australia. So this is a modern picture of Shark Bay in Australia, where you have those stromatolites. Those are biologically constructed structures. This is what life looked like on Earth 1.9 billion years ago, right? There was no snails, there was no animals that we can think of or know of during that time. It was way before there was any large amounts of oxygen in our atmosphere, right? The air was very different, and yet the planet was very much alive. Here's another picture of stromatolites underwater. They're absolutely stunning. And so these are, my friends, our ancestors to all life on Earth. The ancestors between you and the tree that you have outside is these guys, these stromatolites. So it's very useful to appreciate biology today, to think about life in the past. And so that's where I find it's very humbling to be an astrobiologist, because you can be very creative with your mind, grounded in science. But here I am imagining what it was like on Earth 1.9 billion years ago, sitting among the stromatolites, watching the impact crater crash into the planet and devastating the area. Within the rocks in that area, you can find evidence of shock structures and materials have come from this giant impact. The rocks record the environment, and if you understand the language of geology, then suddenly you have a beautiful book of Earth history that opens. It's like if you're given literature that's in Chinese and you don't know Chinese, you open the book, it doesn't mean much, but as you learn the language, the rich literature that is Chinese literature comes alive in your mind. The same is true for the rocks. They kind of look like stones if you don't know much about geology, but as you learn the language of the rocks, you have this incredible story that unfolds in front of you. Now, I've been talking about ages that are in billions of years, and it's not easy to wrap in your mind what actually that means. So let's try a little exercise together with an arrow of time, right? So what this means is that on the right side of this arrow of time is this presentation right now. And on the left side of this arrow is when the Earth formed. So the Earth formed 4.5 billion years ago. At the location of where the Earth was today, there was another planetary body called a planetesimal, probably smaller than Earth. And it was impacted by another planetesimal the size of Mars. And this collision created the Earth-Moon system. So the Moon was part of Earth in the far past. And this collision kind of creating the Earth-Moon system is called a moon-forming impact. And that's essentially what starts the clock of our planet. And it happened about 4.58 billion years ago. So that's the left side of the arrow of time there. So often when I give this presentation, and sometimes to children, I ask them, like, what is the oldest animal you can think of? And they tell me dinosaurs. I'm like, yes, dinosaurs are very cool, even to a deep time geologist. And where do you think in this arrow dinosaurs appear and die? So I'll give you like 3 seconds to think in your mind, where do you think dinosaurs are? And dinosaurs are in fact right here. So the first dinosaurs appeared roughly in the Permian, so that's 250, 270 million years ago, and got extinct at the KT impact that hit in modern day Mexico 65 million years ago. So they had a long stretch of time, you know, a little under 200 million years of activity on our planet. And yet that was essentially yesterday in the grand scheme of the arrow of time of Earth, right? So the Earth is 4.5 billion years old. So in the middle is 2.2 billion years ago. And that's roughly when the air in the atmosphere started accumulating oxygen. So for more than half of Earth history, there was no oxygen on the planet. And yet it was very much alive, as I mentioned. The stromatolites that I showed you in Canada are a bit younger. They were 1.9 billion years old. But in places like Australia, which has even older rocks, you can find stromatolites that are 3.5 billion years ago. So those are really old evidence of life on our own planet. So just from this perspective, we can tell that the Earth has changed markedly over its history. And the Earth we live in today is just a snapshot in time of the Earth that has been and the Earth that will be. What's incredible about Earth today is that it is populated by biological species, humans, that can actually control the fate of themselves, the fate of biology on Earth, and can control the state of the planet for the future. That has never happened before. Are we able to come together as a society, as a humanity, and take the planet in a path that is good for us? In the current climate of our world, I am anxious about that statement. So let me take you even further back in time. Two examples of some rocks that are older, much older than the dinosaurs, and that record an environment before oxygen started accumulating in our atmosphere. And you're able to see that you can already say a lot about our planet from very old rocks. So here's one example. Isn't it cute? I'm talking about the rock below, of course, not the meerkat. That's there just for scale. But you can see the rock underneath it is actually an ash layer that is 2.7 billion years old. And you can see that it's full of little holes. And these holes are actually craters, small craters formed by rain. So this rock here, which is from South Africa, is the oldest weather report of our planet. It shows us that it rained on Earth 2.7 billion years ago. And why is that interesting? Well, the size of the crater can tell us how thick the air was, right? I mentioned that this is a time before there was any oxygen. So right today, our atmosphere is essentially 80% nitrogen, 20% oxygen. So if it was a time before any oxygen in the atmosphere, was the pressure of the Earth less than it is today? Because if the air pressure today is 1 bar, that's 80% nitrogen, 20% oxygen. If you remove the 20%, all you're left is 0.8 bars, right? So what was the pressure on the early Earth, right? It had absolutely no reason why it had to stay at 1 bar, the value it is today. So that's where studies that look at these craters formed by rain come in handy, because they can tell us the thickness of the air. If the air was thick, the drops would fall slowly and the craters would be small. If the air was thin, the drops would fall faster and the craters would be larger. Now, we don't know the size of the rain that form these raindrops, but what we can do from physics is note that the maximum size a raindrop can be is independent of how thick the air is, independent of air density. And so you can use that as an upper bound of the size of the raindrop that formed these craters, and thus back calculate how thick the air was. So you can do atmospheric science from geology using rocks that are very, very old. Here's another example of a rock that doesn't look like much, right? This is a rock from Australia that is the same age as the rock from South Africa. What you see here is the top of a lava flow called a basalt, and it has a bunch of bubbles at the top that are filled in with secondary minerals. You can see the Swiss Army knife up top there for scale. It's not a very big rock. You can walk by it and not notice anything about it. But if you're a geologist, you're like, ooh, this is very interesting, because it can remind you of a bottle of Coca-Cola. When you open, you see the gas bubbles at the bottom. As they rise, they grow in size. And how big they grow as they rise depends on how much pressure there is on top. So a bottle of Coca-Cola is, when it's closed, you don't see any bubbles, because the pressure inside the bottle is quite high. But if you remove the cap of the Coca-Cola bottle, expose it to air pressure, which is less than the pressure inside the bottle, the bubbles suddenly exsolve and rise from the bottom to the top of the bottle. And as they rise, they change in size, right? So you can use the size difference of the bubbles in a lava flow from the bottom to the top to calculate the air pressure on top, right? So what is the air pressure? What is the pressure, rather, acting on the bubbles at the top of the lava flow? It's just air pressure. What is the pressure acting on the bubbles at the bottom of the lava flow? Is air pressure plus the weight of the rock. So if you can measure the size of the bubbles at the bottom and at the top, which you can do using X-ray, the same technology that is used to image your bones when you go to the doctor and you had an injury. A little higher power, of course, to look into rocks, but nonetheless, it's the same principle. If you know the size of the bubbles at the bottom and at the top, and if you know how thick the rock layer is, you can back calculate what the air pressure is, right? So that's another example of creative thinking in using rocks to say something about the environment. And there's a bunch of different ways scientists and deep time geologists have used rocks to extract information about what the Earth was like 2.7 or more billion years ago. And that's how we know the Earth was a very different planet. And again, we use our ability to think back in time, use our imagination and what we know about the rocks to think about what the Earth was like 2.7, for example, billion years ago. So in this picture, you can see the stromatolites on the shore that I showed you evidence of from the back time. That's essentially what biology looked like in this world. There was no grass, of course, no animals, no trees, right? So because there was no biological activity the way we have today, there was no soil that we can really, not in the same sense at least that we think about today. What you would see is these large land masses full of lava, black lava, right? And in distance, you would have these volcanic islands, similar to Hawaii, shallow slope because the Earth was much hotter, so you can't really build steep slopes, kind of erupting a lot. So the Earth has been slowly cooling over time. So if you go back in time, was much more geologically active, so the volcanic activity was much higher than it is today. We know there was an ocean because we know it rained, and not too far from the lava flow picture that I showed you, you can see evidence of lava entering a body of water and kind of shattering, creating glass. So when lava flow flows into a body of water, the cooling is very, very quick. It's a process called quenching. The crystals in the rock don't have enough time to grow. So what you see essentially is glass. So there's evidence of that in the ancient rock record. And in the ancient rock record, you find evidence for rivers. And so it was a planet that had a lot of water on it and less land mass. So the land mass we acquire today, the continents have been slowly growing over time. Also let you know that from the rocks, we can say something about the air. We know there was no oxygen in the air because of the minerals that we find on the surface. And also the sun was brighter back then. So the sun is slowly becoming less, the opposite. The sun was fainter back then. I'm very sorry about that. The sun was fainter back then, and it's slowly getting brighter over time. And so, yeah, the fainter sun, the moon was quite a bit closer to the Earth than it is today. So the moon is slowly moving away. Back then, it was much closer. The Earth was spinning faster. So a day was 12, 15 hours instead of the 24 hours that we have today. Fast spinning Earth, the moon is closer. It means the tides are stronger. So for all intents and purpose, the early Earth was an exoplanet, right? The sun was emitting was not as bright and was much stronger in the extreme ultraviolet. The planet was different, the air was different, and yet it was very much alive. So in fact, the best studyable exoplanet is in fact our own planet a long time ago. And the reason why it's the best exoplanet to study is because we have the rocks. We can say a lot about a planet with just the rocks. So if there's anything I want you to take home from this presentation today, is that the rocks are the history book of our planet. They tell our common story, and they will record our common future. So our behavior today as a society, we can't hide that from the future geologist, the geologist of the future. That will become recorded in the rocks. Already today, the nuclear tests from the 40s, that evidence is in the rocks today. Future societies will be able to understand our behavior based on what they see in the rocks. Okay, so let's kind of the geological picture I want to paint for you of a planet that has been changing over time, that will continue to change. And the Earth that we live in today is just a snapshot in time of the planet that has been and that it will be. But nonetheless, it's a beautiful snapshot. It's a planet that I'm proud to call home, and I will do my best as a human on this planet to make it a better place for our descendants. But let's change gears a little bit now, because this is a planet that we recognize, right? This is obviously Earth from today. We recognize the clouds, we recognize the continents, we can tell what continent it is. This is North America with South America on the bottom right, and you can see the oceans. But then we can go back a little bit and take a picture of the Earth again. So you see the bright dot. Let's see, I don't know if you can see my mouse, but I'm circling the Earth there. This picture was taken in 2004 by the Cassini spacecraft that was orbiting Saturn. This is perhaps the coolest selfie that humanity has ever taken of itself. But we know it's Earth because it's a picture taken in the context of a solar system that we're familiar with. You can see the rings of Saturn there. The hue of the planet, that blue hue, is very unique to our planet compared to the neighbors like Mars, which you can identify very clearly in the sky because of how red it is, and Venus, which is not blue because of its very high density atmosphere and haze. And so we can keep going backwards and go back to that pale blue dot picture that I started this presentation with. You can see the pale blue dot within the sunbeam here. That is Earth as well. But from that perspective, it could be any planet. It could absolutely be any planet. So that's, again, where you can use the creative aspect of being an astrobiologist and kind of imagine what that world will be like. So it could be a world that looks like this. Who knows? A planet that has rocks, a planet that has water. If it has water on the surface or any other fluid, it probably has weather. Will that planet have biology? Who knows? But it could. So we take, again, the ship of the imagination and land on this planet, and we may encounter a biology that looks unfamiliar compared to the biology we have on Earth today. And one of the reasons is the biology on Earth today is very much tied to the sun, right? The colors that we see, that you and I see, are the wavelength at which the sun is the most intense at, right? So the eye has evolved over time to be sensitive to where the sun is the brightest, right? It makes sense. But if our sun was not the sun that it is, a different kind of star, like an M dwarf or another type of star, then the biology would adapt to the local intensities of that particular star. So plants may not be green, they might be different colors because the sun's, their star's intensity is different than our sun, right? We sleep during the night and are awake during the day, so we're very much slave to the rotation of the Earth. So how would we operate in a planet that was spinning much faster, right? Well, the local biology will have adapted to these conditions as well. So not only is humanity a product of the long evolutionary history of the Earth, but also of that of our star, right? We're really built for the Earth with a sun. But all these stories I've been telling you now is kind of a figment of the imagination. Can we be scientific about it? And the answer is yes, because we live in this very exciting time where we have telescopes that can look at faraway worlds away from the disturbance caused by the Earth atmosphere. We have rockets powerful enough today to launch space telescopes. And one of the most exciting one is the Kepler Space Telescope that was launched in, when did it launch? 2004, 2006, somewhere in there. It's no longer operating, but it was a very successful mission. And it looked, essentially, it stared at like 10,000 stars without blinking. And it did not look straight into the Milky Way, the bright band of stars you see in the sky, because it's too bright, nor did it look at 90 degrees up, because you're outside of the plane, outside of the galactic plane, so there's not as many stars. So it kind of looked not inside the galactic plane, but a little bit above it, at a patch of space between the stars of Deneb and Vega. And as I mentioned, just stared continuously at all these stars without blinking. And what the telescope was looking for was slight dips in the intensity of the light coming from each of these stars. And the dip in intensity could reveal whether or not there was a planet orbiting that star. And so in the beginning, we were not quite sure what to expect. And I was lucky enough to begin my scientific career after my doctorate at the NASA Center, where I'm still am today, NASA Ames, which is where the Kepler telescope was managed from. And being a young scientist, I remember the scientists were like laughing because there are planets everywhere. So this is a slide on purpose that I selected that is very old. The data is 10 years old. And the reason I'm showing this older data is because in 2 days, you will have a presentation by Dr. Eddie Schwieterman, who is an exoplanet scientist, and he will give you all the latest results on the exoplanets. But I don't need the latest data to make my point here. This is 10-year-old data, and yet the Kepler Space Telescope found planets everywhere that it looked at, right? And the patch on the sky that the telescope looked at was very small compared to the overall, hemisphere of the sky that we see at night. And so this means that everywhere you look at in the sky, you will look at in the direction of an exoplanet, which is humbling, right? We always thought of the Earth, you know, in the times of Galileo, like there was a geocentric model, the Earth is at the center of everything. And now, my goodness, were we wrong, right? It was just a drop in the sand in a beach of planets. And so it's very, very special to be alive today and be able to make those discoveries. These discoveries are going to be enhanced by the James Webb Space Telescope. It launched in January of last year and completely changed the perspective we have about our galactic neighborhood. In fact, so much so that this is the new deep field, well, a portion of the new deep field, and every piece of light that you see there is not a star, but a galaxy. Each galaxy containing billions of stars. The only stars in that picture are the two that have the radiant the cross around them. Those are actually stars, but all the rest are galaxies. So it's just mind-blowing about how big the universe is. And so the question about whether or not we are alive in the universe, just statistically speaking, it's crazy to think that we are by ourselves. But let's return to the science a little bit. How can we tell if an exoplanet has biology that's active on the surface? And the answer to that question, as Eddie will go into much more detail than I will today, is in analyzing the atmosphere. So the atmosphere is a window to the biological processes that are happening on the surface today. So if you didn't know anything about what's happening on the Earth today and just measured what's in the air, you could tell that it was a dynamic planet that has activity at the surface that is more active than what geology could do. For example, in our atmosphere today, you have oxygen and you have methane in the atmosphere, a reduced gas and an oxidized gas. If the processes were slow, then these gases would react to form carbon dioxide. But the fact that we have both oxygen and methane in our atmosphere means that there's biological activity that's contributing to this chemical disequilibrium in composition of our atmosphere. And I'll come back to what the importance of chemical disequilibrium is in the last portion of this presentation. So the telescopes that are flying and will fly will be able to measure the composition of this air by looking at the light from a star that's going through the atmosphere, and they will detect it on the other side. And the reason that you can tell the air composition is because the molecules in the air, different molecules, whether it is oxygen, whether it is nitrogen, whether it is CO2, absorb light at different wavelengths. So on the other side of what the telescope will see was a band of light with pieces that are missing. You can see those black lines there indicates that something in the air that the light went through absorbed that particular wavelength. And it's from this kind of barcode of light that you can deduce what the air is made of these far away exoplanets. So you don't necessarily need to go on the surface, although as a geologist, I'm very partial to that. But just by looking at the light from these faraway worlds, you can tell what the air is made of. That's incredible. And that's something we can do from the space telescopes that we have nearby the Earth. So we can look very far away at these worlds. So this is like a barcode. You go to the supermarket and you present the barcode to the teller, and that barcode is scanned. You can tell that it's an apple. And so that's pretty powerful. Excuse me for a quick second. Okay. So let's continue to this statement that I hope you will remember after this presentation and talk about with your family, that the colors of light from another world can hold the fingerprints of life. What's incredible is that the closest star to our own, Proxima Centauri, likely has an exoplanet. We don't know much about it. Still debated, I think, about the details of it. But nonetheless, we can play with our imagination again and think about a world that is familiar to us extraterrestrial but familiar nonetheless. So this is, of course, an artistic representation of what potentially could be the closest exoplanet to the Earth. So the star that you see is Proxima Centauri, which is an M dwarf, which is not a G-class star like our own. And in the sky, you would see this binary star system. This is the Alpha Centauri binary star system. My gosh, what a sight would that be? Huh? Super cool. But that's what astrobiology allows you to think about, because it requires knowledge of so many different types of disciplines that you bring together in a unique way. Astrobiology, more than just a discipline, it's an intellectual framework on which scientists from a bunch of different disciplines come together and solve these really hard problems, one of which is whether or not we're alone in the universe. And we all have been brought up all over our different countries in different ways of thinking. So that's why science, I find, is the most incredible universal language in our society today, where we can work with people from all over the world who have a little different way of thinking than you do. And and bring those thoughts together can help crack some of those really difficult scientific problems. So the best team for science are the international ones, because they all bring always a different piece to the puzzle, a different way of thinking, which is very, very needed to solve difficult problems. Okay, so I'm going to launch into the last part of my presentation. Am I doing on time here? Good. Hopefully it won't take me too much more longer, and then we can have some time for questions. The last part of this presentation I want to talk about is the famous concept of habitability, right? The quest for habitability drives the discipline of astrobiology. Where should we look for in this vast universe to find evidence of life? We can't look everywhere. So there are slowly criteria that are emerging that help narrow down the search. And the concept of habitability helps narrow down the search. But it means different things for different people. Right? Even on Earth, the concept of habitability for different species is different. For you and I, humans, we need oxygen in the air and not too cold and not too hot, right? Whereas a fish really benefits from being in water. If it's outside of the water, then it's in a condition that's not habitable for it. So habitability is this kind of general term that you have to be careful when you use, because it means different things for different people. So from an exoplanet science perspective, the concept of habitability means that the planet is just at the right distance from its star, that if there was water on that surface, that water would be liquid. If you're too close, it could be steam. If you're too far away, it could be ice. But from what we understand, at least for biology, and you have to be creative, but there's only one kind of life that we know of today, and it requires liquid water. And there are chemical reasons why liquid water is a very, very good solvent for supporting chemical reactions. So from an exoplanet perspective, it has to be at that right distance. But can we think of a way to express habitability that does not depend on biasing ourselves on terrestrial biology? And I think there is a little bit. If we look at it from fundamental properties of any active biological system, it's going to need several things. One, it's going to need raw materials, right? Sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen, those kind of raw materials on which you can build things like those information-containing molecules, amino acids, peptides, DNA. You can be clever in how you arrange these things, but the usefulness of these molecules, these atoms, sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen, is that when they fold, they can, through that fold, contain information as well. So there's a lot to be said for these raw materials. Solvent, you need a solvent. We can play with the idea whether the methane and ethane lakes that we see on the moon Titan, which is one of the moons of Saturn, is a good solvent for biology. The real incredible things about water is that it's a polar molecule, right? And so it can really facilitate chemical reactions in ways that ethane and methane cannot. We talked about raw materials. We are carbon-based life. There's stuff in the science fiction literature about silicon-based life. But silicon is really stable as a molecule, and for biology, you want atomic structures that can break and reform and break and reform, this dynamic chemistry that is typical of biology. The carbon chain is really good for that, because it can be in chain, it can be in circles, you can do a bunch of things with carbon and that you cannot do with silica. So there's something to be said about water and carbon that really drives our understanding of biology, and anything else really requires bending the laws of physics and chemistry a little bit to make it work. But let's never say it's impossible. That's the worst thing you can do in science, is say that something is impossible. We also require clement conditions. So clement conditions in terms of temperature, in terms of pH, in terms of salinity, in terms of pressure. It's also very dependent on the biology, right? My temperature conditions, clement conditions are probably different by a few degrees than your clement condition requirements for temperature. You find biology that lives exclusively in alkaline systems versus in acidic systems. Salinity is also important. We were talking about the stromatolites in Australia. The water is too salty there for a certain type of snails. And so salinity can also affect where animals are comfortable. So there's a lot of variables in a natural environment that can testify as to whether that environment can support life. And finally, perhaps the most important is that you need a source of energy. All the life that you see around you right now ultimately depends on sunlight, right? The sunlight powers photosynthesis, which is a food for many animals, and we eat both the plants and animals. So ultimately, everything that's around us is due to energy that comes from sunlight. But if you go to the bottom of the ocean where there is no sunlight, at hydrothermal vents, for example, you still find a lot of biology there, and because there's chemical energy that can be extracted from the natural environment as well. So I think in order to think about life on other worlds agnostically of terrestrial biology, the energy framework is really, really good. But it took a while to get there, though, because in the beginning, for example, in the Mars exploration program, the philosophy was follow the water. And for a good reason for that, like in all liquid water conditions on Earth, you find cells, right? Even in the plumes of hydrothermal chimneys, you find cells. And so wherever you find liquid water on Earth, at least you find about biology. Could that be true for other systems as well? The trouble of using the binary information as water equals life, no water equals life, is that not all water is created equal, right? A water-rich system is differently habitable for different organisms. And the reason is, it's not the water that's habitable, it's the stuff that's dissolved in the water that microbes can extract chemical energy from. So pure H2O, and you put a microbe in there, will die because it's just a solvent, right? What's really important for biology is to be in an environment that it can extract energy from something. And pure water, there's no energy to extract anything from. However, if you have stuff that's dissolved in the water, like carbon dioxide or hydrogen, then you have stuff that biology can take advantage of, right? It's this chemical disequilibrium that we talked about before in the water that can be harnessed by biology. To harness the energy can be harnessed by biology, yes. So in order to quantify habitability, by quantify, I mean I put numbers on habitability, we need to be very specific about the environment and be very specific about the type of biology that we're interested in. And so once you have these two, how do you then think about habitability? How do you associate numbers? How can you calculate using mathematics and physics numbers associated with habitability? From the energy in the system, can you say yes or no as to whether or not biology can thrive there? And so the way you would do that is to think of biology as a light bulb and think of the environment as a battery. So let me give you an example. If I give you a light bulb and I ask you, will the light bulb shine? You cannot give me an answer. You're like, Sanjoy, I don't know. I don't have enough information. What is the circuit that is connected to the bulb? That's what I need to have information about. I'm like, yes, you're quite right. Here's, so I'm giving you a light bulb and an electrical circuit. And I ask you, will the light bulb shine? And then you tell me, well, I still don't have enough information. Okay, what is the rating of the light bulb, right? Is it a 20-watt light bulb? Is it a 60-watt light bulb? Also, what is the voltage that I am given by the electrical circuit? Like, I need to know that too, right? You can have enough current, but if you don't have enough voltage, then your light bulb will not shine, right? So you need to understand both the voltage and the current of the electrical circuit and the rating of the light bulb to know whether or not the light bulb will shine. And that is true for biology as well. You need to know the voltage of the environment, you need to know the current of the environment, and you need to know the minimum voltage of the biology to take advantage of that natural electrical system, right? So that's the framework that you can use to attach numbers to calculate then whether or not the light bulb will shine, calculate whether biology can be active or not. So I'm going to use a very specific example to kind of illustrate this broadly. We won't go into any details in this presentation, but as I mentioned, you have to be very specific about environment and very specific about biology in order to do calculations. So the specific environment I'm going to be describing is called serpentinization. And the specific biology is methanogenesis. These are big words that I will explain in a second, but essentially serpentinization is a process that takes a mineral that is common on Earth and on other planets called olivine, and you mix it with water, common on Earth, common on other worlds. And what's cool about this geochemical reaction is that you form hydrogen as a byproduct of this chemical reaction. And methanogenesis is a biological process done by certain archaea, so bacteria's cousins are called the archaea. Methanogenesis is a process done by archaea that uses that hydrogen and react it with CO2 that's in the water to form methane, swamp gas, right? And so that's where you can understand, at least have an appreciation about the coupling that can happen between serpentinization and methanogenesis. So again, serpentinization is a geochemical reaction that reacts at its simplest the mineral olivine. You might have heard of the gem version, which is called the peridot. But olivine is common in lava flows, common in volcanic rocks. It's in fact what our mantle, the Earth's mantle, is mainly made of. And so when you react that with water, water is definitely not something complicated in our minds. There's evidence of water on Earth, obviously, on Mars, but also in the icy worlds like Europa and Enceladus. The picture there is a picture of Enceladus and the plumes that are jetting out, the water plumes that are jetting out, so that those geysers are tapping an interior ocean. And so olivine plus water, again, chemical reactions that are not unique to Earth, can form a bunch of different alteration minerals, serpentine, brucite, magnetite. It's not terribly important, but what's really cool is the production of hydrogen, because at its most fundamental level, hydrogen is a really good source of energy for biology. Now, you and I cannot operate on hydrogen, right? It's just not enough energy that we can extract to live. So that's why we use oxygen, much richer source of energy. In fact, a lot of rockets. I guys see the launch of JUICE this morning, the satellite that will explore the icy world. Super exciting. I'm pretty sure that the Ariane 5 rocket uses liquid oxygen as one of its fuels, because oxygen is so good at liberating energy. And so that's why we use oxygen to burn the carbon that we eat. But if you're a tiny life form, you can survive on much less energy. And so we can use hydrogen that's released by just water and rocks to reduce the carbon dioxide that's dissolved in the water, extract energy from that, and release methane as your byproduct, right? So you can see the coupling of hydrogen. You can understand what controls the production of hydrogen, and you can understand what controls the consumption of hydrogen. So you have this link, this mathematical link between geology and biology. And so what is the environmental voltage? How do you calculate an environmental voltage? Well, it's this concept that you may have seen or not if you've taken some of the advanced physics classes that are available to you. It's called the thermodynamic Gibbs free energy. Essentially, it's the energy available in the system that can be used to do work. So on the x-axis of this plot, the value is not really important, but you have from left to right, you have increasing amounts of voltage, essentially. So on the top right, the biological mechanism that's listed is CO oxidation. So that's carbon monoxide oxidation. Anything that's an oxidation that uses oxygen, you'll have a lot of energy for. And if you go towards the bottom left, you have a methanogenesis, which has, if you can see my, my arrow is at the very bottom there, close to 0 voltage, right? There's very little energy available. And if there is very little energy available in the system, methanogenesis sometimes can take advantage of it. So it's really important to properly calculate what the voltage is in the system, because it's very close to 0, but at least it's calculatable, because it's a fundamental property of thermodynamics that you can extract quantitative information regarding the amount of energy available in the system. And this Gibbs-free energy is the equivalent of the voltage of the environment, right? But I mentioned you need both the environment and you need the current to say something quantitative about biology. Having the voltage alone is good, it's better than nothing, but it's not conclusive. In terms of the current, so the current in the electrical system is the flux of electrons through the wires. For a biological system, it is the flux of nutrients into the cell. So for a methanogen, typically there is more CO2 in the environment than there is hydrogen. So the limiting nutrient, that's the one we have to pay attention of, is the hydrogen. How much hydrogen is flowing into the cell? And how can we calculate that? Well, at a very simplest way, the process is one of diffusion. Right? The biological cell is consuming hydrogen that has diffused into it. And so you can use the diffusion equation, again, a mathematical treatment, to calculate the flux of hydrogen or whatever is limiting, whatever nutrient is limiting into the biological cell. So you can use the diffusion processes, which are well established mathematically, to calculate an environmental current into a biological cell. And you can use the environmental Gibbs-free energy, again, very robust mathematically, to compute the environmental voltage. And using the two, then, you can calculate the power available in the environment, and using the power, make conclusive statements about whether there's enough power in the environment, enough power in your battery to fuel biology. Okay, so that's one kind of approach to think about how to associate numbers with habitability, is to think about the natural environment as a battery powering a light bulb. And so given those calculations, you can then go to the natural environment on Earth, sample waters. There are wells kind of dug all over the world. Here is Oman. Oman is interesting because the rocks that you see there is called an ophiolite. So those used to be underwater rocks that over time have been abducted on the surface of the Earth. It's a lot cheaper to go explore underwater rocks when they're on top of the Earth than when they're underwater. So here you have colleagues of mine that are sampling waters that are a result of this serpentinization process. And then using the chemistry of the water, myself and colleagues can make some predictions about whether or not these waters can host biology. And then I have colleagues who are microbiologists who will actually look for those biological species in the water. And can I confirm or not whether the mathematical approach is conclusive about whether there is biology in the system? So you can test the mathematical expressions of habitability with what's actually in the water on Earth. So the Earth is actually the best place to do astrobiology from my perspective as a geologist, because you can really have some theories about assessing whether or not an environment can host life. Okay, so this kind of concludes my presentation. Remember that our planet is a snapshot in time and in space. You and I were born essentially, if you stretch our mind about how long the planet has been around and how small it is in the vastness of space, you and I have been born at the same time and the same place, which makes you and I cousins, brothers and sisters. And as we understand the fate of our planet going into the future, and knowing that we can control its fate by our own behavior towards people from the world and how we affect the climate of our planetary system, hopefully these awarenesses in time and space can just help us become better humans for our planet. So with that, that's the end of my presentation. I thank you very much for your attention, and I'm excited to take some of your questions.
Okay, thank you. It was really amazing to listen you. And I will start with first question. Why are we looking at the planets having similar conditions with Earth? Why are even small differences affecting the life like that?
So there's the evolution of Earth and the evolution of biology actually interlinked. And so you can have small discrete events that completely change the direction of a planet, of a planet's evolution. A good example of that is the meteor that killed the dinosaurs, right? What world would we live in today had that meteor missed the Earth? Like, would we be intelligent reptiles? Like, I'm joking a little bit here, but we just don't know, right? Not only is biology and geology tightly linked, I mean, the more oxygen we have in our atmosphere, the more oxidized the minerals are, which, for example, oxidize the iron into iron oxide, which is what we as a society mine to create steel to build our civilization. Right? So if you don't have oxygen in the atmosphere, how would have society evolved? Would it have evolved at all? There's so many different possibilities of directions a planet can go that it's really hard to predict, because you have those kind of random events that happen as well, like meteor impact that can completely change the direction of biology. So when the meteor impact that killed the dinosaurs happened, it opened the ecological niche for mammals. Before, mammals were very small because if they became big, they were immediately eaten. Now that the main predators were gone, mammals could start, taking more of the ecological space for themselves. And that was just because of a random event. So it's really hard to I think there's no environment that's going to be the same. No planets are going to be identical just because of those random variations.
Okay. Next question. How much we close to understand all the required best conditions for life and interactions of them?
We're still discovering. It's amazing how resilient life is. In places where you least expect to find it, you will find it. Even going back to the 70s, it was not very long ago, it was thought that the seafloor was actually devoid of life, right? And then we discovered hydrothermal vents. And then we discovered the bacteria that are living in them. Also in deep mines, humans have been drilling deeper and deeper to create mines. You find biology there that has been disconnected from the surface of the planet for millions of years, and then it's still able to extract energy from the environment. So it doesn't take much for biology to find a way to extract energy from the local environment. The difficult part in my mind is not really thinking about how biology can take over energy that's available on a planet, but how it can actually get started. Like, I think the origin of life is a incredibly interesting but really difficult discipline, because we can go back to using the DNA family tree. We can go back to the last universal common ancestor, Luca, but there's a big gap in knowledge between the origin of life and Luca. So how do we bridge that gap? I think is a really interesting field of study as well.
Yeah. Okay, next question. If we mimic Earth atmosphere in a life-promising planet or trigger the process of building it, can we control also the start of microbial life?
That's the difficult part, is that so as I mentioned, the planet was very different in the early Earth, and it's maybe the life started underwater, not necessarily in an environment connected to an atmosphere. So we don't know, but we have to test, right? Some hypotheses about the origin of life state that it had to happen in a continental hot spring setting. So a hot spring on the surface exposed to the air and you had hydration and dehydration reactions going on as the hot water full of chemical species came and went. Some other hypotheses state that origin of life was at the seafloor, was in those hydrothermal vents, where the chemical conditions are unique and special and can start polymerizing some of these complex reactions. Other hypotheses suggest that it happened on a beach near a source of naturally occurring radiation, radioactive minerals. Again, hydration and dehydration plus the constant ionization of these radioactive minerals. We just don't know, so we have to kind of explore everything. It's not necessarily linked to the ability to control the atmosphere.
Okay, thank you. How would a globally warming planet would have geological signs billions a year later, or can we lose some of the geological knowledge due to the global warming side effects, such as acidic waters and warmer climate?
Yeah, so I mean, the rock record is not continuous, right? If you look at this, if you go to the Grand Canyon, for example, or any big canyon system, you can see all the different types of layers. Sometimes the layers are continuous, indicating a change in environment, and sometimes there is a jump, like there's very different kinds of rocks. And that indicates there was a period of erosion where the signature was erased. And so that's a natural way that geological evolution happens. Yes, ocean acidification is a problem, but if you find in the rock records, say, millions of years from now, seawater rocks rich in carbonates, and then over a period of time you see those carbonates disappear, and you can measure the isotopes, so the weight of the carbon atom in the sequence, you can tell that something has happened. I mean, even in the ice age records, we can tell when humanity started smelting iron, because you had a huge spike in pollutants that's then recorded into the ice. So you can do archaeology with that type of work as well. Some of these events are a bit young to have a strong rock record, but ice is also a good preserver of information. So yes, some geological events add to the rock record, some erase it. And so, but if they are erased in one locality, they may be added in another. So that's the fun part of geology, right? You're given a book with a bunch of different missing pages, and the missing pages are scattered all over the world. So if you try and piece together what the book says based on evidence that you gather at different locations. Because yes, in some localities, rocks might be destroyed, but in some others at the same time, they might be added. So you have to try and piece together that story.
Okay. Why is life based on elements like carbon and oxygen?
So the building blocks of life are sulfur, phosphorus, carbon, oxygen, nitrogen, hydrogen. There are people who do look at organic chemistry are much more versatile than I am about this. But as I mentioned, there are reasons why to think that water is really important because of the dipolar nature of the water molecules. The carbon chain is able to do a bunch of different aqueous chemistry, so chemistry in water. So there are good reasons why carbon is a good building block for more complex molecules. And there's not an infinite number of ways you can create molecules, right? The periodic table of the elements is finite, and if you're going to take small molecules and actually do quick and interesting chemistry, you're kind of limited to even smaller portion of it. So there's not an infinite number of possibilities. Of course, we are very much biased because we only know of one kind of living system, and that is terrestrial life, right? There is zero evidence of life beyond Earth at this point. Yeah. And so this knowledge really biases our interpretation. It's very hard to try to think about something that is still sci-fi.
Yeah. Okay, I will ask this question to you, but also I recommend you, Kerem Johnsons, to ask this question tomorrow to Dr. Svetlana Shkolyar, because he's also working on extremophiles. Could extremophiles on Mars survive hundreds of millions of years?
Yeah, no, absolutely. So the surface of Mars is not great for biology, just because the planet no longer has a magnetic field and doesn't have any oxygen in the atmosphere, or at least very, very, very little. And therefore, there's no ozone layer, and therefore, there's no protection from UV. So the surface of Mars is baked by radiation. So on the surface, that's bad. But if you go underground where you have a different type of conditions, I mean, we find evidence on Mars of flowing brines, so salty water, right? So there are pockets underwater of brines. And like Professor Dasarma will tell you tomorrow, he studies bacteria, extremophiles, that are adapted to salty environments. There are also bacteria that can handle very strong radiation. The famous one is Deinococcus radiodurans, who can survive like radiation from space, right? I mean, it's unbelievable what biology can adapt to in order to make a living. The hard part is starting life, I think. Once life has started, it is very good at evolving to find ways to extract energy. Now, evolution itself requires energy too. So if the entire planetary system only has a little bit energy, such that the biomass turnover, like the doubling time of a cell, is on the order of 100 years, just because there's so little energy there, then there might just not be enough time for evolution to take place, for those early cells to take advantage of all the chemical gradients that are made available to them. So yes, if you take a modern extremophile on Earth and place it on Mars, it may survive, but it has had the benefit of 4 billion years of evolution to acquire the skills to be an extremophile. And so whether those luxury of time happened on Mars, for if life started on Mars, had the evolutionary chance to conquer the planet and take advantage of all the chemical gradients, is a completely open question.
Okay. I will also read this question, but I recommend to ask this question to Dr. Shelley Johnson, because she will talk tomorrow about alien communication. Let's say we find a life form or sign of life. How will we communicate?
That's a great question. I love that question. Thank you so much for asking it. There is life forms on Earth that communicate very complex languages, and we have very little idea of what they're saying. I'm thinking about whales and dolphins. They have a very rich communication. They organize hunts together. They tell each other where to go, like very complex communication. And, we just don't know much of it. So, if an alien species would probably be of similar complexity, if not completely different. So if we cannot understand life that is terrestrial, understanding life that extraterrestrial seems even more far-fetched. However, you can look, even if you don't understand the language, you can probably find markers that suggest intelligence. Maybe there's a regularity of patterns in the sound. Maybe there's a regularity of patterns in the wavelength that the alien species transmits with. Maybe we can't understand them, but mathematics and physics is not going to change from one planet to the next. So maybe they can encode some fundamental mathematical principles, like prime numbers or something, in their communication that we could understand. If we receive prime numbers from a faraway planet, it's very unlikely that it's just a geological process, right? So we can't communicate without understanding each other by first building this kind of mathematical relationship between our worlds. And maybe a common language could be built from those initial mathematical connections.
Okay, thank you. Next question. How might the discovery of life on other planets impact our understanding of the origin of life on Earth? Could it suggest that life on Earth may have had multiple origins or was seeded by extraterrestrial sources?
Yeah, so because we don't know how life started on Earth, all these things are possible. So it's possible that life had multiple origins on Earth. But as things happened, Darwinism got going and competition happened, and one species got extinct and another grew stronger. And this has happened continuously over the history of our planet. Millions of species are killed as evolution happens. So it's possible. Biology originated at different localities. And whether panspermia is a thing, that's interesting as well. So that suggests that life started elsewhere and seeded the planets. There's no evidence of that. It's one hypothesis among others. But what's incredible is that if we do find evidence of life, for example, on Mars or on Europa, that would suggest that life can inhabit multiple planets within a solar system. That means that life is everywhere, right? And that's the importance of why exploring, doing astrobiology research on our own solar system, because the consequences of finding an independent origin of life on a planetary system so close to Earth means that life has started everywhere.
Okay, next question. Is the born of life on Earth affected of gravity on another planet?
Oh, could you repeat the question?
Is the born of life on Earth affected of gravity on another planet?
Okay, I didn't quite understand the second word, but I think I understand the gist of it. How gravity can affect life on other worlds.
Yeah. She is trying to ask how gravity is affecting the life in another planet.
Yeah, so completely. Our evolution is such that we humans don't really feel gravity, right? It's not hard to walk necessarily, unless you had a bad day. But we have evolved to handle the gravity. If we go to space, a lot of the astronauts must work out, put pressure on their bodies to keep the bones and the muscles strong, because we are so dependent on this gravity to keep ourselves healthy. In microgravity, our body completely decays unless we're actively working against that decay by doing a lot of exercise. So astronauts every day have several hours worth of gym time to do in order to keep their bone density strong and their muscles strong. So even from a human perspective, we're completely dependent on gravity for our health. And so we can imagine in the future, there's this TV show called The Expanse. I'm not sure if you've seen it. It's kind of based in the future where humanity has kind of like evolved kind of on Mars, and there's another subspecies called the belters. So there's humanity that has lived in the asteroid belts that tend to be taller and thinner, and when they come to Earth, it's really bad because gravity is so strong. So gravity really, really controls how evolution happens, for sure.
Yeah. This is the last question. Could there be other genetic codes like DNA?
Yeah, I mean, why not, right? DNA is one form of encoding information that's based on different nuclei. There could be other ways, and I think people are working on it, different kinds of so right now we have ATCG as like the main building blocks of DNA. Could you play around with that, and instead of a double helix, would a single helix work? Would a triple helix work? There's some chemical stabilities that suggest that a double helix is the best way to support this backbone. I'm actually not sure. I don't know the answer to that, but I'm sure these are questions that I thought about. There's nothing that prevents another type of genetic backbone to hold information in ways that could be transmittable, right? DNA is what our biology ended up using. I suspect it's going to be something similar, but again, I'm probably very much biased with how I think about biology based on the only life that we know of. So that's the cool thing about astrobiology. It really allows you to be scientifically imaginative, right? I gave you a few examples about imagining another world, about imagining life on Earth, but also thinking about those chemical systems in a new, creative way, I think has the potential to really unlock new, interesting scientific questions.
Okay,
you'll notice throughout your career that you'll be asking many more questions than finding answers, unfortunately.
Yeah. Thank you for those answers and this incredible presentation. Also, at first year for about serpentinization. Serpentines, Serhat Sevgen was actually explaining in detail, but there was a misfortune and he lost the connection, and then we again connect. but we have learned from him so much in detail about serpentinization actually. But,
Oh, wonderful. Yes, he
yeah.
knows a lot about it.
Yeah. And you have talked today also. But I really want to thank you for joining us here at this conference, because I'm feeling so lucky to have you here.
Oh, that's very kind. Thank you. I feel lucky to be with you today. It's the best part of my day today, absolutely, speaking to you.
Thank you. Thank you. Okay. I want to say see you.
Yep, see you soon. Have a wonderful evening, and have a wonderful rest of your conference. You have great speakers lined up. I'm very excited for you.
Yeah. I'm also very excited to listen to them. Okay, see you.
Okay, bye-bye.
We will move on with next session with Dr. Jacob Haqq Misra at 9:30 p.m. See you.
Hi everyone, my name is Banu. I am a member of Agenastro team. I will host this session, and our guest for this session, Dr. Jacob Haqq Misra. He is a senior researcher investigator at Blue Marble Space Institute of Science. His research focused on understanding the conditions that allow life to detecting signature of biology or technology on other planets.
All right, thank you very much. Thank you for hosting me here.
Hi, Dr. Misra, how are you?
Doing well.
If you want, I try to introduce you as much as I can, but is there anything you want to add?
I mean, I think that's good. You know, I'm part of Blue Marble Space. I think you've heard from some other speakers today who are also from Blue Marble Space. And yeah, you know, I am a scientist who studies planetary habitability, but what I'm going to talk about today is actually some of my research on planetary governance.
So if you want, you can start your presentation.
Okay, I think you should see my slides. Yep, there we go. So, who should own Mars is definitely a thought-provoking, provocative question, and so you know we'll unpack this question. What does it really mean? You know, I started off by asking myself this question back when we first heard about Elon Musk and other private space entities, as well as NASA and other agencies, thinking about sending people to Mars. And I started thinking like, well, who owns Mars? You know, and I was, as I just mentioned, I study climate and the climate of other planets, extrasolar planets, and Earth in the future, and Mars, as part of my work as a scientist. And at the time, I was a postdoctoral scholar at Penn State studying ethics, and specifically the ethics of climate. And so I was thinking about climate change on Earth, but then I also thought about like, well, if humans go to Mars, you could do things, you could build settlements, you could terraform the atmosphere of Mars. And then I started thinking like, well, there's a lot of human dimensions to this problem. How would we kind of govern ourselves on Mars, and who owns Mars? Who has the right to do such a thing? And so as I investigated this problem more, I realized that it's actually a question about sovereignty. It's about what does sovereignty mean on Mars. And so we will get to that in this talk. Between this question of ownership and sovereignty, and why are we even in space to begin with. So here's a picture of the sky. Hopefully you looked up and seen Mars. Recently Mars was really nice and bright in the sky. We have the moon, Mars, and Venus all up in the sky here. For most of human history, Mars was not really thought of as a place that you could go. Mars was a planet in the sky, and for ancient astronomers, the planets were wanderers. That's where the root of the word planet comes from the Greek, I think. But the stars were the fixed points in the sky. You look up every night, you'd see stars in the sky. The stars would move at the same rate as the Earth turns, as we know now, as not the ancients didn't necessarily know at the time. But the stars go around the Earth. They appear to go around the Earth. And the planets have different movements. The planets move at a different rate. Sometimes you see Mars go backward and then forward again, which they call retrograde motion. And so the stars were studied and the planets were studied, but they were not necessarily thought of for a long time as places that you could go. That's a recent development that we have in our times. And even the moon, similarly. So here's an image of Mars. On the left is in the visible, and on the right is in the infrared. This is from the Palomar Observatory, taken in 1959. So this is a ground-based telescope. This was about the best quality image you could get of Mars prior to the satellite era. So by this point, we did know that Mars was a place. We knew that it was a planet in the same sense of Earth. On the left here at the top and the bottom, you can see bright spots. Those are the polar ice caps on Mars, and you're seeing the reflection of the ice. And then on the right, you can see these white bands going across. That's evidence of upper level clouds, and we're seeing the infrared reflection of the cloud decks on Mars. And so here we've got evidence that Mars is a planet. It's got some sort of planetary processes similar to what we have on Earth in a general sense of the way a planet operates. So it's not just, it's different than the stars. But we haven't been there yet. This is a place you study remotely. So what changed? What allowed us to go from Mars being an object we study through a telescope to Mars as a place that we might think about going? And the answer is nuclear weapons. And so this is a part of space history that is very intertwined with politics. This is a picture of the mushroom cloud that resulted from the Hiroshima detonation of a nuclear weapon in 1945 toward the end of World War II. Nuclear weapons are intimately intertwined with the space race, and I'm going to argue that the nuclear arms race and the following Cold War is arguably the reason why we even continue to care about having a human presence in space. So what I'm going to do is unpack this a little bit. I'm going to show you a timeline here, and I'm going to show you events in history that correspond with a change in the number of nuclear warheads. On the y-axis here, you have the number of nuclear warheads, and I'm going to show you for the United States and for the Soviet Union. And then on the x-axis here, we have time. And so you can see right here already, in 1950, there were, I believe, 4 nuclear warheads in the world. There had been 2 that were detonated in Hiroshima and Nagasaki, and then the Americans had another 4, I believe, that were held on reserve. But you step forward just a few years, and now we're already getting to about 10,000 weapons total, or just under 10,000, with the United States having several thousand, and the Soviet Union developing a noticeable stockpile of their own already. Right here, we have the launch of Sputnik 1, followed by Sputnik 2, just I think a few months later. This was the first time that anyone on Earth had launched an artificial satellite around the planet. Sputnik 1 orbited the planet for several, I forget how many hours it was, maybe 40 or so hours, then fell and burned up in the atmosphere. I'm not 100% sure on that. It's in the book. But and Sputnik 2 lasted a little bit longer. They sent a transmission back to space. It was the first demonstration that this was possible, to launch something into an orbit of any kind of stability, and then send a transmission back to Earth. So this was a huge challenge to the United States in terms of its technological superiority. But what does this tell you? When Sputnik was launched, it requires 2 things. We focus on one of these things. One is the precursor to orbiting satellites that enable science and communication and other things that we like in our world. The technology required to put Sputnik into orbit is fundamentally the same technology that would be needed to deliver a nuclear warhead anywhere else on the planet. Now, the United States was not oblivious to this fact. So Sputnik being launched in orbit, it was more than just a sign that the Soviet Union is scientifically ahead of the United States. This was evidence that the Soviet Union has more precise capabilities to deploy nuclear weapons anywhere on the world than the United States. And that is an important security threat, not just a threat to scientific superiority. So shortly thereafter, NASA was founded, and the presidential administration and Congress all saw this as an important investment. And what I'll mention before I go on is that there was a discussion within the U.S. government as to whether or not NASA, whatever this space agency was going to be, should it be housed in the military? Should it be housed under an existing science branch like the National Science Foundation? And what was decided was to create NASA as an independent entity that answers to the U.S. government and is part of government, but is a civil agency. And that's why you have people who work at NASA have the title of civil servant. The NASA was intentionally not a military agency, and instead invested in training civilian employees, as well as employing contractors, investing in small businesses, working with large defense partners. So part of NASA's success is its ability to sort of stir up the U.S. economy and gain, not just its own government employees, but to really invest in a lot of other parts of the economy. This was a contrast to the model that the Soviet Union followed, which was the space agency was housed within the military. Everything was shrouded in secrecy, and oftentimes the designers of one rocket, their name might not even be known to people working on other projects. You didn't have a lot of cross communication between projects, and so arguably one of the reasons for the ultimate outcome of the Soviet Union space program may have been that its reliance on secrecy and housing it in this military culture made it less effective than a public and commercially partnered space program like NASA. But Russia had another first, and you can see just as Yuri Gagarin takes his flight, the first human to orbit the Earth, first human space flight, that is, you see we've reached above 20,000 nuclear warheads. I will pause here just to mention, you only need a handful of nuclear weapons to destroy all life on the planet. You don't need very many. You need tens of nuclear weapons to destroy life on the planet, really. Hundreds if you really want to be more liberal on your estimate. 20,000 nuclear warheads is already a catastrophic situation to be in. But this is the case where Yuri Gagarin takes his first flight, and again, this is a challenge. Even though the U.S. has a greater number of nuclear warheads, what I don't have on here is the quality, the type of nuclear warhead. And so what the Soviet Union is showing is that they have rocketry technology that can put a human into space, and they can survive and land and come back safely. And so although the United States has a large stockpile of nuclear weapons at this time, the Soviet stockpile is non-negligible, and arguably their technology is perhaps superior. And so people in Congress at the time were talking about how do you close the missile gap, meaning that there is a technology gap between the Soviet Union's ability to conduct precise rocketry and what the United States was able to do. So we continue escalating further. Perhaps the height of the Cold War is the Cuban Missile Crisis. So the Cuban Missile Crisis was an event where between the United States President John F. Kennedy and the Soviet Prime Minister Khrushchev, and it was discovered that there were missiles being secretly transported from the Soviet Union to Cuba, and these would have been capable of reaching the eastern United States in a very short time. And so the United States when they discovered this, was not happy about this, and essentially forced a naval blockade around Cuba, preventing further Soviet ships coming in. And for about a month, in October, the world was essentially at a standstill, waiting to see if we would have this unthinkable nuclear war happen. And after about 3 weeks or so of negotiation, the Soviet minister backed down, withdrew the warships. The United States withdrew the blockade. The missiles were removed from Cuba. The United States had some missiles, I believe, in Turkey, actually, at the time that the Soviets were unhappy with, and those were also removed. And so following that, we had the Nuclear Test Ban Treaty, which limited where you were allowed to test nuclear weapons. So prior to this, nuclear weapon testing occurred in the atmosphere and on the ground. And so after this treaty, everything had to be underground only for tests. So the world narrowly avoided, according to some analysts, nuclear war at this time. But the stockpiles would continue to grow. Now, the U.S. stockpile reaches a peak the same time the Outer Space Treaty was signed, 1967. I'll talk about the Outer Space Treaty a little bit more later in this talk, but one of the key principles of the Outer Space Treaty is this idea that space doesn't belong to anybody. Now, as nice as that maybe sounds today, the real motivation in this context was the United States didn't want the Soviet Union to claim the moon as part of the Soviet Union. The Soviet Union was equally worried that the United States might claim the moon as the 51st state. So the Outer Space Treaty represents a Cold War era treaty that was responsive to specific political threats and political momentum that was occurring at this time. So one of the things we'll also talk about a little bit later is the Outer Space Treaty did not necessarily anticipate the kind of world we have today, where you have commercial entities thinking about sending tourists to Mars or mining asteroids or anything like that. So it was a very different environment when the Outer Space Treaty was written. Shortly thereafter, NASA succeeds in the first lunar landing, and there was a series of lunar landings to follow. The Soviet Union continues to increase its stockpile. The day that the Americans landed on the moon, the Soviets actually had a crashed landing of an uncrewed spacecraft into the moon. So there was a crash landing on the moon the same day. The Soviets would continue to attempt to reach the moon. You know, the Americans had sort of been bested by the Soviets for a number of times with Sputnik, with Yuri Gagarin's flight. There was a number of other firsts that the Soviets were able to claim during this space race. But the Apollo lunar landing, in a way, was the technical scientific victory for the Americans, and at least gaining a notable first on the Soviet Union. The Soviet Union had another setback with its lunar landing program, its lunar rocket. In fact, the designer of that rocket died. There's kind of a tragic backstory where at one point he had been imprisoned in Soviet camps and had suffered some health problems. But because of the secrecy, Korolev is his name, and because of the secrecy surrounding the Russian program, Korolev's name was not even necessarily known to a lot of his colleagues or others in the space program in the Soviet Union. He was known as the chief designer to most people until his death. And with his death, not only went a lot of knowledge he had, but also sort of his position power within the Soviet military space agency. And so his successor just didn't have the same sort of charisma or institutional recognition by his peers to continue the Soviet lunar rocket program. But the Soviets would continue building their stockpile as the American supply declined slightly and then remained steady. There was the Strategic Arms Limitations Treaty, held in the early 70s. Just during the Vietnam War, shortly thereafter, the Saigon falls, sort of signifying the United States retreating from Vietnam. So the Vietnam War, although you think about this as just being some isolated conflict, the Vietnam War in many ways was sort of the terrestrial embodiment of a competition between superpowers that was simultaneously playing out in space. So as the lunar landing is occurring, where the United States is attempting to demonstrate to the Soviet Union its superiority in its rocketry technology and in its defense capabilities. At the same time, you have U.S. military forces in Vietnam attempting to send the same message to demonstrate that the military forces of the United States and its allies can withstand the ambitions of the Soviet Union and its allies to spread communism into Vietnam. And so, the fall of Saigon was a significant setback for that aspect of the conflict, and certainly marked a point of escalation in the Cold War. And so the Soviet Union gains on the United States in terms of the size of its nuclear weapons stockpile. We've got about 30,000 nuclear weapons on each side now. There's another strategic arms limitations treaty. Doesn't seem to necessarily be doing a lot of good, but some of there was some gains made in these negotiations in terms of the types of deployment you're allowed. But you can see, obviously, we're still increasing the number of weapons on the planet. Early 1980s, you have atmospheric scientists getting involved in nuclear winter research. The realization that we have this many nuclear weapons on the planet pointed at each other between the United States and the Soviet Union, pointed at each other with people at the trigger ready. There's a launch system, but there's only so many checks before you actually launch. And so if the United States were to receive a threat, for example, this is still true now, from the Soviet Union, there's a decision tree that you follow to figure out, do we retaliate by launching this nuclear weapon? And you have a very short time to decide that. So you could imagine that a false positive, like accidentally thinking that the Soviets launched a weapon and now we actually launch one at them. Theorists were really worried about this kind of situation, which they called mutually assured destruction. As soon as one nation launches a nuclear weapon at the other, it's game over for everybody, for the whole world, because you have so many nuclear weapons that you could literally extinguish life on the planet if you launched enough of them. On top of that, if that's not bleak enough, atmospheric scientists realized that the fires and the soot and smoke that accumulated from such detonations would essentially go through the upper layer of the atmosphere, through this tropopause into the stratosphere. It would dim the sun for probably several years, causing massive crop failure and difficulty in the ability to feed ourselves, and lead to, if not total extinction, certainly widespread collapse and massive starvation. And so there was a lot of lobbying. Carl Sagan was one of the scientists who studied this along with others. Alan Robach continues to study this. This is still a problem. But this was first raised in political context, and this is an example of scientists taking their science and trying to convey to policymakers that the science is suggesting policy conclusions. Although in this case, it's bleak enough already without nuclear winter. That's just the icing on the cake, in addition to the destruction from the weapons themselves. So by the early 90s, the Berlin Wall falls, signifying the reunification of Germany as a democratic country, signifying the retreat of communism from Eastern Europe, and followed by the collapse of the Soviet Union. And you can see that, of course, this is coupled with a drastic fall in the number of nuclear warheads as the Soviet Union is grappling with its ability to succeed as a state. It's losing its ability to manage its nuclear stockpile. The United States stockpile continues to plummet then as its primary adversary loses its hold as a superpower. We have another treaty to attempt to reduce the number of nuclear warheads, which to some extent has some buy-in. Finally, we have a resumption of NASA's Mars program. So NASA focused a lot on the moon. There was some initial, the Viking missions were sent to Mars in the early mid-70s. But beyond that, NASA actually really didn't focus very much on Mars during the 80s and the early 90s. And so, Mars being on NASA's radar again is possibly also correlated with the fall of the Soviet Union and NASA's ability to focus on other programs. India then, by the late 90s, develops nuclear weapons. So again, this connection between your space activities and your nuclear weapons doesn't go away even now. And so the fact that India has nuclear weapons shows that, number one, nuclear technology is becoming easier to develop. Other nations who were not one of the original nuclear superpowers are trying to join the club. And then if you have nuclear weapons, the ability to launch them, then you are a space power. You're one of the states that has a capability to put things into orbit. As an attempt to sort of revive its fledgling space program, Russia dabbled with space tourism, and they were the first. They launched Dennis Tito into space for several $1 million, and have launched a few others. And then ESA launches Mars Express, and ESA has engaged in a partnership with Roscosmos to launch several of their space missions, up until very recently with the war in Ukraine, where ESA actually broke its partnership then with Roscosmos. And that's an unfortunate case again, where politics on Earth is interfering with the ability to conduct space missions. And in this case, the next ESA mission, ExoMars, was supposed to have launched by now, and because of breaking their partnership with the Russian Space Agency, that mission is now delayed. But yeah, you can see here there's been other attempts to reduce the number of nuclear warheads. We are now under the 10,000 nuclear weapon mark. There's about 10,000 or so, 10 to 12,000 total between the US and Russia and the other nations. I'll just say once again, that's way more than you need to destroy all of life on Earth. But this is at least the trajectory we went on, and just emphasizing again the trajectory that the Cold War followed for both nuclear weapons and space, competition in space. This is not coincidental. So look at this. We have on the left an intercontinental ballistic missile made by Boeing. And on the right, we have a Falcon 9 rocket made by SpaceX. So what's the difference? What's the difference between these two? The main difference is what you put in the top part there. The SpaceX capsule, wants to take, maybe cargo to the International Space Station, maybe people. The one on the left, the missile has a warhead in it, but the technology on the bottom is fundamentally the same. It's a rocket. And so the sophistication of a nation's rocketry is directly correlated to its ability to deploy a nuclear warhead. Now, you can make as many jokes as you want about Elon Musk. I'm not going to stop you, but I'll point out one useful thing that he's doing, as well as any private agency that's engaged in rocketry. What we're doing here on the right, this is democratized rocketry. We have now taken rocketry out of the exclusive hands of the military, and rocketry is now something that the private sector can do. You democratize rocketry. Now, this is still useful from a political standpoint for the United States, because its own citizenry now is advancing the country's ability to launch with precision anything they want. Now, at the same time, Elon Musk is not going to get his hands on nuclear warheads. That's a good thing. We have the Department of Energy is in charge in the United States of who gets to use nuclear technology. And it's not going to be SpaceX for building nuclear warheads, especially. So the fact that we have now decoupled our rocketry from our nuclear weapons, I think this is a good thing. I think it's still there, though. The competition between the United States and China, for example, continues to play out in space, but you can do this in a different way. You can do this where it doesn't have to be who's building more and better missiles. You can now remove the warhead. You can fight a surrogate Cold War, and you can say who has better rockets, because everybody knows in the back of their mind that you could always put a warhead on that rocket if you want to. But we live in more peaceful times, perhaps, so we can just remove the warheads, keep it in the back of our mind while we play out sort of the same political Cold War, just without the focus being on the military capabilities, and the focus instead being on science. So I love this picture. hopefully you've seen this picture, but if not, this is the Perseverance rover now by NASA. And this is a selfie. This rover extended its arm and it took several images. It took a selfie of itself with right back in the back. That's the Ingenuity drone. It's a helicopter, essentially a mini drone that can fly on Mars. Now you ask yourself, why are we doing this? Now, I'm a scientist. I study Mars. I study the climate of what was life like on Mars. I am very excited about the science that a mission like Perseverance can do. I do want to know about what the evidence is for an ancient ocean on Mars. Is there evidence for microorganisms on Mars, either in the past or today? What kind of water is on Mars? I'm very interested in those questions. But is that worth all the expense, to put that there? Why do we have a drone on Mars? Okay, well, the stated purpose is we're testing powered space flight on other planets because in future missions, you're going to want to be able to use that drone to go explore other places on the planet that would be really hard to get to otherwise. Well, that's great. I don't disagree with that at all. At the same time, this is a very convenient political device. The fact that scientists have a genuine motive in exploring Mars, because what you're also saying with landing Perseverance on Mars and and landing, flying in the Ingenuity helicopter, the United States is saying to China, hey, look what we can do. Look how great our rocketry is. Look at how precise we can maneuver things in space and on other planets. So this is a demonstration, again, of rocketry and technological superiority decoupled from nuclear weapons, done in a very public way, but still sending a very clear message that drives competition. China has a Mars lander. It has a rover on the moon. And so, again, we're in this game of staying one step ahead of the superpower that you're challenging, but in a way that's not growing the size of our nuclear stockpile. If you haven't seen the footage from the landing of Perseverance, it's amazing. I mean, NASA did a really great job of kind of capturing the emotion and just the excitement of Perseverance landing. But it's not coincidental that it would be worth Congress investing in not just the mission, but also supporting that kind of publicity, because this again sends the message about, hey, look what we can do. And I don't even think this is bad. I'm not here to say that this is bad. Maybe this is good. What was worse is building up giant stockpiles of nuclear weapons. So if we can get away from that, and instead of building more weapons, we're building more spacecraft, okay, I think I'm okay with that. But I think it's important to keep in mind that missions like this are political first and scientific second, even if NASA says otherwise. The reason that the taxpayers and Congress are funding this is political. So let's get into the Outer Space Treaty. What does the Outer Space Treaty say? The Outer Space Treaty says space is for everyone. Article 1, the outer space is the province of all mankind. So anybody can launch something they want to in space. On the left, that's Sputnik 1. And on the right, that's Explorer 1. That's the first United States satellite that was developed at the Jet Propulsion Laboratory. Article 2, no nation can claim territory in space. So it says outer space is not subject to national appropriation by claim of sovereignty, use of occupation, or any other means. So you can go to space. You can't say any of it belongs to you. Now, here's the Americans unveiling the flag on the moon, and this was authorized by an act of Congress. And in that bill, they specifically said that this is not a claim of sovereignty by the United States to the moon. This is a symbolic gesture to celebrate the achievement of landing on the moon. But the U.S. Congress is very clear that this was not the United States claiming to now be the owners or the rulers of the moon. There's also a fun article you can look up about the technical challenges of unveiling this flag. It's actually very difficult to unwind this flag while you're in a spacesuit, and the pole had to be folded up a certain way and to keep it then stiff in the airless environment of the moon. So yeah, there's some interesting physics there. nuclear weapons stay on Earth? So here we have the direct connection to the Cold War history that I just showed you. Article 4 says the parties to the treaty will not place nuclear weapons in orbit or other kinds of weapons of mass destruction. Now, interestingly, this does not prevent any weapons from going into space, just nuclear weapons and weapons of mass destruction. Astronauts today regularly carry knives into space, mainly for utility purposes. Russian cosmonauts were regularly issued a standard issue Makarov pistol as part of their cosmonaut gear. This was mainly because in the early days, when the cosmonauts would land on Earth, they would land somewhere in Siberia. The other people in the space agency would try to track the trajectory of the capsule as it landed, with its parachute into Siberia, but it would take up to a few days before the astronauts were found. We didn't have the kind of GPS tracking we have now, and so for the few days, these astronauts are essentially camping in remote Siberia, waiting to be rescued, and of course worrying about being attacked by bears. And so one time there actually was a bear that threatened these cosmonaut campers. Their standard issue pistol was found to be ineffective. They somehow managed to get away from the bear anyway. And so then this pistol was developed. This is the TP-82. This is a triple-barreled pistol with the power of a shotgun. It has never been fired in space. If you were to fire it in space, you may damage the spacecraft and yourself. But this was the solution to bear attacks in Siberia. And I believe up until recently, or possibly now, there may still be a gun in the International Space Station. Check on that. But up until very recently, that was still the case. You own your stuff in space. So you can't say that the moon belongs to you, but if you put a structure on the moon, you can say the structure belongs to you. So ownership of objects in space is not affected by their presence in space or the return to Earth. So here's the International Space Station. International Space Station is a very interesting situation because it's modular. There's different sections of it. And if you're in the American section, it belongs to the Americans. So American laws apply. If you're in the Russian section, you're in Russian territory. Russian laws apply, and so forth. And so there's a lot of, sort of sometimes confusing or sometimes odd policies or rules or just ways you have to do things to govern an international project where people own different countries own different components. So the Outer Space Treaty was pretty successful. You can see, I'm going to show you a few maps of different treaties in this talk now. The light gray are countries that are party to the treaty. That means the country signed the treaty, and then they took it back to their home legislative bodies, and that their home government then approved the treaty, and so they're now party to the treaty. The treaty, they agree to be bound to the terms of the treaty. If you're a signatory, it means your diplomat signed the treaty, but it hasn't yet been approved by your country. So you can see the Outer Space Treaty has been accepted by a majority of countries. More importantly, all the nuclear powers have agreed to abide by the Outer Space Treaty. And so here, we've got the nuclear powers today with the United States and Russia. We have China, we have India, there's the UK and France. Now, Israel is widely assumed to have nuclear weapons by analysts, but Israel has never formally said they have nuclear weapons, nor have they denied having nuclear weapons. They maintain a policy of deliberate ambiguity, but Israel is generally considered to be a nuclear state. And then I've also included here Pakistan and North Korea. Now, Pakistan and North Korea don't really have the ability to launch satellites into orbit, but the fact that they've invested so much, so many resources into becoming nuclear states and having nuclear powers and nuclear weapons and using that as a bargaining chip, at the international table. this emphasizes the role that nuclear weapons still play in the world today. So even though we have widespread disarmament, you don't need very many nuclear weapons to be considered a threat. You just need the ability to have any of them, really. So I don't think space policy, of course, is going to be determined by whether or not North Korea or Pakistan participate in a treaty or not. But I've included them just to make the point that being a nuclear power continues to be highly relevant in today's world. But the Outer Space Treaty, accepted by most countries, by all the nuclear powers, and in general, this is considered to be customary international law. So even if you haven't really signed on to the Outer Space Treaty, it probably would apply if there were a court case that were to emerge in the future. The Outer Space Treaty is the only successful treaty that we have about ownership in space. So we've kind of answered the question already. Who owns Mars? Well, Article 2 of the Outer Space Treaty says nobody owns Mars because sovereign nations are not allowed to claim, to appropriate Mars in any way. So no one owns Mars, right? And space is for everyone. So there was an attempt in 1979 to go a little bit further and say, like, okay, well, what if we said that space belongs to everybody? Not just that space is open to everybody, but space belongs to everybody. And you have to have some kind of equitable sharing. So they declare the moon and its natural resources as the common heritage of mankind. So this is different than the province of all mankind. This is kind of the way lawyers think, but the province of all mankind is what we had in the Outer Space Treaty. Anybody can go there. Here we have the common heritage of mankind, which implies a belonging to everybody. And in this moon agreement, there's this idea of having a new international agency to govern sharing, an international regime that would include an equitable sharing by all parties and the benefits derived from resources in space. So the idea was, well, what if there was some sort of international moon mining organization, and whenever a state, a country, or a company goes onto the moon and makes some sort of profit from whatever they extract there, that has to be divided equally among all the nations of the Earth. So that idea was not quite as popular as the Outer Space Treaty. You can see here, there's a handful of parties and signatories to the Moon Agreement. None of the parties to the treaty have launch capabilities at this time. Australia does have a space program, but as of now, Australia does not have their own independent launch capabilities. India has launch capabilities. They've signed but not ratified the treaty, so they're not a party to the treaty. So they're not fully bound to this, and I don't think it seems likely that India is going to sign or to ratify the Moon Agreement. And then France is also a signatory that has launch capabilities and nuclear weapons, but is not party to the treaty. And I'm not sure, but France may, they may have no interest also in becoming a party to the treaty. So the Moon Agreement, very little support from the nuclear states. It's generally considered to be a dead treaty, an ineffective treaty. There's been deadlines passed for the Moon Agreement parties to come up with this international regime for sharing, and nothing is materializing. So then we can ask ourselves, okay, if that's all we have the Outer Space Treaty that still kind of applies to space, but it's very general. The Moon Agreement didn't work. So what can we say? Can we look for examples of cooperative sovereignty on Earth that we could apply to Mars? So examples where nation states are trying to maintain their independence, but also trying to cooperatively approach problems of shared governance. So the law of the sea was one place I went to. The how do we govern the oceans and the high seas and our coastal regions? So you can see that this is the agreement on the third law of the sea. most countries in the world are party to this. You can notice a couple of exceptions here. Actually, the United States is not party to this treaty. Also Venezuela, Israel, and Turkey. Now, there's also a group of landlocked countries here, but the ones I named are certainly countries of note that have access to water that have not agreed to this. I don't know enough about the history of Turkey's involvement, but I suspect it's the same reason for the United States, because my understanding is that this was kind of a uniform opposition. So today, the United States actually, and probably the other countries, they do abide by the law of the sea. There's one specific provision that was objectionable, and that relates to this idea of common heritage, just like in the Moon Agreement. So in the law of the sea, the way it's written now, the resources of the deep seabed were declared to be the common heritage of humankind. And there was then to be an international body, the International Seabed Authority, which we have now. This was created from the law of the sea to govern, who can drill and extract resources from the deep seabed, and then to enact some sort of equitable sharing of the profits from those resources. So the United States, mainly treaties have to be approved by the United States Senate, and so the Senate has repeatedly blocked any attempt to ratify the law of the sea. But the United States respects the other aspects, and the other nations too, other aspects of the law of the sea that have to do with navigation and freedom of movement and things like that. But so again, this idea of equitable sharing comes up as a theme, and so this is one of the points I make in my book, is that equitable sharing is very unlikely to gain buy-in from all the major powers. So as nice as it might seem to say, like, oh, wouldn't it be great if such and such big companies were to share all their profits with the rest of the world? Well, you're probably not going to get that in a treaty, because it's probably not going to be acceptable to all the major nations, and for possibly good reasons. When you can imagine that the nations that bear the greatest investment into technology, whether it's to reach space or to mine the deep seabeds, if you put heavy investments into that, you may want to make some profits out of that to recoup your costs. So it's not really clear what the answer is, but I at least think that the idea of equitable sharing in a treaty makes it much less likely for that treaty to gain sort of a status as general accepted international law. But another part of the law of the sea is worth thinking about for how it could apply to Mars. And in the United States and other countries generally also agree on how to do this. So on the left here, we have the land, your continental land area, and then going out to the right, we have the ocean. And this is the coastal area for any country that's a coastal state. So from the baseline where the land hits the water, a country gets 12 nautical miles out to the coast of a territorial sea. So that territorial sea is just like it's the land. The country can exert its sovereignty over that 12 nautical miles and say, this belongs to us. 12 nautical miles out from there is a contiguous zone where you're not allowed to say it's yours, but you can sort of exert military presence there. You can enforce exclusive access for your military only, and you don't have to necessarily allow passage through to others. Now, 200 nautical miles out from the baseline is exclusive economic zone. In the exclusive economic zone, a country does not have the right to send away anyone else. You have to allow rite of passage. You have to allow other activity from other states, but your country has economic exclusivity. So no one else can conduct mining in that area, or even science. If another country wants to do science in the exclusive economic zone of a different country's science, of a different country, you have to get permission. And you are encouraged, even if I was an ocean scientist and I wanted to do research off the coast of Chile, I would have to get permission to do that in the Chilean exclusive economic zone, and I would be strongly encouraged by the language of the treaty to seek out Chilean collaborators to do that research with. And so this is sort of a way of compromising, where you don't say that the nation owns that 200 nautical miles from the baseline, but they do have the exclusive rights to any economic value that could be derived from that zone. Beyond the exclusive economic zone is the high seas, where that's a free-for-all. Nobody can claim ownership or exclusivity to the high seas. And then the deep seabed is all in the high seas, where that's governed by the International Seabed Authority. So you could imagine doing something like this for Mars. You can imagine a settlement that has a contiguous zone, I've just made up some numbers, 12 kilometers, let's say. And maybe that's where you can't say that the settlement owns that, but you can say that they have the ability to conduct military maneuvers or patrol, or just like a keep out sort of zone. And you can imagine an exclusive economic zone beyond that, where that's where that particular settlement has the right to extract water or mine resources or something like that, and they could exclude others from taking resources, but not exclude others from the right of passage. And then beyond that is the Martian frontier, where that's open to anyone and nobody can claim exclusivity. So, that's just an idea. I'm just trying to think, what models do we have on Earth that could translate to Mars without having to invent a new treaty? In this case, you'd just be drawing on the precedent from maritime law and then applying it in sort of an analogous manner into space. Here's a picture of the exclusive economic zones of the world in light blue. So you can see that the light blue versus the dark blue is just open ocean, the high seas. An awful lot of the ocean, I think it might be up to a third or so, a lot of the ocean is claimed by nations with this 200 nautical mile radius around any coastal regions. You can see islands, tiny little islands in the Pacific and all over, really. Doesn't matter how big your island is, you get 200 nautical miles off the coast of the island. So in some cases, the exclusive economic zone claim is itself bigger than the land claim. And we show that here. Here's a bar chart showing the size of the exclusive economic zone in million square miles. France has the largest amount of water that it controls. You don't necessarily think of France as being a maritime power, but they are, followed closely by the United States. This is mostly because all the islands that those two countries hold. It gives you a tremendous amount of ocean that you have at least some control over to exert your economic exclusivity. And it's certainly no coincidence that in the United States we have 6 branches of the military now, 3 of which have to do with the water. We have the Navy, the Marines, and the Coast Guard. Water is very strategically important. And you notice Australia is third. There, maybe you think of them as an oceanic state. Now here I have Russia, Canada, and Brazil colored in gray. Those countries have more land than water that they control. So the rest of them are the opposite. These other countries have more area in the exclusive economic zones than they do land in the country. So this idea, and so thinking about Mars, well, it's sort of a double-edged sword. In some ways, it would incentivize the development of settlements on Mars. But just think about to what extent has this type of policy in the law of the sea then driven political tensions and driven challenges. And so here's one example: is China and the Philippines have both signed and ratified the law of the sea. So by the treaty, I have in light gray here where the China exclusive economic zone should be and where the Philippines exclusive economic zone is. China, however, follows this 9-dash line claim. So this is what China claims to be a historic claim. There's some old map that they sometimes reference that has these dashes on there, or it's sometimes called the cow tongue. And China asserts that it has historically engaged in fishing and other economic activities in the Yellow Sea here, and there's other areas too. And so the Philippines filed a lawsuit in the International Court of Justice claiming that China was breaching its obligations under the law of the sea by engaging in commerce that intersected here with the Philippines, EEZ. And the court ruled in favor of the Philippines, but the Chinese government didn't recognize the ruling. And so this continues to be a major political issue today. And, just keep this in mind, the South China Sea, this is South China Sea, I think the Yellow Sea, there's others where China may not engage in overt military action, but what you do get is sort of covert. You get incidents where the sea is swelled with a bunch of fishing vessels that happen to disrupt transport, because these can be very heavily trafficked naval routes for transporting goods. And so you get political interference, but not from military vessels, from commercial vessels, fishing vessels, and things like that. And so this continues to be a challenge in this case, where countries have agreed on the treaty, and yet the enforcement poses a challenge. So one other example we can talk about is Antarctica. And so Antarctica is possibly the real last frontier in terms of the last part of the planet to be explored. There was an effort in the early 1900s, intentional by the world's geographers and scientists, to map out and explore the poles, the North Pole and the South Pole. And so there were a number of countries that sent explorers who actually made claims to Antarctica. You can see the claims here. There's Australia has claimed 2 wedges, France a little bit, Norway, and then the UK has this claim in red. And you can see intersecting the UK's claim is claims by Argentina and Chile. There's a sector here called Marie Birdland. That's one of the only places on Earth that has not ever been claimed by a sovereign nation so far. And then there's also a claim that was exerted by Brazil a little bit later. So these countries all declared their they declared sovereignty. Australia, France, New Zealand, Norway, and the UK, some version of we were the first to get here. Some version of, we set foot here, Captain Cook was the first to see it at a distance, something like that. Chile and Argentina actually had a different argument. They said that that part of Antarctica was given to Spain by the Pope in a papal bull from the 1400s. And since Chile and Argentina descended from Spanish rule, that they were now the rulers of that part of Antarctica. And so that was also argued in court, and Chile and Argentina did not agree with the British position on that. The Antarctic Treaty System, it got a little bit more complicated here, but just to say overall, what the Antarctic Treaty System did was it suspended all of these claims. It didn't say they go away. You'll find this in a map. These claims still exist, but the Antarctic Treaty System said, let's suspend these claims. They exist, but we're just not going to enforce them. Instead, we're going to create Antarctica as a scientific oasis, a place where nobody is owning anything with the suspended sovereign claims. And it's just a place to build scientific bases with no military or commercial activities. So what we have here in the darkest colors, we've got Australia, Chile, Australia, New Zealand, Argentina, Chile, Norway, the UK, and France. Those are all the countries with stated claims. They have all said we have sovereignty over part of Antarctica. Now, the US and Russia have actually stated their right to make claims in the future. So they have not made claims, but they have said that they may have evidence that they could use to support a claim to sovereignty in the future, whatever that means. There may be something secret locked up that says, hey, a Russian or an American was here first, really, and here's the proof. We just didn't want to show it until now. So they have made reserve the right to make a claim in the future based on previous evidence. Then the rest of the next gray is consultative parties with no claim, and then we have non-consultative parties. So those are both participants in the treaty-making system. So here's the distinction. If you want to be part of the treaty as a consultative party, which means you have decision-making capabilities in the treaty itself. If you want to participate in the treaty as a consultative party, you have to have a research program in Antarctica. That's the rule that the treaty says. So a lot of countries then are incentivized to fund scientists to do research in Antarctica because they want to participate in the treaty, because this is the treaty that governs one of the 7 continents. So there's a couple of outcomes from this. One, you can see on this map, there's one continent that has very low participation in the treaty. South Africa is the only country in Africa that is a consultative party. And South Africa's participation in this treaty was very controversial until their apartheid government fell. Because a lot of the United Nations, for example, was very against the participation of the apartheid government of South Africa in this treaty. But that situation resolved itself. So one can imagine that many African countries may not have the resources to invest heavily in an Antarctic research program. And so if you can't do that, you don't participate in the treaty. Likewise, there might be countries that have no real interest in Antarctic science, but they have the political motivation to fund such things because they want to be part of the treaty system. So there's an interesting case that I'll mention briefly where Australia continues to exert sovereignty over Antarctica. Even though the treaty says sovereign claims have been suspended, Australia, as a matter of its national policy, continues to exert sovereignty to the extent that it can. And so what we have here in dark gray, here are the parts of Antarctica that Australia has claimed, the Australian Antarctic territory. The Australian Parliament passed a bill, an environmental protection bill, that established a whaling sanctuary, which you can see in light gray. So the whaling sanctuary is like the exclusive economic zone. It goes all the way around Australia and the islands it controls, and then they exert it on the coast of Antarctica where they claim they control. Now, Japan was engaged in what they called a scientific whaling expedition, the JARPA 2 whaling program. And you can see here in the dashed lines that the Japanese whaling program included much of the Australian whale sanctuary in Antarctica. And so the Humane Society filed numerous court cases, lawsuits documenting the whales that Japan harvested in the Australian whale sanctuary, and trying then in Australia, in the Federal Court of Australia first, and then later in the International Court of Justice, trying to show that Japan had breached the conditions of this whale sanctuary and therefore should be found liable for that. The courts ruled that Australia could not enforce its sovereignty. The Federal Court of Australia attempted to do this, but the International Court of Justice said that Australia could not enforce its sovereignty in Antarctica without undermining the Antarctic treaty system. So as far as the whale sanctuary goes, Australia was not able to use that to halt the Japanese whaling program. Now, through a different set of court proceedings, the Japanese whaling program was found to be non-scientific, and so Japan was forced to withdraw the whaling program. Japan responded by withdrawing from the whaling treaty itself, notifying the International Court of Justice that it no longer recognizes the court's jurisdiction over maritime matters, and then starting a new commercial whaling program where they just do what they want anyway. So in this case, it's not clear, who the winner is. In one sense, there's a moral victory where Australia sort of won a technical battle against Japan by getting the whaling program shut down and getting sort of a local enforcement of its whaling sanctuary. On the other hand, Japan just exited from the global whaling treaty and is just going forward with commercial whaling, which is kind of the opposite intended outcome. So it's not really clear how well these treaties work, but but the enforcement is always the difficulty. When you have sovereign nations that come into conflict, is there a higher authority? And I think this is another one of the problems. Most nations do not want a new higher authority to tell them what to do. The International Court of Justice has limited effectiveness because of this. And so I think we can't count on that. We can't count on a new world space agency to be the super police and tell everyone what to do, as much as some people might like that. Forget about worrying whether or not the World Space Agency becomes corrupt. That's a separate issue, but it's probably not going to be popular. You're just not going to get total buy-in for a country to give up some of its sovereignty to a new entity. One other thing, we could think about is, are there areas of Mars that we want to preserve? Maybe you want to set aside the way we have, state and national parks. Maybe you want to preserve, Olympus Mons or the Marineris Valley or, the Hellas Basin, or maybe this historical park where the Viking landers went. So maybe there's some preservation ideas that we want to carry forward from Earth too, in terms of how we might use Mars. But now I'll end by just talking about a different idea, which I also talk about in my book. What if we did something more radical? We said, let the Martians own Mars. Now, what I mean by that is, if we really are thinking about people who permanently go to live on Mars, well, if you're permanently living on Mars, maybe we should think about it, not that you're an Earthling who's living on Mars, but you're now a Martian yourself. If that's your home planet, let's think about this in terms of what I call planetary citizenship. And maybe Earth and Mars are like planetary states or planetary nations. They themselves, you don't have, Mars relating to different countries. What if you had Mars and Earth sort of as juridical peers, in the sense that they're planetary equals? And so the people who go to Mars think of themselves fundamentally as Martians, and maybe the Martians themselves are who we would think of as the owners of Mars, rather than any people or entities on Earth. And so I come up with this sovereign Mars model with just a few kind of ideas to get us thinking about what would it mean to truly think about Mars as sovereign. So you could say that each person gets one planetary citizenship. So if you're on Earth, you're an Earthling. If you're on Mars, you're a Martian. You can visit and go from one planet to another, but you can't be a citizen of both. You get to choose. You can only gain money and power on your home planet. This prevents some entity on Earth from exerting too much control on Mars. And then it keeps the powers on Mars investing in Mars itself and building the society on Mars. Earthlings can do science on Mars only if the Martians agree. So this is kind of going back to the idea on the law of the sea, where you have to gain permission to do science in the exclusive economic zone of another country. And then also recognizing the Cold War history, where science has traditionally, in many cases, been a vehicle for politics and for political goals, rather than the science as an endpoint in and of itself. So in order to prevent Earth policy from using science as a tool on Mars, the Martians get the final say in whether or not that should occur. Only Martians can decide how to use land on Mars. Again, this goes back to the idea of just preventing too much exertion of control from Mars to Earth. And then finally, Earthlings may give gifts to Martians, but may not make any demands. Now, this is the most difficult one, because if you want to have a sustainable civilization on Mars, you need a lot of stuff from Earth. You don't have enough raw materials to, at least not right away on Mars, to sustain yourself. So you need to bring stuff from Earth. So how do you prevent Earth resources and Earth powers from using that to control Mars. Well, here I say, well, it can be a gift. You can bring resources, you can drop them off. The Martians get to use them however you want, however they want. You can't make any demands from them. Now, I get into this a little bit more in the book. I am not at all saying that this is the most likely thing to occur. This is obviously very idealistic, but I think it's good to start thinking about what are some of the models that we have that work on Earth, what are some of the ones that don't work, and then even start thinking, what would we do if we really wanted to do something different? I don't believe that this is probably exactly how it will play out. That's unlikely. What I'd like to do is start the conversation about what are some new ideas that we could think about for how to think about sovereignty and how to build governance structures on Mars. And I think that now is a really good time to think about that. So my book is Sovereign Mars. It is available now. I talk about, in detail everything I've talked about here. I talk a lot more about the Sovereign Mars model. I also talk about some other things about how going into space will help transform our way of thinking and how it might give us new perspectives on both ourselves and our civilization. And so just in closing, we'll turn it around. Here's a picture of the Curiosity rover on Mars looking back at Earth. And I love this picture. And I find this picture to be incredibly inspiring. But if I think about standing on Mars, looking back at Earth, this is terrifying. I mean, I think about wow, look how far away my home is. Why did I come here to Mars? And I think about well, how long is it going to take for the resupply mission to get here? And what if my flight back is delayed? I feel like this experiencing this as a human is going to reveal to us a lot of psychological and emotional sides of humanity that we haven't seen before. And I'm not sure we're ready for it yet. I think a few astronauts will be ready, but I think most people who say they want to go to Mars probably aren't ready to go to Mars yet. But I think it's certainly worth thinking about how would we build civilization on Mars and how would we adapt, and are we ready for that yet? So I'll just leave you with some questions. Are we in a new Cold War? Are government and commercial interests really decoupled in Mars? Can you have science without government interest in sovereignty on Mars? And will we ever get new space treaties? Or basically, do we have to think about new ways to govern ourselves in space? So that's what I have. Thank you very much.
Thank you for your presentation. It was wonderful. And now, if you want, we have a few questions for you. If you're ready, I will start the question. First question is, just 1 second, please. Okay, I am so sorry, but just 1 minute. Okay, question is, if a habitat is established on Mars, how and according to what should we determine the rules?
That's a good question. So the Outer Space Treaty tells you a very limited number of things. But what I get into this more in the book, the Outer Space Treaty does say that a government agency, a country, is responsible for overseeing the activities of any non-government agencies that launch into space. So if SpaceX goes into space, they are bound by American laws. So immediately by that at least determines some set of rules. You are bound by American law for how the crew interacts with each other. And in that case, SpaceX might have their own rules for how the settlement is governed. Now, if you have a settlement that has multiple partners, multiple countries, or many different commercial partners, then it has to be an agreement between them, either like the Artemis Accords, where the different countries agree, or really just contracts between companies. But I think that it's going to come from the bottom up. It's going to be small agreements between everybody who's involved, rather than from the top down, where you get new treaties or new laws that govern it.
Thank you. And next question: if we hope to leave this world one day and live on Mars, we will have to change. But is it ethical to radically change ourselves and create new people who have to stay in their own design?
I do think that everyone who goes into space should do so of their own free choice. So I don't consider any situations where people are being forced to go into space. And if we're talking about, sort of bioenhancement or something like that, that I think, the ethical problems are certainly more difficult if you are coercing someone to do this. Now, if you're talking about, sort of genetically engineering, future people to be more adapted to space, that's also, there are definitely some ethical challenges for that. So, but I don't think that's what people like Elon Musk are necessarily talking about. I think what they're talking about is, sort of you get on a spaceship, you go to Mars, you stay there for, 2 or 4 years or so in a space hotel, and then you come back. So for that, I think then you don't have to worry so much about changing ourselves. But certainly, if you were to go the bioenhancement route, there are a lot of ethical challenges to bioenhancement for sure.
Thank you. And third question is: if there is an environment on Mars where living things can be found, could another living thing be the reason for its extinction?
Sure. Yeah, that's possible. It's possible that there is current life on Mars, microorganisms living in, maybe shadowy, moist regions of the planet, maybe underground. It's also possible that Earth life has already contaminated that life on Mars. We have landers and rovers and crashed landers on Mars. It's plausible that a piece of rock or something with some Earth microorganisms was ejected into one of these slightly more habitable niches on Mars and found a way to take hold, and maybe it outcompeted life on Mars. So sure, it is certainly possible.
And another question: is it ethical to Earthize Mars, that is to create opportunities where we can change Mars without changing people?
Oh, okay. I think maybe this is like terraforming, right? To make Mars, the climate, more like Earth. That's a great question. Is it ethical or not? It depends on what ethical framework you take. In one sense, you may say that you could take a sort of planetocentric view and say, well, Mars has value by itself because it's Mars. It has its own history. We don't want to mess with that. Or maybe we find life on Mars and we say we want to leave that alone. We want to let Mars belong to the Martian microbes. Maybe you take a biocentric viewpoint, though, that says life is good and more flourishing of life is good. And so then if you can take life to Mars and make life more flourish more, then that's better. And so those are two different viewpoints. It really depends on what your ethical framework is. Because if you believe more life is good, then terraforming might also be a good thing.
Okay. In addition to para-ESOI questions, does radical change of people do any good? Shouldn't it be evolutionary process? This also takes time.
Absolutely. No, that's I believe that's how it will happen. That people who go to Mars, I don't think bioenhancement is really going to help us at all. I think, if we do survive on Mars, then the adaptation will be slow. And then if we really survive on Mars for long periods of time, then there will be evolutionary divergences between populations that remain on Earth and populations that remain on Mars. But that's a very long process, and over at least tens to hundreds of thousands of years.
Okay. Another question is that ethical or possible humanity not move to another planet, but just factories move there?
Yeah, it's a great question. My collaborators and I, we call these service worlds. So could you use a world just for industry or agriculture or something like that? Is it ethical? It depends again on your ethical framework. So if you believe, in that Mars has value by itself, or we have life on Mars and you don't want to touch it, then you would say maybe that's not ethical. But maybe you say that it's better to pollute the atmosphere of a planet like Mars that's dead because that makes life better on Earth. So in that case, you might say that is ethical. So it really depends on your ethical framework.
Thank you. And okay, this is last question. Space said they plan to make a manned landing on Mars in 2025. Do you think they can make this landing? And can they establish a habitat there in the future?
I don't think they will be successful by 2025. No, I think they're at least 10 years out, if not longer. But eventually, I think they will. But I would say closer to 2035.
Okay, thank you for your answer. Our questions are over. And I want to say, if I make any mistake, I'm so sorry. And thank you being a part of our conference. And thank you for your time as well. I have to say goodbye to you. But before goodbye, do you want to add anything?
No, just thank you very much for having me. This was really fun.
Okay, so see you. Have
See
a
you
nice
later.
day. Okay, hi everyone again. I am so sorry, but this was last session for today. Thanks to everyone who watched us, and thanks to all my friends. I hope you enjoyed. That's why sen konuşabilirsin Zeynep.
Okay, so thanks everyone because you joined us today and watch us until this hour. It's too late, I know, and you are also tired. And we are really enjoyed today, and we want to see you tomorrow at 1 p.m. We will continue with Dr. Dimitra Atri. See you.
Yes. Thanks, everyone. See you tomorrow.
Okay. Bye-bye.